All right, people. I believe everybody is doing great, nice, and absolutely fine. I just need to know in the live chat itself if I am audible and visible properly. Let me know. Yes, let me know. And is everybody doing great? All the people, send the thumbs up in the live chat, send some fire, send some hearts, okay? And we'll be starting this electrostatics chapter, okay? We'll be killing the entire chapter in just one go, in just one shot, okay? Yes, I can see a lot of people out there. And do like this session. Make sure you hit the subscribe button. You like this particular session, okay? Because before starting the session, you are supposed to mark the attendance. That is mandatory. Okay, cool. Great. Let the people join and we'll start accordingly. Okay. So we'll be basically completing the entire chapter, all the topics, okay? Whatever the topics are there in the complete electrostatics, we'll be targeting those. We have previous year questions. We have sure shot questions, okay? Which have high chances that they can be asked in the NEET, in the upcoming NEET on 5th May. So we'll be targeting all those topics. We'll be targeting all those problems also, okay? Okay, cool. Good evening. Duration of the class, we'll see. It can go up to 6 hours, more than that. Okay. And we have the Telegram channel, that's Unacademy NEET English. I want you guys to join that, okay? Because we'll be putting up the notes over there only. So let the people join and we are starting the session. We will start the session. Yeah, breaks will be there. I'll be giving you the breaks also in between. Okay. Yes, JE students can also watch this session. Cool. So, guys, almost I say 300 people are watching and the likes are only 194. I want you guys to basically like this session as soon as possible. Then only I'm starting this session. Okay? Great. Okay.
So what's up, guys? How are you all doing?
we have someone over here. Okay.
I hope everybody is super duper excited about Yawar sir session, yeah? Right, people? All set? Guys, there should be some fire signs in the chats. There should be some fire emojis in the chats. That's how we'll get to know how excited you guys are. Quickly, people, everyone, and call up everybody. Call up everybody. Whosoever is preparing for NEET 2024 as well as 2025. This particular session is going to be amazing, my dear students. It is absolutely going to be amazing. So I would want you guys to call up everyone. Yes. Call up every single guy, whosoever is preparing for 2024 NEET 2025, right? This particular session is for everyone because Yawar sir, he's absolutely going to start from the basics, from the scratch.
From the scratch,
yes. And slowly he'll be scaling up the things.
Okay.
Super duper excited? Yes.
Are there any more surprises coming up on this particular channel?
Absolutely. There are more surprises coming up. We'll let them know after some time.
Yes.
Guys, can you let us know from where exactly you are watching this session? Which state you guys are from? We just want to see. Because we are right now live from Srinagar, J&K.
It's very cold over here.
Yeah. Just let me know quickly in which part of the country you guys are watching this particular session from. Quickly, everyone.
I guess most of the people are from South India.
Yes. Majority is from Tamil Nadu. Wonderful.
Great.
Tamil Nadu, Andhra, Bangalore, Telangana, Kerala, Bihar. Wonderful, guys. Wonderful. Great. By the way, before Yawar sir starts the session, let me tell you, on 23rd of this particular month, 23rd December, we have arranged a mega offline event in Chennai for all the NEET aspirants. Will be there, your complete NEET English team will be there. There will be NEET toppers, basically, who have qualified this particular NEET with amazing scores in 2023, 2022. You will get a chance to meet us. You'll get a chance to interact with those toppers as well. There'll be a lot of influencers who are going to absolutely motivate you, my dear students. Okay? So remember the date, 23rd of December, right? That is coming out to be Saturday, I believe, at 5 p.m. The event will start. Okay?
Exactly.
And in order to join that event, you just have to fill one Google form, right? The session which you guys are watching right now, in the description box of the video, you'll find a Google form, and I can see, right? The Google form will be pinned in your live chats as well. You just have to click on that Google form, fill it once. It will not take more than 10 seconds, right, people? So that it'll be an amazing event, amazing offline event in Chennai with complete Unacademy NEET English team. Yeah.
Okay. Whatever the doubts you have, you can come over there and you can ask the doubts to the NEET toppers or the teachers over there.
Exactly.
And clear those doubts and crack the NEET, kill it.
And see, we are starting this journey. We are starting to, we have just started. The first event is going to be in Chennai. We'll meet you guys in other states too. The ones who are from AP, the ones who are from Kerala. There will be other events too. You need not worry about that. Okay?
Yes.
Perfect. All right. So I think Yawar sir is about to start the session.
Let's. Okay.
Wishing you all the luck and wishing you luck too, guys. I'll keep on coming in between. Okay? I'll keep on coming. I'll keep on boosting up. Yeah.
Cool.
Chalo, take care.
Chalo.
See you.
Thank you. So let's basically start the session. We'll start from the scratch only. Just a second. We will be starting from the scratch. Just a second, guys. Okay, guys. So let's basically start the session. Let me just tell you, if you have not studied the electrostatics before, if you are watching this for the first time, you'll get to understand each and every single point. I will not go in much detail, but let me just tell you, I'll be to the point, okay? And I'll tell you the amount of detail, amount of concepts, okay? The detail regarding the concepts, only that much, which you actually need in order to solve a problem, okay? I'll not go in much detail. I'll be to the point. So let's basically start this particular journey. Make sure you stick to this particular session till the end, because at the end, you would be able to solve each and every single question, okay? So first and the foremost thing in this electrostatics, we will be talking about that is nothing but electric charge. That is nothing but we say electric charge, okay? See, when it comes to the kinematics, when it comes to the mechanics, we say, sir, we talk about the acceleration. We talk about the body is in motion. We talk about the velocity, displacement and all. But when it comes to the electrostatics, we talk about the charges, okay? There is a charge, sir. It creates the electric field around it. Two charges are applying some sort of force on each other. Now, over here, the first topic that we need to discuss in this particular case, that we need to discuss is nothing but we say electric charge. See, what this electric charge is all about. Let me just tell you over here. Let's suppose I have a comb over here, okay? This is a comb. Okay. Now, what I'm doing over here is that I'm rubbing this comb with my hair. Okay. I rub this comb with my hair. And there are some piece of papers placed over here, small piece of papers. I'll just write piece of papers. Okay. And you might have done this experiment at your home when you were kids. You rub the comb with your hair and then you take this comb near to the piece of papers. Tell me what's gonna happen. These piece of papers will get attracted towards this comb. These piece of papers will get attracted towards this comb. Attraction will be there. And if I ask you, why is this attraction over there? Why does these piece of papers stick to this comb? You'll say, sir, simply because see, something gets occupied on this comb. If I have a comb, before rubbing this comb with my hair, if I take it near to the piece of papers, it will not attract those piece of papers. So once I rub it with my hair and then afterwards if I take it near, they will get attracted. They will get attracted. They will stick to the they will stick to the comb. So we say, sir, this attraction is only after you rub this with your hair. So we say after rubbing, something gets occupied on this comb, and this something is what we call the electric charge. So we say comb gets charged over here, this comb gains the charge, and because of that charge, this attraction took place. Because of that charge, this piece of papers, they were attracted towards the comb. Okay. Now we say, sir, this electric charge is something due to which a body shows, we say magnetic and electrical effects. Yes. So it is because of the charge only. These piece of papers are basically being attracted. Attraction took place over here. So we say electric charge is something due to which these magnetic effects, electric effects are basically shown over here. I hope this is clear. Now listen to me very carefully. I'll scale up the things. Let me start from the scratch. Okay. Now, when it comes to the electric charge, sir, we have studied there are two types of charges. The first is, we say, sir, positive charge, and then we have, sir, negative charge. There are two types of charge, positive charge and we have negative charge. And when we have, let's suppose if we have a positive charge over here and if we have another positive charge over here, I'm taking one positive charge nearer to the another positive charge. We say they will repel each other. They will repel each other. Why? Because positive repels, like charges repel each other. And if we have, let's suppose, positive charge over here, and if we have over here negative charge, we say, sir, these two charges will attract over here. Why? Because positive and negative, unlike charges, attract each other. Is everybody able to understand each and everything? Is it clear to everyone? Yes. Can you please increase the volume? Are you able to listen each and everything? Okay. Great. Is volume okay? Give me a thumbs up. Is volume okay? Give me a thumbs up, everyone. Okay, cool. Now, if we have, let's suppose we have a negative charge over here, we have another negative charge over here, they will also repel each other, okay? Because we know when it comes to the like charges, they repel each other. When it comes to the unlike charges, they attract each other, okay? I hope each and everything is clear. And one more important thing is, sir, when it comes to this electric charge, the symbol of electric charge is nothing but Q. We say, sir, on this body, let's suppose if this is a sphere, on this body, we say Q is equal to 2 Coulomb plus 2 Coulomb. Q is equal to 3 Coulomb. Like we say, symbol of mass is M. M is equal to 2 kg, 3 kg. Over here, we say Q is equal to 2 Coulomb. Okay. And when it comes to the SI unit, we say it is nothing but Coulomb. Okay. Like we say mass is equal to kgs. Over there it is kg, over here it is Coulomb. I hope each and everything is clear. Sir, electric charge is something due to which a body shows magnetic as well as electrical effects. Over here, when this comb gains the charge, because of that charge only, this attraction over here took place. These piece of papers got attracted over here. Now, we will talk about the neutral body, the positively charged body, and negatively charged body. Let's suppose I have a rod over here. And on this rod, we say the amount of positive charge is equal to the amount of negative charge. The amount of positive charge is equal to the amount of negative charge. I can say over here. So we say when the number of positive charge is equal to the number of negative charge or the amount of negative charge, then in that case, we say the body is a neutral body. If, for example, I have a rod over here, the amount of positive charge is equal to the amount of negative charge, then we say this is a neutral body. And if I have a rod over here, okay, there is a body. And on this rod, we say, more positive charge is present as compared to the negative charge. When we say number of positive charge is greater than number of negative charge, in that case, we say the body becomes positively charged body. As simple as that. And when it comes to over here negatively charged body, let's suppose we have the same rod. And on this rod, if we say negative charge is more as compared to the positive charge, we say, sir, number of negative charge or the amount of negative charge is greater than amount of positive charge. Then we say it is negatively charged body. As simple as that. Is it clear to everyone? Is it clear to everyone? Let me know, is it clear to everyone? Okay, as I told you, I'll be to the point, specific. We will not go in much detail. The amount of information that you need in order to solve a question, we'll be doing that only. Okay. Yes, clear, great. Now see, let me just tell you over here. Now we'll talk about the properties of charge. First property is nothing but we say charge is conserved. Okay, what are the different properties of charge? Charge is conserved. Let me just tell you, my dear friends, over here, let's suppose we have a box. This is a box I am having over here. And inside this box, we have a ball which contains plus 2 Coulomb charge. Okay, we have this box. Inside this box, we have a sapphire or a metallic ball. On this metallic ball, plus 2 Coulomb charge is present. Now we have another ball. Let's suppose on this plus 3 Coulomb charge is present. And we have another ball. On this ball, we say plus 4 Coulomb charge is present. Okay. Now, could you please tell me what is the net charge present inside this ball? You say, sir, net charge is nothing but 4 plus 3 is 7. 7 plus 2 is 9. That is plus 9 Coulomb. Okay. Yes. Now, what you are doing is that you'll take this box and you'll shake it. Okay. You'll take it some other place and you'll keep on shaking it. You'll throw it up and then it falls back. Okay. Then afterwards, you place this box over here. Afterwards, you place the same box over here. Cool. And you observe that while you opened this box, you observe that inside this ball, it was 1 Coulomb charge, plus 1 Coulomb charge. Previously, inside this first metal, inside this first sapphire, it was plus 2. Now it is plus 1. And inside this second ball, you observe that it is, I would say, plus 4 Coulomb charge, okay. Now inside the third ball, if I ask you how much is the charge present inside the third ball, see, when it comes to the net charge, sir, net charge is plus 9 Coulomb. So we say 4 plus 1 is 5, and we say, sir, 4 plus 1 is 5. So how much it has to be over here? You say, sir, or let's suppose I'm saying we'll place 2 Coulomb charge in this one. 2 Coulomb charge in this one. Now 2 plus 3 is 4. 2 plus 1 is 3. And in this case, it will be 6 Coulomb charge in this one. Sir, initially, inside this box, we say 9 Coulomb was the total charge. Finally, what about the net charge? You say finally it has to be 9 Coulomb also. Sir, inside this box, initially, inside this ball, 2 Coulomb charge was there. Now finally 1 Coulomb charge is over here. Inside this ball it was plus 3. Over here it is plus 2. It was plus 4. It is plus 6. So the balls can share the charge between each other. But when it comes to the net charge of the system, net charge remains conserved. Net charge of the system remains conserved. That's what we say. The charge is conserved. The charge is conserved. I hope each and everything is clear. Okay. Conservation of charge. The net charge of the system remains conserved. Okay. Now let's move on to the next one. I hope this is clear. Let me know in the live chat. Is it clear to each and everyone? Let's move on to the next one. Now, the next over here, yes, law of conservation of charge, net charge is conserved. Is it clear? Give me a thumbs up, everyone. Guys. Yes, cool. Great. Okay. The next property is basically charge is quantized. Okay, a lot of people basically get confused in this property also. Let me give you the proper feel of this quantity, this property. Let's suppose you have got a shop over here. This is a shop 1 or shop A. Okay, and this shop, let's suppose, sells the balls or the cricket balls. Okay, we say it sells the cricket balls. Cool. Now I went to the shopkeeper. I asked him one thing: give me the smallest ball that exists in your shop. He is saying that this is the smallest ball that I have. Take this ball. I'm saying no, I want the smaller ball than this one. He said, okay, take this ball. This is smaller. I asked him, I don't want this one. I want the smallest ball. He said, take this one. I said, no, smaller than this one. He said, next one is this one. I said, no, smaller than this one. He said, then take this one. And once I asked him afterwards, give me the smaller ball than this one, he said, no, this is the smallest ball that exists in my shop, that is available in my shop. The company which manufactures these balls, this is the smallest ball they make. Okay, so we say this is smallest ball existed. Okay, this is the smallest ball possible. Cool. Now I went to the shop B. Listen to me very carefully. I'll give you the exact feel of what is charge is quantized. Now I went to the shop B, shop 2, and this shop 2 basically sells the charge. Okay, it sells the charge. This one sells the balls, it sells the charge. Okay, let's assume it is selling the charge. We are assuming it. So I asked him, give me the smallest charge you have. He said, this is the smallest charge I have over here. I said, no, I want the smaller than this one. He said, then take this one. This is the smaller one. I said, no, give me the smaller than this one. He said, take this one. I said, no, give me the smaller than this one. He said, this is the smallest charge. This is the smallest charge that exists and that is possible. We say smallest charge possible. Now, my dear friends, the question is, what is the value of this smallest charge? You say, sir, the value of this smallest charge is nothing but that is charge on 1 electron. And that is how much? 1.6 into 10 raised power minus 19 Coulomb. Sir, this is the smallest charge which exists. Yes. Sir, can you give me half of this charge, half of this electron? I say no. Why? Because this is the smallest charge that exists in the world. And this is the smallest ball that exists. I hope you got it. And how much is the smallest charge that exists? That is charge on 1 electron. That is 1.6 into 10 raised power minus 19 Coulomb. Okay, sir, I got it. Now, my question to you is, okay, before this, do you guys know, see, we have electrons. If you see an atom, okay, you might have heard a basic theory about the atom. If you see, sir, inside the atom we have electrons. Atom is made up of electrons. It is made up of protons. Okay, so inside if I, for example, make the atom over here, this is a nucleus. Around the nucleus we say electrons are revolving. Inside the nucleus we have protons plus neutrons. And when it comes to the electrons, electrons has positive charge. Electrons have negative charge. Electrons have negative charge. When it comes to the protons, it has positive charge. And when it comes to the neutrons are basically neutral. So now, coming back to the topic, smallest charge possible is nothing but charge on an electron. Now, if I ask you the simple question, let me know in the live chat. Yes, let me know in the live chat. Sir, if I ask you, that is nothing but, see, can you give me 1 electron? Is it possible for me to get 1 electron? You say yes, because 1 electron exists in the world. And if I ask you, could you give me E by 2, half of this electron? You say, sir, no, it is not possible. Why? Because this is the smallest charge which exists. Okay? So because this is the smallest charge. And if I ask you, can you please give me, is it possible for you to get 2 electrons? Yes, sir. Yes. You'll get 1 plus 1 is equal to 2. Sir, is it possible for you to get 3.5 electrons? We say no. 4.75 electrons? We say no. 4 electrons you can get, but you cannot get 0.75 electrons. Similarly, you can get 3 electrons, 4 electrons, 5 electrons, and if you keep on doing this, you can say, sir, I can get n electrons. Okay. Now, charge on an electron is how much? 1.6 into 10 raised power minus 19. So I can simply say, sir, the charge possible which exists in the world is nothing but Q is equal to n times of E. And we say plus minus n times of E. These are the charges possible. Charges possible. Charges not possible. Sir, why? Because this is the smallest one. You cannot get half of the electron. I hope you got it. So now it is like, for example, you are going to a shopkeeper and you ask him, can you please give me 1 pen? He'll give you 1 pen. He will give you 2 pens. Is it possible for you to buy 3 pens? Yes. Is it possible for you to buy half of the pen? No. Okay. Because 1 pen can exist, 2 pens can exist. So that is, we say charge is quantized or charge is available in fixed amounts. Charge is available in fixed amounts. Sir, what does that mean? That means charge is available in 1 electron, 2 electrons, 3 electrons, 4 electrons, but it is not available in E by 2, half of the electron, 3.5 electrons, 4.75 electrons. I hope you got the feel of this one. Let me know in the chat. Is it clear to everyone? 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 Okay. So charge is available in fixed amounts. Like if we say pens are available in fixed amounts, similarly quantized charge is available in fixed amounts. Now let's basically move on to the next. That's charging a body. How do you exactly charge a body? The first property that we say is nothing but charging by friction. It is charging by friction. It is charging by friction. Cool. Great. Is it clear? Let's basically move on. Let's move on to this one. Charging a body. Okay. So the first thing, how do we exactly charge a body? See, the first example that I gave you, I rubbed the comb with my hair. Listen to me very carefully. I rubbed the comb with my hair. So this comb basically got charged. Charge was occupied on this comb. So that is how we exactly charge the body. Like over here, listen to me very carefully. The first property, the first method by which a body can be charged is nothing but charging by friction. Let's suppose I have a rod over here. Okay. And this rod is neutral. And this is glass rod. Okay. And this is neutral. Sir, what does neutral mean? Neutral means the number of positive charge or the amount of positive charge is equal to the amount of negative charge. Amount of positive charge is equal to the amount of negative charge. Now, in this particular case, what I'm doing is that I'll take a silk cloth. Over here. This is a silk cloth. I'll take a silk cloth. Now, what I'll do is that I'll rub this rod with the silk cloth. It is like I'm rubbing the rod with the silk cloth. Okay. I'm rubbing the rod with the silk cloth. And this silk cloth is also neutral. The amount of positive charge is equal to the amount of negative charge. Yes, sir. Absolutely cool. So once we rub this glass rod with the silk cloth, we observe that negative charge got transferred from this rod to the silk cloth. And afterwards, can I say that, sir, if negative charge from the rod gets transferred to the silk cloth, we say what remains over here, it is positive charge. Okay, it is positive charge. And if I just make the silk cloth over here, sir, negative charge is transferred on the silk cloth. We say now more negative charge will be on the silk cloth as compared to the positive charge. As compared to the positive charge. Yes. So can I say over here? Can I say over here? On this rod, now it becomes, sir, positively charged. Yes. Why? Because now more positive charge is present on the rod. Negative charge has left. And this becomes negatively charged. Why? Because more negative charge is now present on the silk cloth. Yes. So we say we charge these two things by rubbing. This is what we call the charging by friction. It is to charge a body. It is to charge a body by rubbing. It is to charge a body by rubbing. It is to charge a body by rubbing. Is it clear? Is it clear, guys? I just need to see the fire symbols or I'll stop the session. Everyone in the live chat. Is it getting clear, everything? See, I'm rubbing this rod with the silk cloth. So I observed that negative charge from the rod gets occupied on this silk cloth. This gets transferred from the rod. So what remains on the rod? Positive charge. And what is being occupied on the silk cloth? We say more negative charge. This becomes positively charged. This becomes negatively charged. Yes, cool. Okay, great. Your fire symbols, your hearts give me more energy. Okay, that's why keep on sending these fire symbols and hearts. Then only we'll scale up this session. I'll be showing you each and every single problem and you'll be able to solve it. I'm 100% sure. Okay. Now, let's move on to the next one, that is charging by conduction. Sir, what does this mean? Let's suppose we have a metallic sapphire over here. Okay. And this metallic sapphire is positively charged. This metallic sapphire is positively charged. We say it is nothing but positively charged. Means it has got more positive charge on it as compared to the negative charge. Cool. Now, what I'm doing is that I'll take an uncharged sapphire near to it and I'll touch it with the uncharged sapphire. Or this is a neutral sapphire, we say uncharged sapphire. Okay. So while I'm touching this positively charged sapphire with this uncharged sapphire or the neutral sapphire, I observed that, sir, this positive charge, some of the positive charge gets transferred on this metallic sapphire. We say on this sapphire, previously on the sapphire A, on the sapphire B, previously on the sapphire A, positive charge was there. Let's suppose 10 Coulomb of positive charge. We say some positive charge still remains over here. Let's suppose 5 Coulomb plus 5. And some positive charge gets transferred to the sapphire B, that is uncharged sapphire. This is a metallic sapphire. So we say on this sapphire also the positive charge gets occupied. Positive charge gets occupied. So can I say over here, it was initially positively charged, now also it is positively charged. And this uncharged sapphire, this neutral sapphire, can I say this also becomes positively charged? 110% yes. This also becomes the positively charged. Why? Because the charge has transferred from this sapphire to this sapphire. Now, tell me guys one thing. Did I rub the two sapphires? No, sir. Did I touch the two sapphires? Yes, sir. So can I say charging by conduction means it is to charge a body. It is to charge a body by. It is to charge a body by just touching. Okay, I don't have to rub the body over here. Sir, what was charging by friction? Charging by friction was rub the two bodies and then they get charged. But in this case, we just have to touch the two bodies. Sir, what is the difference? Over here, we take the metallic sapphires. Over here, this is a glass rod, this is silk cloth. Materials are different. Now, you guys tell me one thing. Next is charging by induction. You guys tell me one thing. See. Over here, when it comes to the charging by induction, sir, first was you just have to rub the two bodies and get them charged. Second was you just have to only touch them. And sir, what about the third? Just bring them close to each other and they'll get charged. I hope each and everything is clear. I hope each and everything is clear. Let me know in the live chat itself. Is everything clear over here? See, I'll take the example over here. Let's suppose we have a rod which is negatively charged. Yes, sir. And I'll take a sapphire in this case. This sapphire is neutral. Sir, what does neutral sapphire mean? Neutral sapphire means the amount of positive charge is equal to the amount of negative charge. The amount of positive charge is equal to the amount of negative charge. Okay. Now, you guys tell me one thing. I am bringing these two close. Get them close. Bring them close. Okay. Let me use the correct English over here. Bring them close. Okay. Do not touch them. Do not rub them. But bring them close. So when you bring these two bodies close to each other and you observe that, sir, you observe that after bringing these two charges close to each other, sir, we know negative charge repels the negative charge and negative charge attracts the positive charge. See, the negative charge of the rod will repel the negative charge of the sapphire and the negative charge of the rod will attract the positive charge of the sapphire. So we say after some time this sapphire looks like over here, sir, this will be the positive charge from this side and this will be the negative charge from this side. Yes or no? We have this body over here. This is the positive charge from this side. This is negative charge from this side. Why? Because the negative charge of the rod will repel the negative charge of the sapphire. And the negative charge of the rod will attract the positive charge of the sapphire, because positive repel, negative repel, negative positive attract. And afterwards, what we'll do is that we'll bring another uncharged body. This is the body, another uncharged body. Uncharged body. Okay. Now, once we bring this another uncharged body and we touch it with this body, and you get to see that, sir, this negative charge gets shifted onto this uncharged body. Okay, this gets shifted over here. This is what we have done experimentally. You just have to remember it. Okay, so we say, sir, once we separate these two bodies afterwards, see if the negative charge will shift from this sapphire to this uncharged sapphire. So on this sapphire, we say what remains, that is positive charge. On this sapphire, what will be occupied on the sapphire? You say, sir, negative charge. Why? Because negative charge of this sapphire will get shifted onto this. Let me repeat it once again. In case of charging by induction, how do we explain it? We take a negatively charged rod and we take a neutral sapphire. The amount of negative charge is equal to the amount of positive charge in this sapphire. Once we bring them close, the negative charge of the rod will repel the negative charge of the sapphire and attract the positive charge of the sapphire. So the negative charge of the sapphire will get shifted on this side and positive charge of the sapphire will get shifted from this side. Now we bring another uncharged body, touch it with this body, and we observe that this negative charge gets shifted onto this new sapphire. This also. And afterwards, once we separate them, what remains over here? Positive charge. And what gets occupied on this one? Negative charge. Guys, in the live chat, I just need to know, is it clear? This is how we charge a body by induction. In the live chat with the fire symbols, everyone. And we say it is to charge a body by bringing them close to each other. Now see, don't get confused over here, sir. You are touching the body over here. This is just the method, okay? The main principle is basically you are bringing them close. Don't go in much detail. As simple as that. The amount of information I'm giving you, just take it and keep on solving the questions. That's it. Done. Okay. Great. Super. Okay, South Indian people say, or the people from Tamil Nadu say, super. Okay. Now, Let me just tell you over here, guys, the Unacademy NEET English team is coming to the Chennai very soon, okay? Very soon, what I mean is that on 23rd of December, I want you guys to basically come over here and meet us. We'll speak to you. Whatever the confusions you have regarding the NEET, you can ask us. Whatever the doubts you have regarding these competitive exams, you can ask us. And there are also some NEET toppers who are going to come over there, and you can ask them, how was your journey? How did you prepare this subject, that subject, and accordingly. So register it. The Google form is in the description below. Join it and fill that up as soon as possible. Okay. So it will be on 23rd of December. So do it as soon as possible. Okay. Great. Let's move on to the Coulomb's law. Now comes, see, this is from here, the problems will start. Okay. From here, the problems will start. From here, the problems will start. Now see, the first thing that I want to tell you over here is, what is this Coulomb's law all about? You guys tell me one thing. Let's suppose we have a magnet over here. We have another magnet over here. You say, sir, if we have the two magnets, if we place it onto the table, they will attract each other. Okay, we have seen this. Okay, they apply the force on each other. Same is the case over here. Now, instead of these two magnets, we'll place what? We'll place a charge over here. Let's suppose this is plus Q1 and we have another charge that is plus Q2. These are the two charges we have over here. This is plus Q1 and this is plus Q2. And they are separated by some distance. I'm placing one charge over here, another charge over here, separated by some distance. Sir, like the magnets, will these two charges also apply the force on each other? We say yes. This positive charge will repel this positive charge with a force F. This positive charge will repel this positive charge with a force F. They will apply the force on each other. So both positive repels positive, negative attracts. As simple as that. Now the question is, sir, we know this. These two charges will repel each other. They will apply the force on each other. Question is how much force they will apply on each other. We say, sir, the more stronger these two charges will be, more will be the force. If you have a bigger charge over here, they will apply more force on each other. Yes, sir. Yes, sir. So we say, listen to me very carefully. This force between these two charges is directly proportional to the product of the two charges, Q1, Q2. More the charges are there, strong magnitude, more is the force. And we say F is inversely proportional to R square. If you place these two charges very far from each other, sir, they will apply less force. Bring these two charges close to each other. It is like magnet. You place the two magnets close to each other, they'll apply more force. You place the two magnets very far from each other, they'll apply less force. So F is inversely proportional to R square. Now combine these two, we can say F is proportional to, sir, Q1, Q2 divided by R square. Yes, sir. Now replace this proportionality with a constant. We say F is equal to K. We have Q1, Q2 divided by R square. Sir, this is the amount of force they apply on each other. And this was given by Coulomb, and hence it became the Coulomb's law. If we have two charges, they apply the force on each other. How much force they apply on each other is nothing but F is equal to K. Q1, the first charge, Q2, the second charge, divided by R square, the distance between the two charges. Yes, sir. Now, sir, what is this K? K is what we call the constant. Okay, K is the constant of proportionality. Listen to me. Sir, this K is nothing but this K. The value of this K is equal to 1 by 4 pi epsilon naught. Sir, this is a constant. What is the value of this constant? 1 by 4 pi epsilon naught. And what is this epsilon naught? This is permittivity of free space. See, after some time, I'll tell you what is permittivity of free space. As of now, you just remember it. Just see, this permittivity basically tells us how much the two forces will apply the force on each other in air. I'll tell you after some time. Now, Could you please tell me what is the value of permittivity over here? Is everything clear over here till over here? Let me know in the live chat, everyone. Okay. So this is the force between the two charges, and this is the permittivity of free space, and the value of permittivity we say 8.85 into 10 raised power minus 12. We say Coulomb square upon Newton meter square over here. Newton meter square over here. Is it clear over here? Is it clear? Yes, great. 10 raised power minus 12. 8.84 in 10 raised power minus 12 Coulomb square upon Newton meter square. That's great. Now, do one thing. See, just a second. Do one thing. Sir, put this permittivity, value of permittivity over here. 8.85 into 10 raised power minus 12. Put it over here. You say 1 by 4 pi. Value of pi is 3.14 into 8.85 into 10 raised power minus 12. And then once you solve it, just a second. Once you solve it, you say, sir, K is equal to 1 by 4 pi epsilon naught. Epsilon naught is nothing but 8.85 into 10 raised power minus 12. If you put the value over here, this K would come out to be 9 into 10 raised power 9. This would come out to be 9 into 10 raised power 9. And this is Newton meter square upon Coulomb square. This is the value of K. I hope you got it. Sir. Now, can I say, I can write this force as F is equal to 1 upon 4 pi epsilon naught. Instead of K, I'm writing this. Then you have Q1, Q2 divided by R square. This is the complete detail about the Coulomb's law. Okay? I hope you got it. So value of K is 9 in 10 raised power 9. Value of permittivity is nothing but 8.85 in 10 raised power minus 12. Let's move on to the next one. Now guys, see. Listen to me very carefully. Let's suppose I have over here, this is a force. This is from the vectors. Okay? Listen to me very carefully. I have a force over here, or let me just show you over here. Let's suppose I have a block. And on this block, I am applying some sort of force in this direction. And I am applying some sort of force in this direction. The two forces are making the angle of 90 degrees with each other. Listen to me very carefully. Sir, if the two forces are making 90 degrees with each other, could you please tell me what is the net force over here? We say, sir, net force in this case will be under root of 2f. Remember it directly, we don't have to solve it. Sir, now, if let's suppose, for example, we have the same block. And on the block, one force is acting somewhere in this direction, another force is acting something like this, okay? Same force. If this is F, this is F. Sir, now the angle between these two is 60 degrees. In this case, what is the net force of these two? You say, sir, the net force of these two will be nothing but under root of 3f. Remember it directly. Now, if I have, for example, the same block, one force on the block is acting something like this. Another force is acting something like this. This is F. This is F. Angle between these two is 120 degrees. When the angle between the two forces becomes 120, we say net force becomes also F. Listen, when angle is 90 degrees, okay, then in that case, angle net force is root 2F. When angle is 60, root 3F. When angle is 120, the net force is F only. The net force is F only. Is it clear? Is it clear? Great. Yes. Just a second. Okay. Now see, the first question we have on the screen, I want you guys to let me know the answer of this particular question. Okay. Tell me the answer of this particular question. Find the net force on the center charge. We have a charge placed at the center. You are supposed to tell me what is the net force on this charge which is present at the center. Everybody over here. Let me know. This is plus q, this is plus q, this is minus q, this is minus q, and on the center we have plus q. Everyone, I just need to know the answer in the live chat. Before I solve the question, it is your responsibility and it is your duty to solve it. Okay? That's the rule. That's the rule, and you guys are supposed to follow it. As simple as that. Great, 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 great. Net force will not be 0. Why are you saying net force is 0? This is minus q minus q. It's not plus q over here. Why is everyone saying 0? This is plus q, this is plus q. These two are minus q minus q. If I place the plus q over, then it becomes the easy question. Why is everyone saying 0? Is there anyone who can give me the correct answer? Not 0. No, 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 no. Hey guys, see, I'll show you. This is the charge q. This is the charge q which is present at the center. Okay. We have to find the net force on the center charge. The charge which is present at the center, we have to find the net force on it. The first thing, listen to me very carefully. Sir, this minus q will attract this plus q towards itself with a force F. Let's call it force F, because negative attracts positive. And over here, sir, this plus q will repel this plus q with a force, let's suppose F also. They will apply the same force. So this repels, this attracts. Now over here, this minus q will attract this with a force F. This plus q will repel this plus q with a force, let's suppose this is also F. So now, this is attracting, this is repelling. This is attracting, this is repelling. If I make this over here, it is something like this. This is F and this is also F. This is, sir, F. This is also F. So can I say, sir, the two forces are in the same direction? Whenever you see the two forces are in the same direction, you say, sir, their net force becomes 2F. F plus F is 2F. And this net force is also, that is 2F. I hope you got it, each and every one. See, now, sir, how much will be the angle over here? This angle is nothing but, we say, 90 degrees. In the square, this angle is 90 degrees. So this angle is 90 degrees over here. If this is 2F, this is 2F. Angle between these two is 90 degrees. Guys, I just told you, if I have a force F, the resultant will be, if angle is 90, the resultant will be root 2F. Now, over here, I have 2F. So we say, in this case, net force would be under root of, see, it is under root of F. But we have over here 2F, so it will be under root of 2F. See, in this case, it was F. Over here, it is 2F. So that's why it will be, that is nothing but 2 root 2. How many of you got it? Root 2 of 2F. Yes, that's great. A lot of people are sending the correct answer. That's great. Is it clear? Is it clear, guys? Is it clear? That's cool. Great. So basically, this is under root of 2F. Now, if somebody asks you, sir, put the value of F also over here. How to put the value of F? See, value of F means force between any two charges. Now see, if I ask you to find the force over here between any two charges, sir, we know force is K, Q1, Q2 divided by R square. Q1 is how much? We say, sir, Q. Q2 is how much? We say, sir, Q. Q divided by distance between them. Guys, if this is A, if the side of square is A, this distance from half of the diagonal, this is nothing but A by root 2. So this is nothing but A by under root of 2 whole square. K, Q1, Q2 by R square. And if you solve it, this is nothing but, we say, sir, K, Q square. Q into Q becomes Q square. And this is nothing but A square over here divided by under root 2 whole square. Root and square will get cancelled. So this will be nothing but 2. You can write it, if you take the 2 in the numerator, 2 times of k q square divided by a square. Okay, this is the force. Now F net is equal to, let me just write over here, F net is equal to under root of, F net is equal to 2 root 2 F, and it will be 2 root 2. Instead of F, I'll put up this value, that is 2kq square by a square. That is 2kq square by a square. 2 into 2 becomes 4 root 2 kq square by a square. I hope you got it. Done. Let me know. Is it clear? Guys? Yes, great. Okay. Let's move on to the next one. Got it. Cool. Let's move on to the next one. We have this question. 3-point charges plus q, and minus q are placed at the corners of an equilateral triangle. It is saying that we have 3 charges. We have 3 charges over here. The first one is plus q. This is plus q. And then we have minus q. The 3 charges are placed, plus q, and minus q are at the corners of an equilateral triangle. Off side A, this side is A. Another charge plus q is kept at the centroid. Force exerted on plus q is, we are supposed to find the force on this charge which is exactly present at the center. You guys tell me one thing. See, sir, it is very easy. We can swallow it. See, sir, when it comes to this plus q, this is positive charge, this is positive charge. Plus charge, positive repel, so it will repel it with the force F. Now, this plus q will also repel this plus q with the force F. This will repel this with a force F. This will also repel this with a force F. Now, this charge is negative, this is positive. Negative charge attracts the positive charge, we say, with a force F. All the 3 forces will be equal because this distance, and this distance is equal. Now, you guys tell me one thing. Sir, first force is something like this. Second force is something like this. And third force is something like this. Now, how much is this angle in this case, sir? This angle is 120 degrees. In this case, this angle is 120 degrees. Remember it, okay? The whole is basically 360 if you keep on revolving in the cycle. So this angle is 120 degrees. And you guys tell me one thing. When the angle between two forces is 120 degrees, what is the resultant? It is F only. Now, over here, in this particular case, sir, this is F, this is F. So the resultant of this force and this force, so it is F only. See, I'll show you with this color. Sir, the resultant of this force and this force, it is F only because angle is 90, angle is 120. So it becomes something like this. F, resultant of this one, and this is F over here. So it is nothing but 2 times of F. So this is what we call the net force over here. And we are supposed to find it something like this. Now find the value of F. See, the value of F in this case is, just a second. The value of F in this case is, see, F is basically the force between any 2 charges. If I say, sir, we are supposed to find the force between these 2 charges. If this is the distance A, this distance will be A by root 3. Just a second. This distance will be A divided by root 3. Okay. Now find the force. F is equal to, sir, K, Q1. Q1 is, take any of the charge, this one, and the center charge, that is Q, divided by R square. R is how much? that is A divided by root 3 whole square. And if you solve it, you say, sir, it will be K Q, this Q upon. This will be A square divided by 3. And if you take in the numerator, it becomes 3KQQ divided by A square. Okay. Now, over here, sir, we got the net force. We got the net force at as how much? We got the net force as 2F. We got the net force as 2F. Okay. So we say, sir, 2. And how much is the F? F is nothing but 3KQQ by A square. We say, sir, 3KQ, this Q divided by A square. So this will be 3 to 6 KQQ by A square. Okay. Now, which option? This one. This one. Instead of K, he has put 1 by 4 pi epsilon naught. We can also put 1 by 4 pi epsilon. I hope this is clear. I hope this is clear. I hope this is clear. Okay. Let me know in the live chat if it is clear. Okay. There is some previous student of mine. Okay. That's great. She is in the IIT right now. I'm in IIT. Okay. I'm in NIT Durgapur. That's great. Clear. Just a second. There is some electricity issue. I'll just fix it and I'll come back. Just give me 1 second. Give me 1 second. Okay. So great. Is it clear to each and everyone? Is it clear to each and everyone? Yes. Let's move on to the next question. Okay. I have put up so many questions. Okay. So we have the next question over here. Find the net force on 2C. We have got a charge over here that is 4C. This is C is what? C is Coulomb. 4 Coulomb charge minus 2 Coulomb charge minus 2 Coulomb charge plus 2 Coulomb charge. And this distance is 2 meters. And the diagonal distance is how much? That is root 2. And we have to find the net force on this charge. Net force on this charge because of the rest of the charges, because of the other charges. Now, listen to me very carefully in this particular case. See, we have to find the net force on 2C. First and the foremost thing, you guys tell me one thing. Sir, this is minus 2 Coulomb, this is plus 2 Coulomb. Negative charge. Because of this charge on this charge, the force will be attractive. Why? Because this is negative, this is positive. Negative charge will attract the positive charge, and this negative charge will also attract this positive charge. Now, see. Guys, we call this force as F1. We call this force as F2. And this 4 Coulomb charge, this is positive charge. Positive charge will repel this positive charge because positive repels, and we call this as F3. F1, F2, F3. Let's find the values of F1, F2 and F3. First, F1 is the force between this minus 2 and this plus 2. Sir, let's find F1. F1 is nothing but, sir, K, Q1, Q2 divided by R square. Now over here, sir, K, what is the value of Q1? Sir, value of Q1 is, let's suppose, 2. See, why am I not taking the minus 2? Because when we find the magnitude of force, we just take minus 2 also as plus 2. Just take it. We are finding the magnitude of force. Just take minus as plus also. So plus 2, this is 2 Coulomb. And then how much is this charge? This is also 2 Coulomb divided by, what is the distance between them? Sir, distance between them is 2 meters, that is 2 square. Now 2 into 2 is 4, and they will get cancelled out over here. What remains is K. So the value of F1 is K. Let's find the value of F2. Let's find the value of F2. You say, sir, value of F2 is nothing but same K Q1 Q2 by R square. Sir, K, what is the value of Q1? Sir, force between this charge and this charge. This is 2. This is 2 Coulomb. And how much is this force? This is also 2 Coulomb divided by, what is the distance between these two? This is a square. So this is also 2 square R square. This will get cancelled. So this is also K. So F1 is K, F2 is K. Let's find the value of F3. F3. Sir, F3 is the force between this 4 Coulomb and this 2 Coulomb. So you say, sir, it is nothing but K. And Q1 is how much? Let's take it as 4. Q2 is how much? Sir, let's take it as 2. 4. This is 2 divided by, sir, R square. Distance between these two. We say, sir, 2 root 2 whole square. That is R square. Now, see, 4 into 2 is 8. So this will be K, and this is 8. 4 into 2 is 8 upon. Now this is also 8. 2. This is 2 multiplied by under root 2 whole square. Sorry, this is 4. See, this is 2 square is 4 into under root 2. Under root 2 whole square. This square and root will get cancelled. This is 4 into 2. 4 into 2 is 8. 8 and will get cancelled. This is K. So we have the force F1 as K, F2 as K, F3 as K. Let's draw these forces over here. The first force, we have F1 something like this. This is K. This is F1, it is K. I'm making it exactly like this over here. And this is F2 in the downward direction. So we say this is also K because F2 is also K. And then you have this F3. This is also, sir, K. Now this is K, this is K. Sir, angle between these two is 90 degrees. Sir, you have told us whenever the force between the two vectors is 90 degrees, the resultant of this one and this one is nothing but under root 2K. Yes, sir. Yes, sir. Now, we have this vector, we have this vector. Listen to me very carefully. We say, sir, in this direction you have root 2K. In this direction you have, sir, K. Now, what is the net of this one? See, net will be this vector minus this vector. Whenever you have two vectors in the same direction, add them. If they are opposite, you subtract them. So we say in this case, F net will be under root 2K minus K, and take the K common. You say, sir, this will be root 2 minus 1. The root 2 minus 1. K root 2 minus 1. Is it clear to everyone? Yes, great, great, great. Is it clear to everyone? Let me know in the live chat. All the people out there. Let's move on to the next question. Let's move on to the next question. We have this over here. Sir, this is minus Q, minus Q, minus Q. This is plus Q, plus Q, plus Q. And I asked you the question, find the net force, F net, on the center charge. Center charge. The charge which is placed at the center, you are supposed to tell me the net force on that center charge only. Can you guys tell me, can you guys let me know about this net force? Okay. See, sir, the net force on this center charge because of the rest of the charges over here, listen to me very carefully. We say, sir, this is minus Q and this is plus Q. This minus Q will attract this plus Q towards itself. Let's call with the force F. Sir, this plus Q will repel this plus Q because both are positive with a force F. Sir, this minus Q will attract this plus Q with a force F. Sir, this plus Q will repel this plus Q with a force F. Can I say something like that? Positive, positive will repel? Yes, sir. Now, this minus Q will attract this plus Q with a force F. This plus Q will repel this plus Q with a force F. Yes, 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 yes. I hope you got it. Now, can we draw these figures over here? Sir, this is nothing but F plus F is nothing but we say 2F. And then we draw this force. It is something like this. F plus F is nothing but 2F. And then we draw this force. This is also, that is F plus F is 2F, because they are in the same direction. Okay. Now over here, sir, angle between these two is 120 degrees. Angle between these two is 120 degrees. And in this particular case, listen to me very carefully. We say, sir, whenever the angle between this and this is 120, so resultant of this one and this one is resultant just a second. Okay, resultant of this one and this one, resultant of this one and this one is how much? We say, sir, it will be nothing but it will be 2F only. So now we have first 2F in this direction. This was the already, just a second. We have resultant of this one and this one will be 2F. Okay. And this 2F is also in the forward direction. So I'll make it over here. So 2F plus 2F is how much? That is 4F. 4F is correct. A lot of people are giving me the correct answer in the live chat. That's great. 4F is the correct answer. Okay. Can I just put the value of F over here? Yes, sir. 4. And what is F? F is the force between any two charges. Take any two charges over here. Sir, you say, sir, F is equal to K, Q1, Q2 by R square. Q1 is how much? You say, sir, Q. Q2 is how much? You say, sir, this Q divided by R square. What is the distance between any two forces, any two charges? That is A square. So we can put it over here, 4K Q, this Q divided by A square. I hope this is clear to each and everyone. This is clear to each and everyone. Let's move on to the next question, boys and girls. Okay. If you get some sort of confusion over here, listen to me very carefully. I have a limited time and I have to finish this entire chapter. Okay. In the regular classes, we teach this electrostatics. Even if I say in the offline, when teachers teach this chapter, they take, we say 1.5 months or 1 month. Okay. So I have to finish this entire chapter in one go. So we have a limited time. If you get any sort of confusion at any particular point of time, so what you are supposed to do is that you move forward. Okay. Leave that confusion. We'll see that later. Okay. And just once we are done with the stream afterwards, you can replay it and you can watch it and clear that confusion. But as of now, don't keep on basically fixing that confusion over here because we have a limited time. We have to finish this entire thing over here. Okay, great. Let's move on to the next one. Okay, we have the relative permittivity. Let's move on to this topic. See, I'll tell you, relative permittivity is the topic in which a lot of people have confusion. I'll tell you in few seconds. Few seconds you'll get to understand what is the feel of relative permittivity. See, sir, let's suppose we have over here, this is a container box, whatever you say. And inside this box, what is present is air, okay? Or this room, inside this room is air only. Now, inside this box, I'm placing two charges. First one is Q1, another is Q2. Distance between these two charges is R. We have Q1, we have Q2, and distance between the two charges is R. Now, my question to you is, sir, will the two forces apply force on each other? You say, sir, yes. Because whenever there are two charges, they apply force on each other. So we say force between the two charges in air is, let's call this as F naught, force in air. Cool? Yes, sir. Now what I'm doing is that over here, I'll take another container or I'll take another room, whatever you say, box. And inside this box, what is present is water. Over here it was air, over here it was water. And I'll place inside this box the same two charges. This Q1 I'm placing over here. This same Q2 I'm placing over here. Okay. And distance between these two is same, that is R. I'll cap the same distance. Now my question to you is force between the two charges in water / medium. We call it a medium, another medium. The medium is air, the medium is water. Sir, how much is the force in a medium? How much is a force in a medium or how much is a force in water? Sir, is there any, in Hindi we call it jugaad. Is there any jugaad by which we can find the force in this medium? Same charges, same distance. I say yes, there is a jugaad. There is a method by which we can do it. See, I say, sir, you just write one formula. Force in a medium is equal to, sir, force in air or force in free space. Air or free space, one and the same thing. Then divide it with ER. Sir, this is force in a medium. Force in a medium, it will be equal to force in air slash free space divided by, what is this ER? It is relative permittivity. Yes, sir. Now. If I ask you, if I tell you over here, sir, this relative permittivity, we represent it with ER. See, just wait for a few seconds. If I tell you, sir, different medium has got different relative permittivity. Different medium has got different value of relative permittivity. When it comes to the water, the relative permittivity of water is 81. Let's suppose 81. So over here, can you tell me now force in water? You say, sir, now I can find easily force in water. You say, sir, force in water, that is force in medium, is equal to force in free space. How much was the force in free space that I gave you? That is F naught over here. Sir, that is force in free space F naught divided by relative permittivity. What is relative permittivity? That is 81. Sir, this gives me an idea. Relative permittivity gives me an idea. If you want to find the force in water, means you divide the relative permittivity to the force in air. Means force in water has been decreased by 81 times as compared to the force in free space. Force has decreased by 81 times. Yes, sir, force has decreased by 81 times. Sir, can I not say the definition of relative permittivity is, it gives us an idea, or it tells us force in a medium or force in a medium as compared to force in free space. Yes. So I can say over here, relative permittivity tells us the force in a medium force in a medium as compared to force in free space. Yes, sir. Relative permittivity tells us force in a medium as compared to the force in free space. Let's suppose if I have another medium over here, and the relative permittivity of this medium is, let's suppose 7 of this 7. And I am asking you, I am placing the two charges in this medium. Can you tell me what is the value of force between the two charges in this medium? You say, sir, yes. We say force in this medium will be force in free space. Force in free space we can find easily, divided by relative permittivity, that is 7. Means force in this medium has been decreased by 7 times as compared to the force in free space. I hope it is clear to each and everyone. I hope it is clear. Let me know in the live chat, guys, if it is clear to each and everyone. Okay. Great. Okay, one more formula I'll tell you. So relative permittivity is the concept which helps us to find the force in a medium. Now, one more concept I want to tell you over here. One more concept, that is nothing but, we say this relative permittivity, ER, it is equal to permittivity of medium divided by permittivity of free space. This is the permittivity of free space. And this is the permittivity of medium. See, different mediums has got different permittivity. Okay. So that's why we say this is the permittivity of medium. If I say you have to find the permittivity of a medium, you will say, sir, EM is equal to, you will say, sir, it will be ER, E naught multiplied by this ER. Means it also helps you to find the permittivity of a medium. Yes, sir. See. I'll say it helps us to find the permittivity of a medium also. It helps us to find the permittivity of a medium also. Okay. Now, how? Sir, I have to find the permittivity of water. You say, sir, permittivity of water is equal to, permittivity of medium means permittivity of water is equal to permittivity of free space. That is 8.85 into 10 raised power minus 12 multiplied by relative permittivity of water, that is 81. Done and dusted. Relative permittivity is a concept which helps us to find the permittivity of a medium. Relative permittivity is a concept which helps us to find the force in any medium. Let me know with the fire symbols in the live chat if you understood each and everything, guys. Then I will move forward. This was the question which was asked in NEET 2020. Okay, it is saying that when air is replaced by a dielectric medium of force constant K, the maximum force of attraction between the two charges is, see, decreases by K times. Done. Just one single step. See, it is saying that if we have a medium, okay, if we replace air with a medium, if we have a medium, and inside this medium, this is a medium, okay, and the relative permittivity of this medium, this is a box, inside it there is medium present, some whatever it may be, water, glass, okay, ER is equal to K. Relative permittivity of this medium is K. The two charges are present inside this medium, Q1, Q2. It is asking us what will be the force in this medium. You say, sir, force in a medium is equal to force in free space divided by relative permittivity. How much is that? That is K. So, in this medium, force has been decreased by K times. Force has been decreased by K times. Is it clear, boys and girls? Love from Kashmir. Okay, thank you. Means a lot. Great. Let's move on to the next concept, that is equilibrium position. Let's move on to the next concept. Great. So, everything you understood, huh? That's absolutely great. Okay, cool. I'll give you, sir, your teaching is just like your Wasim, sir. Thank you. Okay. I'll be basically giving you some breaks also in between. Don't worry about that. See, our goal is to get you the selection. We want you guys to be in the medical colleges in 2024. Okay, in the next session. Okay, that's our goal. That's why we have to complete this series. Make sure you tell your friends also. They will be completing the complete physics, complete chemistry on this channel only. Let's move on to this one. Let's get going, guys. Let's move on to this one. Equilibrium position. What does equilibrium position mean? Let me just tell you. Let's suppose we have a charge over here that is plus Q. And we have a charge over here that is n times of Q. Sir, what does n times of Q mean? This can be Q. This can be 4Q. This can be 9Q. In that case, n is 9. In that case, n is 4. Or this can be Q. This can be 15Q. In that case, n is 15. And distance between them is R. Okay. My question to you is, where should we place the third charge so that net force field on it is 0? Net force on it is 0. The question is, where should we place the third charge so that net force on that third charge becomes 0. Sir, we'll do one thing. We'll place it over here. Not here, but over here. Now, in this case, let's see. We have to place it at that position where net force on the charge becomes 0. On this charge, we say this positive charge, this is also positive. This positive charge will repel this positive charge in this direction. This positive charge will repel this positive charge in this direction with some force, let's say F. Okay. Sir, don't you think these two forces will cancel out each other? So we say over here net force is equal to 0. Yes, we got that position where we have to place the third charge so that net force on it is 0. Now, my question is, what is the value? What is the value? How much is that distance? Let's call it X. Where should we place the third charge so that net force on this charge is 0? Sir, I'll place it over here. Over here, net force will not be 0. Over here, net force will not be 0. Okay, we'll not go in much detail. See, this will repel it. This will also repel it. Both the forces will be in this direction. No. Over here, both the forces will be in this direction. No. If you place it over here in the middle and towards plus Q, towards this smaller charge, we say net force will be 0. And we are supposed to find how much is the distance from this Q. Remember it directly, one single go. So we say this X will be equal to, how much is the distance between the two charges? That is R upon, we say under root of N. N is what? How much this is greater than this one, this N, plus we say 1. This is the distance at which you are supposed to place this third charge so that net force on the third charge is 0. Okay, great. Let me show you a question on this one. Let's suppose we have a charge plus Q, okay? And we have another charge that is 9Q plus 9Q, okay? Distance between these two charges is, let's suppose, 10 meters. And I ask you, where should I place Q naught, third charge, so that F net on it is 0. So that net force on it becomes 0. Let me just tell you, sir, we know we'll place it somewhere around over here, and this distance is nothing but X. And how to find this distance? X is equal to R upon under root of N plus 1. Sir, R is how much? R is the distance between the two charges, that is 10 upon under root of N. Sir, N is what? N is 9 over here in this case. Sir, this is under root of 9 plus 1. So this will be 10 upon under root of 9 is 3 plus 1. 3 plus 1. So this will be 10 by 4. You are supposed to place it at 10 by 4 distance. I hope you got it. Let's move on to the next question on the same concept. Okay. First we'll do this one. Let's suppose we have a charge. Forget about this one. See, in this case, we were having both the charges of same sign. This is positive, this is positive. This is positive, this is positive. Now, this formula is valid when the two charges are positive. When the two charges are of same sign. Positive, positive, negative, negative. Now, I say if Q1 and Q2 are unlike charges, opposite in nature, let's suppose I say I have plus Q over here, and at this R distance I have minus N times of Q. Sir, over here will the formula be different? Slightly different. If I have plus Q, this is N times of Q. Now in this particular case, same question. Where should I place the Q naught so that net force on the Q naught is 0? In this case, we'll place the Q naught over here. At what distance? At X distance. Okay. Not inside. Inside it will not be 0. Over here it will not be 0. But over here. Sir, please go in detail and explain this. No. I want you guys to remember it directly, because if I go in detail, it will create a lot of mess and we'll waste our time. Just remember the formula and application of this one. Sir, at X distance from this side, What is the value of this x distance when the two charges are of opposite sign? We say this x is equal to r upon, we say under root of n, then we have minus 1. When the two charges are opposite in nature, then we have under root of n minus 1. When the two charges are of same sign, then we have under root of n plus 1. Let me move on to the question. We have this question. See, find the distance from 9q where q0 is placed to experience the zero force. We are supposed to say, where should we place the third charge q0 so that net force on it is 0? This is minus q. This is plus 9q. This is 18 meters. Tell me the answer. In the live chat, I'm waiting for you. I'm not going to solve this question over here. Let me know the answer in the live chat itself. Everybody over here. Come on. I just need to know the answer in the live chat. Everyone. Guys. 9 is not the answer. You are supposed to tell me from 9q. This is the distance from plus smaller charge. This. So this distance plus this distance, the answer has to be 9 plus 18, that is 27. How many of you got 27? The answer has to be 27. The answer has to be 27. Don't tell me 9. Wasim sir is telling 27. Yeah, guys, come on, everyone. The answer has to be 27. Great. I'll tell you. Sir, where should we place the third charge so that net force on it is 0? First and the foremost thing is we'll place it over here. I told you it will be outside, from the outside towards the smaller charge. This is x. How much is this x? This x is r upon under root of n minus 1. Now in this case, r is how much? R is 18. Distance between the two charges, that is 18 upon under root of n. Now in this case, n is 9. And then minus we have 1. This will be 18 upon under root of n is 3 minus 1. So this will be 18. 3 minus 1 is 2. 18 by 2, that is 9 meters. Now this 9 meters is from minus q charge, from the smaller charge. If this is 9 meters, and from this point to this point, this is how much? This is 18 meters. We have to find distance from 9q. From 9q, it will be 18 plus 9. So it is 18 plus 9, that is 27 meters. I hope you got it. Let's move on to the next one. Okay, next is basically, what should be the value of q0 if all the three charges are in equilibrium? See, I told you, if I have a charge plus q, if I have charge plus n times of q, where should we place the third charge so that net force should be 0? This, we were finding this x. Then I told you, I have this plus q, I have n times of q. I told you, where should we place the third charge so that net force on it 0? So you basically got this distance x. Now we are not finding the distance. We don't have to find the distance. Third case is, we have to find what is the value of this charge q0. The third charge which we are placing here, what is the value of this charge only? Okay, in this case, I'll write here, we don't have to find the equilibrium distance. But we have to find the magnitude of q0 itself. We have to find the magnitude of q0 itself. What is the value of this q0, this third charge? Remember it directly. I say the value of this q0 will be, see, sir, this q0, and there is a condition. If all the three charges are in equilibrium, net force on all the three has to be 0. This q0 will be n times of q. N means how much this is greater than this one. This is n times of q. divided by under root of n plus 1 its whole square, then place the negative sign over here. This will be the value of Q naught in this case. What should be the value of Q naught? Let me solve a question on this. This was asked in NEET 2013. Let me solve a question. In this question, a charge Q is placed at the center of the line joining the charges Q. We have a charge Q. We have a charge Q. Okay? And a charge Q, this Q is placed at the center of the line joining the two charges. This Q is placed between these two charges at the center. The system of the three charges will be in equilibrium. Condition is there. All the three charges are in equilibrium. Net force on this is 0. Net force on this is 0. Net force on this is 0. And we are supposed to find, if Q is equal to, we are supposed to find the value of Q. I told you, if you have to find the value of Q, directly use the formula n times of Q upon under root of n plus 1 whole square. So can I say this will be minus n times of Q upon under root of n plus 1, and it will be whole square. Now, in this case, sir, what is n? This is Q, this is Q. This is how many times greater than this one? In this case, we say n is equal to 1. So we say this is minus, instead of n, I'll write 1, and instead of Q, it is Q only, upon under root of n. N is how much? 1 plus this 1 whole square. Now, this will be minus Q divided by root 1 is 1, 1 plus 1 is 2, 2 square is 4. The answer is Q by 4. Done and dusted. Yes, minus Q by 4, minus Q by 4. Great, great, great. Write with a bright color, sir. Okay. Is it clear, guys? Okay. Let's move on to the next one. Equilibrium of two suspended charges. Let me show you over here. Let me show you over here. Equilibrium of two suspended charges. This is very important, even from JE perspective also. This is very important, even from JE perspective also. Let's suppose, I'll show you. I have a charge, okay? I have a charge. It is like pendulum. I have a metallic sphere or a charge, we say Q, and a rope or a string is attached to this one. This is a ceiling. I am attaching a rope to this one, okay? And I'm attaching a smaller charge over here. It is like pendulum. And we have another charge over here. We have another charge over here, that is Q. Okay? You tell me one thing. Before this, if I say I have one charge over here, this is Q. I have another charge over here, this is Q. Both the charges are positive, or this is the sphere in which positive charge is present. This is the sphere on which positive charge is present. Don't you think these two charges will repel each other? Yes, sir. It is like this initially. When they repel each other, they will basically create some angle, something like this, okay? They will go away from each other. So after some time, it becomes something like this. It becomes something like this, okay? Now, they will not do the perfect circular motion, no, but they will remain at this particular position. This is what we call the equilibrium position. This is what we call the equilibrium position, or equilibrium of two suspended charges. These are the suspended charges, okay? So before they were close to each other. After some time, they will basically move something like this, and they will stick to this and position, and they will remain in equilibrium. This is what we call the equilibrium of two suspended charges. Now, in this case, what the questioner can ask is, listen to me very carefully. Sir, what is the value of this distance? Find x. Find x when the two charges are in equilibrium. when the two charges are in equilibrium. Also find Q, find the value of this Q, find value of this Q. Also find this angle, at what angle the two charges remains in equilibrium, find theta. Also, sir, there will be tension in the string. You might have heard, whenever there is a string, there is tension in the string. Find tension. See, this Q and this X, they both were asked in NEET 2020, in JEE 2021 mains. Okay, I'll be showing you over here. We have the two charges. Okay, the two charges will repel each other. Okay, and they will be separated from each other, and after some time they'll stick something like this and they'll remain in the equilibrium. Okay, at what a distance they remains in equilibrium? They remains there only. Okay, fixed. What is the tension? What is theta? What is the value of Q? In order to solve this type of problem, let me show you the basic approach and then we are good to go. The first thing is draw the diagram. This is the charge, we say Q. This is another charge, we say Q. Listen to me very carefully. Over here, if I say this angle is given as theta, this will be tension. Tension is the force which is in the string. Remember it, okay? Tension is the force which is in the string. And this distance is nothing but x. You tell me one thing. Sir, on this charge, this charge is having some mass. We call it has mass m. Sir, in the downward direction, force is acting, that is mg. First and the foremost thing is draw the forces acting on the body. Downward force is mg. And if I just tell you, this charge will repel this charge with a force, that is what we call the electrostatic force, Coulomb's force, K Q1 Q2 by R square. And this will be equal to K Q1 Q2, that is Q1 is Q, Q2 is Q, that is Q square divided by distance between them is x square. So downward force is mg, rightward force is electrostatic force, and my dear friends, this force is tension. Can I say this will be, if this is theta, this is also theta. So this will be T cos of theta. Okay. The component of tension from this side is T cos theta. And this will be T sine of theta. This will be T sine theta. Now all the forces are over here. The force in the upward direction is T cos theta. Force in downward direction is mg. Force from this side is T sine theta. Force from this side is Fe. Now, balance all the forces. Why? Because the charge is in equilibrium. The charge is at rest. So you balance, you can balance. You can say upward force is equal to downward force. Leftward force is equal to rightward force. Then only it is in the equilibrium. So we say T sine of theta is equal to K. We say Q square by X square. This force is equal to this force. Upward force is equal to downward force. We say T cos theta is equal to downward force is mg. This is equation number first. This is equation second. Divide first by second. Divide first equation by second. T will get cancelled out over here. Sin theta by cos theta will be tan theta is equal to, over here it will be K Q square divided by X square into mg. So from over here, first part of the question is done. You got the value of theta. Theta is equal to tan inverse of, you just have to directly remember these expressions. Tan inverse of KQ square X square into mg. Okay, this is the value of tan theta. Okay, what you are supposed to do is, in order to find this theta, first make the charge in equilibrium, draw all the forces, then make these forces equal to each other. Upward force is equal to downward force. Rightward force is equal to leftward force. Okay. Now let's find second is, let's find second. Which one? Q. Let's find X. This is the formula. Let's find this Q or X, one and the same thing. You tell me one thing. In this case, listen to me very carefully. If the question would be asked something like this, this theta would be given over here small. It will be given in the question only. Theta is very small. Theta is very small. This angle theta is very small. This will be given from the question itself. Okay. And remember, my dear friends, if value of theta is small, we say in that case, tan of theta becomes equal to sine of theta. Yes, if theta is small, tan theta becomes equal to sine theta. Now, from this triangle, could you please tell me what is the value of tan theta? What is the value of sine theta? You say, sir, sine theta is perpendicular upon hypotenuse. You tell me one thing. The length of this will be given as L. This will be given as L. And if this is x, can you say this is x by 2? Half of this distance is x by 2. So we can say in this case, sine of theta is this perpendicular upon this hypotenuse. That is x divided by 2L. This perpendicular is x by 2. This is L because whole is x. So sine theta is x by 2L. Now. This was the step which I had to do, which is mandatory in order to solve the problem. Okay. Now, if sine theta is equal to x by 2L, can I say in this case, we can write over here, instead of tan theta, we can write sine of theta is equal to k q square upon x square mg. Yes, sir. Now, over here, I can write, see, instead of sine theta, x by 2L. Instead of sine theta, I'll write x by 2L is equal. From this side, what it will be? K q square upon x square into mg. We can write k q square upon x square into mg. Can I say it something like that? This is the final equation. We are done. We got the value of q. We got the value of x. Now, from this equation, you can find q. Find the value of this q or find the value of this x. So x into x will be x cube. Okay. And then you can take this 2L over here. So it will be is equal to, this is k q square, this 2L multiplied over here divided by 2L divided by this x square, you took it over there, and what remains, that is mg. Now, this is the value of x. X will be 1 by 3 cube root kq square 2L by mg. And from this, you can find the value of, from this, you can find the value of q also. Sir, the q will be, take it over there. So x into x, x square into x will be x cube. And this mg over here, this will be mg. Okay, divided by, you have 2L, and take this k over here also. So what it will be? It will be q square. Done. If you are finding this particular question as complicated question, you can leave it, that's for sure. But I had to show it. Okay. And then afterwards, see, we are done with q, we are done with x. This is your homework. You'll do it by yourself, and you'll tell me the answer of this tension in the comments down below later on. Show me with the fire symbols and thumbs up if you got the complete question. If not, then you can watch the recording later on and you can repeat it. Give me the fire symbols and thumbs up if you got the complete question. Let me revise it in just few seconds. Okay. First and the foremost thing is, you take this, any of the charges, draw the forces T cos theta mg, T sin theta Fv, then balance the forces. Okay. T sin theta is equal to kq square by x square, T cos theta is equal to mg. Okay. Then divide the two equations. It will be tan theta is equal to kq square divided by x square mg. From here, you got the value of theta. Now we say it will be theta in this question will be given as very small. So if theta is small, we say tan theta will be equal to sine theta. And from this triangle, we say sine theta is equal to x by 2L, perpendicular upon hypotenuse. Put the value of sine theta over here. That is x by 2L is equal to kq. So from here, you can find the value of x. From here, you can find the value of q also. Done. Let's move on to the next one. I'll give you break after some time. Wait for some time, guys. Done. Is everything clear? I'll give you the break after some time. Wait for some time. Okay. Now, let's move on to the next topic, okay? That is electric field. That's electric field. Now see, what is electric field? I have showed you so many questions on Coulomb's law and forces, okay? Now I hope you would be able to solve each and every single question. Afterwards, you do this, and tomorrow I'll be taking the problem sessions, practice sessions on this one, on special classes. I want you guys to join that, okay? Also, now see, electric field. What does electric field exactly mean? Now see, let's suppose you have a magnet over here. You have a magnet over here, okay? And if I ask you, you place a coin near to this magnet, what's gonna happen? You say, sir, it will attract, it will be attracted, it will stick to the magnet. If you place it over here, it will stick to the magnet. If you place it over here, it will stick to the magnet. If you place it over here, this magnet will apply force on it, it will be attracted. If you place it over here, this magnet will apply force on it, it will be attracted. Now, if you place the coin over here very far from the magnet, sir, in that case, we say this coin will not be attracted towards the magnet. So can we say this magnet is able to attract this coin in this field only, Yes, sir. So this magnet is creating some sort of field around it. Yes, sir. Okay, let's call it magnetic field for now. But let's suppose I have a charge over here. This is a charge plus Q. And I am bringing one more test charge near to it. One more small test charge near to it. I observed that this was plus, this is also positive. This repelled it some in this direction. Now I took this charge over here. Over here, this was applying the force also. Now I'm taking this charge and placing it over here. It is applying the force in this direction. Now I'm taking the charge and placing it over here. At this position also, this bigger charge plus Q is applying the force on this one. I am placing it over here. At this position also, this is applying the force on this one in this direction. Sir, you said in this case, it is creating some sort of field. Can I not say this charge is also creating some sort of field around it? If in that field any other charge comes, like this Q naught, it experiences force. Yes, sir. It will experience force. And if you place a negative charge, it will be attracted. Yes, sir. So means this space, this region around a charge is called electric field. Like you call this as magnetic field, you call this as electric field. I hope you got it. So is it clear to each and everyone? Sir, if we have a charge, if you place another small charge around it, these small charges will experience the force. We say this charge creates a field space around it in which if any other charge comes, it experiences the force. So this space around the charge is called electric field. It is mentioned. It is a space around a charge in which if any test charge comes, it experiences force. We have a charge Q over here and the test charge Q naught comes over here, it experiences the force. So if I let suppose say I'm placing the charge Q naught over here, very far from this charge. You say, sir, now this Q naught is at very far distance. It will not experience the force. Okay, it will not, so because it is outside the field. I hope you got it. Now, listen to me very carefully. Let's suppose I have a charge plus Q. Okay. Cool. And I'm basically bringing a charge, test charge plus Q naught over here. You tell me one thing. If you bring this test charge Q naught nearer to this plus Q, what will happen? This will repel this with a force F and it will go away from the charge. If you place it over here, it will go away from the charge. If you place it over here, it will go away from the charge. So from this assumption, from this thing, from this experiment, we can say positive charge creates the electric field away from the charge. Positive charge creates the electric field away from the charge. Why? Because if you are placing the test charge over here, it is being pulled away. It is being pulled off. That's why we say because of the positive charge, the electric field is away from the charge. So we say electric field is away from the charge in case of, we say positive. Absolutely cool. Yes. Now, if we have this, let's suppose, if we have the negative charge over here and we are placing the test charge near it, you tell me one thing, what's gonna happen? Sir, this test charge will be pulled towards this charge. This will be attracted towards this charge. So it will move in this direction. If you place it over here, it will be moved in this direction. If you place it over here, it will be attracted. So from this experiment, from this thing, we can say in case of negative charge, electric field is towards the charge. Why? Because the test charge is being attracted towards the charge. We say electric field is towards the charge, in case of negative charge. In case of negative charge. Let me know in the live chat if you understood this each and everything. Okay, that's why we say every charge produces electric field. Whenever you say there is charge, it will produce electric field. Sir, because of the positive charge, electric field is away from the charge. Because of the negative charge, electric field is towards the charge. This is the direction of electric field we are saying. Done? Is it clear with the fire symbols, guys? Okay. Next we have electric field due to a point charge. Okay. Now the question is, sir, you said whenever there is a charge, it will create an electric field around it. And if in that field any other charge comes, that charge will experience the force. Yes, sir. Now my question to you over here is, sir, we are done. Now, could you please tell me what is the value of electric field? Sir, you are saying we have a charge around it, it will create electric field. The question is how much magnitude of electric field? Now we have to find, now to find magnitude of electric field. How much, what will be the formula? Like you have Coulomb's law. Similarly, how much is the magnitude of electric field? Let's suppose if we have charge plus Q at this distance, r distance away, the electric field will be, first is K. You know, sir, what is K? K, everybody knows, 1/4 pi epsilon naught. Yes, that K. K, then you have this Q. Divided by, at what distance you are finding the electric field, its square. E is equal to KQ by R square. Force was KQ1, Q2 by R square. Electric field because of this charge will be KQ by R square. Now, if I have, let's suppose, for example, 2Q at this 4R distance, how much is the electric field? E is equal to, we say K, this charge, that is 2Q, divided by, at what distance? We say 4R whole square. Done. Is it clear? Is it clear? And graph of E versus R. See, electric field is inversely. We say electric field is equal to KQ by R square. Means electric field is inversely proportional to R square. So graph will be rectangular hyperbola. Just remember it directly. Graph would come out to be something like this. And between force and R is also same, rectangular hyperbola. Okay. Next, some graph tricks. Very important. Previously, a question from this was asked in the NEET, and many times the question from this was asked in the JEE also. Okay? Yes. Now see, let me show you some of the beautiful graph tricks, and I'll show you how to make the graph, how to draw the graph. Now, let's suppose we have a positive charge over here. Remember these sign conventions. Remember these, we call it sign conventions. Sign conventions. Okay. Let's suppose we have a positive charge. Okay, fine. Sir, we know because of the positive charge, electric field is away from the charge. So how do I draw it? It will be something like this. Sir, this will be away from the charge and this will be also away from the charge. And we know, sir, because of the negative charge, if we have a negative charge, electric field is towards the charge. This is how do we draw the electric field in case of negative charge. Electric field is towards the charge and electric field is away from the charge in case of positive charge. Listen to me very carefully. If the direction, remember this, I have to show you some graph tricks. Remember these sign conventions. If you have a positive charge, electric field will be away. If you have a negative charge, electric field will be towards. The direction of electric field, which is towards the right, if the direction of electric field is towards the right, take this electric field as positive. Remember it. If the direction of electric field is towards our left, take this as negative. Towards the right, take it positive. Towards the left, take it negative. Now, could you please tell me what is the direction of electric field over here? Sir, this electric field is going towards right. So we take this electric field as negative. Sir, this electric field line, this line is going towards right. So we take this electric field as positive. I hope you got it. And what is the graph of electric field? What is the graph of electric field versus R? E versus R. Sir, we know E is inversely proportional to R square. Graph is rectangular hyperbola. Done. Now, my question to you is plot the graph between E versus R in case of two positive charges. In case of two positive charges, what I'm trying to say is that, let's suppose you have a positive charge plus Q and you have a positive charge plus Q, you have a positive charge plus Q, okay? And you are supposed to make the graph between these two. What E versus R? See. Let me show you first, then you will do on. I'll give you some more questions. That is your homework. Listen to me very, very, very carefully. Listen to me very, very, very carefully. If you have to make the graph between E versus R in case of two positive charges, this is positive charge, this is positive charge. Join them first and then take a line something like this, take a line something like this, take a line something like this, and take a line something like this, something like this, and something like this. On this axis, y-axis, place the electric field, and on this you have R, radius R, distance R. And on this you will have electric field, and from the lower side you will have minus electric field, from the upper side plus electric field, from the lower side minus electric field minus R. Done. Now, how do you draw the graph over here? Listen. When it comes to the positive charge, we know in case of positive charge, electric field is away from the charge. So it will be something like this. And when it comes to this direction of electric field, we take this direction as positive. When it comes to this direction of electric field, we take this direction as negative. Done. And sir, over here also, this is the direction of electric field away from the charge. If it was negative charge, it would have been towards the charge. I'll show you that question also. Now we say, sir, if the direction of electric field is towards right, we take this electric field as positive. And if the direction of electric field is towards left, we take this electric field as negative. Now draw. Sign conventions are done. The way I am solving this particular question, if you do not solve this particular question with the same way, 99% chances are you'll make the wrong graph. Because this is the experience, from experience I'm telling you. I have seen hundreds of students who have made the graph in a wrong way by not mentioning the sign conventions like this. That's why I'm showing you the step-by-step way. Same question was asked in the JE previously. Now see, sir, this is E, this is minus E. See, sir, from the right side of this charge, electric field is positive. You tell me one thing. Positive electric field is from upper side or lower side? You say, sir, positive electric field will take from upper side and negative electric field we take from lower side. So if you are supposed to make the graph from this side, from the right side of this charge, you make it from the upper side. Graph will be rectangular hyperbola only, but from this side, from the upper side. Why? Because electric field is positive. Now come on to this side of this graph. Come on to this side. Come on to left side of this charge. Left side. Electric field is negative or positive? Negative. Shall I make the electric field from the upper side or lower side? Sir, from upper side we take plus E. From lower side we take negative electric field. So electric field is negative, so graph would be something like this. Now come over here. Sir, when we talk about this charge, right side of the charge electric field is positive. And we make positive electric field from upper side. So this will be the direction. This will be the graph will be from upper side. Now come on to this side. Electric field is negative. If electric field is negative, shall I make the graph from upper side or lower side? Sir, you make the graph from lower. And the point where the graph meets electric field is 0 over here because it is meeting. And this is what we call the neutral point. How many of you understood this graph? I have applied my entire energy in making this graph. Come on, tell me. Everyone in the live chat, guys. In the live chat. Everyone. And if you have not liked the session yet, like the session as soon as possible. I want you guys to like the session as soon as possible, okay? Mark the attendance. Clear? Great. Okay. What if I give you the next question? If I ask you to make the graph between plus Q and graph between minus Q. Plus Q and minus Q. Let me make this graph only. I'll make it very fast. First, what we are supposed to do is make the lines. On this line, we say electric field. On this line, we say this is R. And from the lower side is minus electric field. From the upper side, it is plus electric field. From the lower side, it is minus electric field. And this is this. Okay. Now, this is minus Q charge. This is plus Q charge. Sir, when we talk about the negative charge, electric field is towards the charge. So draw the direction of electric field. This is electric field and this is electric field towards the charge. So this electric field we take negative. Why? Because electric field is towards left. This electric field we take positive. Why? Because electric field is towards right. And in this case, electric field is away from the charge because charge is positive. And we take this electric field as positive because it is towards the right. We take this electric field as negative because this is left. Now, you guys tell me one thing. Draw the graph. Sir, when we talk about this negative charge, go on to the left side of this negative charge. This is left or right? Right side. Go on to this side of electric field. Go on to this side of this negative charge. Sir, electric field is negative. If electric field is negative, shall I make the graph from upper side or lower side? Sir, lower side. Done. Sir, come on to this side of this charge, this side. Sir, electric field is positive or negative? Positive. So then make the graph from upper side. Sir, come on to this charge. When we talk about this side, electric field is positive or negative? Positive. So we make the electric field positive from upper side and negative from lower side. So graph would be something like this. They will not have neutral point. They will not meet. Okay. And come on to this side, electric field is negative. So graph will be made from this one. I hope this is clear now. I hope this is clear now. I hope this is clear now. Is this clear? Okay. Next question, if I just give you, this is your homework. This is your homework. This is minus Q and this is minus Q. Just make the graph between minus Q and minus Q. This is your homework. Okay, now we have this question. Important because these type of questions are also asked in the NEET. I know it is not visible. I'll just write the question over here. The question is basically we have a plus Q charge, we have a minus Q charge, we have a plus Q charge, we have a minus Q charge, and so on. Plus Q, minus Q, plus Q, minus Q, plus Q, minus Q. The first charge is at 1 meter. Okay. From here we are measuring. This is the origin. This is the distance from where we are measuring. This is at 1 meter from this distance. This next charge is at 2 meters. This plus Q is at 4 meters. This is at 8 meters, and so on. It keeps on. 2, 4, 8, 16, 32, and it keeps going. Okay. And you are supposed to find, question is find net electric field at origin due to all the charges. You are supposed to find net electric field at origin due to all the charges. You are supposed to find net electric field due to all the charges at origin. The formula is KQ by R square. Let me know the answer. Let me know the answer. Let me know the answer in the live chat. Wasim sir is trying to master physics. Wasim sir is not trying to master the physics. He is already mastered physics. Some of the concepts he taught me only, okay? Everyone, what is the answer of this question? I want all of you to basically solve this question as soon as possible. We're supposed to find net electric field. Let me solve it. See, sir, you said whenever there is a charge, there will be electric field. A charge creates electric field. And because of a single charge, we say, sir, because of a single charge plus Q, electric field at R distance E is equal to KQ by R square. Same formula we'll be using over here. Now see, we are supposed to find the net electric field at this origin because of this charge, because of this, all the charges till infinity. It is going till infinity. Okay. Now see, sir, let's write the electric field because of the first charge. So we say, sir, E net is equal to, because of first charge, electric field at this position will be K. This charge is Q divided by, from this point to this point, the distance is 1. So it will be 1 square. KQ by R square. Then you have minus charge over here. So we say instead of plus, we'll put the minus. We say then K, this charge is Q divided by, because of this charge, electric field at this position, electric field at this point will be KQ divided by this distance is how much? That is 2 meters. That is 2 square. Sir, why are you not mentioning the plus over here? Because the charge is negative, that's why negative. Then you have plus charge. So then write plus. The electric field because of this charge at this distance. We say, sir, K, this Q divided by, from this point to this point, the distance is 4 meters, that is 4 square. Then you have plus electric field because of this charge, as it is negative, so I'll write the negative charge. So it will be K, this charge is Q divided by, from this point to this point distance is 8 square and so on. Okay. Now, can I just write it something like this, sir? It will be K, this is Q divided by 1 square is 1 minus KQ divided by 2 square is 4, then plus KQ divided by 4 square is 16 plus KQ divided by 8 square is 64 and so on. Yes, sir. Now, from all these terms, what is common? KQ, 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 and this is minus. This is minus. This is minus. From all these terms, what is common? That is KQ, KQ, KQ. So what I'll do is that I'll write net electric field is equal to, I'll take the K and Q common. So what remains over here? What remains over here? 1 minus 1 by 4 plus 1 by 16 minus 1 by 64. I say 1 minus 1 by 4 plus 1 by 16 plus 1 by 16 minus 1 by 64 and so on up to infinity. Now, sir, we are done. Net electric field is this much. So now what we have to do, we have to add this. We have to add this, find its sum. This is what we call the geometric progression. If you keep on adding this, it will take you a lot of time. It will take you infinite time. So we have a formula how to add this. Now, how do we add this? We have a formula. We write sum is equal to sum of this GP. This is what we call the geometric progression. How to add this? S is equal to A upon, we say 1 minus R. This is the formula. Now the question is, sir, what is A? A is what we call the first term. A is what we call the first term. In this entire geometric progression, what is the first term? You say, sir, 1. So A is 1. And R is what we call the common ratio. Common ratio. Sir, how do we find the common ratio? Let me show you. Take any term over here, any term you want. Sir, let's take 1 by 16. Okay, 1 by 16. I'm showing you how to find the common term. I'm taking 1 by 16. Divide it with the term which comes before it. What is the term which comes before 1 by 16? That is 1 by 4. And it is minus 1 by 4. Minus 1 by 4. You got the common ratio. 4 ones, 4 fours. So this will be minus 1 by 4. Now R is minus 1 by 4. Even if you take this one, this will also come out to 16 ones are 16 fours are minus 1 by 4. So common ratio is 1 by 4. A is 1. So sum will come out to be A. A is 1 upon 1 minus, instead of R, I'll write what? Minus 1 by 4. Minus 1 by 4. So further I can write sum is equal to 1 upon, see, 1 minus into minus becomes plus, 1 plus 1 by 4. 1 plus 1 by 4. If I solve it, 1 upon 4 plus 1 is 4 into 1 is 4. 4 plus 1 is 5 divided by 4. And this will come out to be 4 by 5. Now, boys and girls, the sum of this is 4 by 5. Now, we can write E net is equal to KQ. Instead of all of this, I'll write just 4 by 5. So, E net is equal to KQ and this will be 4 by 5. And we know, sir, K is equal to 1 by 4 pi epsilon naught. We can write 1 upon 4 pi epsilon naught. Then you have this Q and then you have 4 by 5. 4 will get cancelled. What remains? Q upon 5 pi epsilon naught is the net electric field. How many of you got it? How many of you got it? Yes, electrostatic potential, electric charge, every damn thing will be cleared in this session only. Make sure you stick till the end. If you say, sir, I'll watch the recording tomorrow, I say no, because tomorrow you have the next session. I don't want you guys to miss that session also. Okay? And if you join that session tomorrow, you won't be able to see the recording of this session. So make sure you stick till the end. 70 days are just, we have the 70 days and we'll complete it. You have to give your 100% till the 70 days. Yes, all the chapters in the electrostatics will be completed in this session only. Just extreme killing will be there. Okay. We'll take break. See, it is only 7:24. Let me finish some content over here. Then we'll take a long break. Okay, we'll take a long break. We'll take like 30-40 minutes break. But let's first finish this one. If I give you the break right now, I'll give you just 15 minutes. And if you stick with me for some time, for some more time, then I'll give you a long break and then we'll continue. We'll have some dinner also. Okay. Next. Electric field due to a charged ring. Now see. Before this, I want to tell you something. A statement is there. That is, whenever there is charge, it creates electric field. Whenever you see charge, it will create electric field around it. That's for sure. Whenever you see a magnet, it will create a magnetic field around it. As simple as that. A charge creates electric field. Now, if I tell you, I am taking this charge. I'm taking this charge. It is in my pocket. Okay. I'm getting this charge. I'm taking this charge, and I am placing it. I'm distributing it onto this bottle. Now, charge gets occupied onto this bottle. Sir, you said whenever there is charge, it creates electric field. Now the charge is distributed, present on the bottle. Now this bottle will also create the electric field around it. If the charge is present on the bottle, it will also create electric field. If the charge is present on this pen, it will also create the electric field around it. This is the concept. Now come over here. I say, in this case, I say, sir, we have a ring. And on this ring, we have distributed Q charge. Q charge is present on this ring. It is now distributed on the entire ring uniformly. Okay, Q charge is distributed on this ring. And the radius of ring is R. Sir, you said if I distribute the charge on the bottle, it will create electric field. So will this ring also create electric field? Yes. So we say ring has the charge on it. A ring has the charge on it. So it will create electric field. So this ring will create electric field for sure. Okay. Now, boys and girls, how much is the electric field because of the ring at this x distance from the ring at point P? Now, to find the electric field because of the ring at point P, we have to find the electric field because of the ring at point P. That's it. We are supposed to do. Now, listen to me very carefully, sir. We have a formula. Can anybody of you let me know that formula in the live chat itself? Sir, this will be nothing but electric field because of ring at point P is nothing but E is equal. Because of a single point charge, it is KQ by R square. Because of this, it will be K. Q. K is what? K is, sir, constant 1 by 4 pi epsilon naught. Q is what? Q is the charge present on the ring. KQX. X is what? At what distance you are finding? At X distance you are finding electric field. KQX upon. Then we have R square. What is this capital R square? Capital R is the radius of the ring. R square plus. Then we have X square. Then we have whole raised power 3 by 2. R square plus X square whole raised power 3 by 2. We say this is the electric field because of the ring at point P. I hope you got it. I hope you got it. Now the question is, if I ask you the simple thing, sir, you are saying because of a ring at x distance, this is the ring, at x distance from the ring, electric field is this. Sir, can you tell us what is the electric field at center because of the ring? I say at center, what is the value of x? See, if you keep on decreasing the x, if you come close towards the center, the x will decrease, because at this point, if you move away from the center, x increases. If you come close to the center, and at this particular point, we say x is equal to 0. So at center, x becomes 0. If x is equal to 0, put the value of x over here, 0. So 0 multiplied by the entire term, electric field would become 0. So electric field at center is nothing but 0. Cool. Now the point is, let's suppose we have this ring. Okay. And Q charge is present on the ring. Radius is, let's suppose, R. And I am telling you to tell me the electric field very far from the ring. Very far from the ring. Sir, at this finite distance x, it is kqx upon r square plus x square whole raised by 3/2. At center, it is 0. Very far from the ring, such that x becomes much larger than r. R becomes very small if you go very large, at very large distance. So we say over here, electric field would be, what is the general formula? E is equal to kqx upon, we say r square plus x square whole raised power 3/2. Now, sir, if x is much greater than r, then r becomes very small. So we say in that case we can neglect this r over here, and we can write E is equal to, then we have k, then we have q, then we have x upon, we say it will be x square whole raised power 3/2. And this 2 and this 2 we can cancel out over here. This will be k, q, we have x. Just a second, guys. There is some light issue. Okay, now what to do, bro? I can continue?
Yes.
For sure?
Yes.
Guys, can you see it? Can you switch this light on?
Guys, just a second. Is the screen clear? See, don't look at his face. Just look at the screen. Is the screen clear?
Is the screen clear? Dark mode on. Yes.
Few days back, I taught on the same screen, basically.
Okay.
Light ho gayi thi. You can see the screen, right? People, can you see the screen? Yes?
Clear. Okay. I'll continue.
Perfect. Let him continue. And sir will give you the break at 9, huh?
At 9, huh? Okay.
9 or 8:30.
You say, bro?
8:30 he'll give you a long break, okay?
Okay, long break will take at 8:30 and then we'll continue the session.
Power go.
Kashmir,
you guys can.
in Kashmiri we say power go, huh? Power go.
Power go.
Electricity.
Say it in the chats, power go.
Electricity is gone means in Kashmiri power go.
Okay,
Cool.
so yes, it's ghost mode on. But I think it's manageable, right? The way you managed like few days back, in the similar way, you are going to manage it. I'm pretty much sure.
Okay, great.
Yeah? Everyone is saying power go. Good. Nice.
Great.
Keep on learning Kashmiri too with us, yeah? Power go.
Hashtag power go.
Yo, kala waise. Chalo, you carry on, guys.
Okay. Now see, over here, what we do is that we have kqx upon, this will be nothing but over here, this will be x cube. Okay. Kqx upon x cube. Now what I'll do is that I'll cancel this x with 1x over here. What remains? This will be kq divided by x square. So means electric field would come out to be kq by x square. Now a lot of people have questions, might have question in their mind. Sir, why did you make this? Why did you neglect this r over here? Because r is much smaller than x. It is like you have a swimming pool, okay? You are adding a bucket of water. You have an ocean. You are adding a bucket of water to an ocean. Will it create any difference? No. So by adding a small amount to a very large amount, it will not create any difference. So that's why I can neglect over here. I can write electric field is kq by x square. So when x is much greater than r, in that case, we say electric field is nothing but that is kq divided by x square. As simple as that. Second part of this one is we say if you have this ring over here, this is r radius, and we are saying very close to the ring, very close to the ring, okay, very close to the ring. At this point, in this case, we say x is much less than capital R. We say x is much less than capital R. Assume it is very close to the ring. So now, can you tell me what is the electric field very close to the ring? Sir, we say E is equal to kqx upon, we say this will be r square plus x square whole raised power 3 by 2. In this case, which term I will neglect? I'll neglect this x. Why? Because very close to the ring, r becomes very large, okay, and x becomes very small. So we say electric field would be, in this particular case, that is kqx upon, and I'll neglect over here that is x, so this will be r square whole raised power 3 by 2. 2 will get cancelled. This will be kqx divided by r cube over here. Sir, why are you not neglecting over here? In this multiplication, we do not neglect. In addition, we neglect it. So we say E is equal to kqx divided by r cube. So I have told you all the cases electric field due to a ring. Electric field due to a ring. Sir, if we have a ring, Q charge is present on the ring. At x distance, how much is the electric field? kqx upon r square plus x square whole raised power 3 by 2. Okay. Then we have if we have a ring at x distance, x is much greater than r. What is the electric field? Kq by x square. And if x is much less than r, electric field is kqx upon r cube. Okay. Cool. And this is the graph. This is the graph. Is it clear? Is it clear, guys? All the cases of this ring, is it clear? Is it clear? Is it clear? In the live chat, let me know, guys. Is it clear to each and everyone? Is it clear to each and everyone? Yes. Now see, if somebody asks you what is the graph between electric field and a radius, what is the graph between electric field and x? Graph between electric field and x in case of the ring. E versus x in case of the ring. Okay. This graph would be something like this. It would be something like this. I have made it exactly over here. It is something like this only. I'll tell you the logic of this graph also. It's something like this only. Okay. And from this side, it would be something like this only, because electric field is from both the sides. Okay, I'll tell you. See, listen to me very carefully. When it comes to the ring, sir, very close to the ring, you said electric field is kqx divided by r cube. Can you tell me, sir, very close to the ring, electric field is directly proportional to x? Yes. So graph has to be the straight line because electric field is directly proportional to the x. When x is small, at this point electric field is 0, x is equal to 0. Now electric field is very close to the ring, x is proportional to x. And when it comes to very far distance, electric field is kq by x square. I just got this expression over here. kq divided by x square, kq by x square. Now, if electric field is kq by x square, can I say electric field is inversely proportional to x square? And if electric field is inversely proportional to x square, the graph has to be rectangular hyperbola, inversely proportional to x square. So at very far distance, electric field would be inversely proportional to x square, rectangular hyperbola, and it will be straight line. And in between, I want you guys to join it with a smooth curve, not with a sharp curve. This is the smooth curve. This is not in our syllabus, okay? This is the MSc level where they discuss how does this smooth curve exactly come. We only discuss over here E is proportional to x and E is inversely proportional to x square. The graph would be this. Sir, don't you think that at this point, electric field is maximum? At this point, electric field is maximum. Don't you think at this point, electric field is maximum? Yes. At what value of x, electric field is maximum? We say x is equal to r by root 2. This is plus r by root 2. And from the another side, we say x is equal to minus r by root 2. This electric field would be maximum. So it is mentioned over here, sir, electric field is maximum at plus r by root 2. Electric field is maximum at minus r by root 2. Simply remember, guys, if you have, listen to me very carefully. If you have a ring, because of the ring, electric field would be, the graph of the electric field would be something like this, okay? And maximum electric field will be at x is equal to plus r by root 2. And over here, it will be minus r by root 2 from the another side. That's it. You are supposed to remember this much in this one, okay? Now, the next topic comes over here. Listen to me very carefully. Is it clear, guys? I need to know in the live chat, okay? Is everything visible and clear and you understood this graph and each and every single concept? Let me know. Is it clear, guys? Yes, that's great. Now let's basically come on to this one. See, I'll tell you this. This is also important. See, I'll tell you over here. If I tell you, what is this? If I tell you, what is this? You'll say, sir, this is nothing but a complete ring or complete circle, complete ring, whole ring, okay? Now I'm saying that, can you cut this ring in semicircles? Yes. You say, sir, you cut this ring in something like this. So this is one semicircle from the upper side. This is another semicircular ring from the lower side, okay? Now I'm asking you, can you cut this ring in chords? Sir, what is this chord? Chord means you cut the circle in 4 parts. This much. This is what we call the chord. Okay? Complete circle. Then we cut this circle in 2 parts, that is semicircle, and then this much part is chord. How many chords are there in complete circle? 1, 2, 3, 4. Okay? Now, another concept is, if I have this complete circle, okay, I don't want you guys to cut this in chords. I want you guys to cut some of the part of this circle, some part of this ring, and this some part is called, segment of a ring. It is not a complete semicircle. It is not complete circle. It is not chord. It is some part of the circle. It is called an arc. It is called an segment, whatever you call it. Okay. Now, let's suppose this is the center. From this point to this point, obviously, this is radius and this will be also radius. Now, let's come on to the concept. Take this part, take this segment from the ring and then place it over here. We have this segment over here, segment of the ring. This is not complete circle. This is not a semicircle, but this is some part of the ring, some part of the circle. And this is the center of that circle. So join this one, this will become radius r, and this is also radius r. And angle between these two is nothing but theta. Angle between these two is nothing but theta. Cool? Yes, sir. Now, sir, what we do is that we'll basically distribute this plus q charge on this segment only. Previously, it was distributed on the complete ring. Now we'll distribute it on this segment. Now the question is, see, segment of a ring has charge on it. Segment of ring has charge on it. Segment of ring has charge on it. So it will create electric field. So if charge is present on this segment, it will also create electric field. Where do we have to find electric field? At this point P, at the center. To find the electric field at point P, we have to find the electric field at point P. Now guys, I want you guys to remember this expression directly, and we can find all the expressions from this one. The electric field, because of the segment of ring at this point P, will be E is equal to, it is mentioned, that is 2K. Sir, do you know K? Yes, we know K. That is 1 by 4 pi epsilon naught constant. Lambda. Sir, do you know lambda? We don't know lambda. I'll tell you what lambda is. KQ, lambda divided by. Then you have R. What is R? R is this radius, sir. Then you have sine of theta. What is, sir, theta? Theta is the angle between this radius and this radius. If you join this point with one end, if you join this point with another end, angle between these two is theta, sine of theta by 2. Sir, everything we understood from this expression except one, that is lambda. So electric field because of the segment of ring, electric field due to a segment of ring at point P at center is nothing but 2K lambda by R sine of theta by 2. Let me just tell you what lambda is. See, let's suppose you have a rod over here. On this rod, positive charge is present, plus charge, positive charge Q is present. And length of the rod is L. Q charge is present, length of the rod is L. Listen to me very carefully. Q charge is present, length of the rod is L. If I tell you, divide this charge, total charge, with the total length, total charge upon total length, this is what we call lambda. Lambda is nothing but total charge upon total length, or we say this is charge per unit length. This is what we call charge per unit length. On per unit length, how much charge is present? Who is gonna tell you this lambda? What I'm trying to say, see, on the entire rod, how much charge is present? You say, sir, Q. Q charge is present on L length. My question is, on its unit length, how much charge is present? Who will tell you? Sir, lambda is gonna tell you, because lambda is charge per unit length. How do we find it? Total charge upon total area. One more example. Let's suppose you have a sheet over here. You have a sheet. This is a sheet. And on this sheet, charge is present. How much? Sir, Q charge is present. And how much is the area of the sheet? That is A. Because sheet has area, rod has length. Now I ask you to take the charge, total charge, and divide it with total area. Total charge upon total area. This is what we call sigma. Sigma is nothing but charge per unit area. Means, sir, on unit area, how much charge is present? By the help of sigma, you can find it. Sigma will tell you, because sigma is charge per unit area. So from now onwards, we can say that when it comes to sheet, we take sigma. When it comes to rod, we take lambda. And this sigma will tell you unit charge, charge present on unit area. And if we take, let's suppose this is a sphere. Sir, sphere has a volume, it's like football. And inside this sphere, Q charge is present. And sir, this sphere has a volume. This sheet has area, this has length. And now in this case, we say, sir, total charge divided by total volume. This is what we call rho. This is nothing but charge per unit of volume. So this rho will tell you how much charge is present inside unit volume. How much charge is present inside unit volume? Who is gonna tell you? Sir, this rho will tell you. So when it comes to the volume, we take rho. When it comes to area, we take sigma. When it comes to rod, we take lambda. Now you guys tell me one thing. Sir, in case of a ring, this ring is made up of rod only. If you basically fold the rod in such a way that it makes a ring, it makes a circle. So that's why we are taking lambda over here. Lambda in this case is charge per unit length. How do we find it? Q by L. Okay, this tells you how much charge is present on the unit length. You got it, guys? Yes, volume charge density, linear charge density, and surface charge density. These are the another names also. This is what we call the linear charge density, surface charge density, and volume charge density. I hope you got it. Now, so electric field because of the segment of ring is nothing but this much. Now this is a general expression. Now, if I say, in case of a semicircular ring, listen to me very carefully. How do we find the electric field? Charge Q is present on the semicircular ring, and we have to find the electric field at this point. Listen to me very carefully. Sir, if we take this, from this point, we take a line and join with one end. This is what we call the radius. From this point, we take another line, we join another end. This is another radius. Now, between these two, this is what we call theta. Sir, can we say theta in this case is 180 degrees? Yes. When you have two lines over here, theta is 0 degrees in the same direction. If this is a line, this is another line, theta is 180. And between these two, theta is 90 degrees. I hope everyone knows. Now, in this case, theta is 180. Now, previously, because of the segment of ring, this is a general expression. We'll take the same general expression. Sir, as we know, electric field is equal to 2k lambda by r. Then we have sine of theta by 2. Can I say, in case of a semicircular ring, we say theta is equal to 180 degrees. Yes, sir. If theta is equal to 180 degrees, what will be electric field? You say this is 2k lambda divided by r. And then you have sine of 180 divided by 2. Sir, 180 by 2 is 90. So we say electric field is nothing but 2k lambda by r. Then you have sine of, this is 90. Sine 90 is 1. Electric field would come out to be 2k lambda by r. So electric field, because of a semicircular ring at this point, E is equal to k lambda divided by r. I hope each and everything is clear. Because of the chord, I want you guys to find it over here. Sir, in case of the chord, how much is the angle? This is the chord. Q charge is present on the chord. So from this point to this point, this is one radius. From this point to this point, this is r. From this point to this point, this is r. Angle between these two is 90 degrees. So we say over here, theta is equal to 90 degree. In case of chord. Theta is how much? 90 degrees. So electric field would be, use the same general expression, 2k lambda by r. Then you have sine of theta by 2. Because this is the general expression. Segment of ring is the general lambda by r. Then you have sine of 45 degree. and sine 45 is nothing but this is 2k lambda by r. Sine 45 is 1 by root 2. And if you multiply it with root 2 and divide it with root 2, you multiply and divide with root 2, it will again become the same expression. Sir, root 2 and root 2 will become 2. Listen to me very carefully. Root 2 and root 2 will become 2. So this is 2k lambda by r. And then you have 1 upon this root 2 and this root 2 will become 2. And in the numerator, you have this 2. Because root 2 into root 2 is 2. This 2 and this 2 will get cancelled. So what remains over here is nothing but a root 2k lambda by r. So because of this segment at this point, electric field is under root 2k lambda by r. I want you guys to remember these expressions directly. Sir, because of a segment of ring at this point, electric field is nothing but E is equal to 2k lambda by r. Then you have sine of theta by 2. Theta is the angle between this and this. Sir, when it comes to the complete semicircle, in this case, theta is equal to 180 degree. Electric field would be 2k lambda by r. Sir, when it comes to the chord, in case of chord, theta is equal to 90 degree. We say electric field will be root 2k lambda by r. I want you guys to remember it like I have done. Let me know in the live chat if it is clear to each and everyone, or you are getting some sort of confusion in your mind. Then I'll use some other tactics in order to fit this in your mind only. Let me know in the live chat. Is it clear to each and everyone? Is it clear to each and everyone? Is it clear to each and everyone? Is it clear to each and everyone, guys? Yes. Great. Now I'll take some questions. Don't worry about it. I'll take some questions. Chill scenes. Now let's move on to this one. Let's discuss first question we have on the screen. We have a semicircular ring. So half of the part has got positive charge. Half of the part has got positive charge, and half of the part of this semicircular has got what? That is negative charge. Okay, and it is given minus lambda plus lambda. This is nothing but linear charge density over here. And you are supposed to tell me find net electric field at the center. At this particular point, you are supposed to tell me net electric field. Let me know in the live chat itself. Can you guys solve this question? What is the net electric field at the center? What is the net electric field at the center? Let me know each and everyone. See, sir, because of this is nothing. I know this is a semicircle, but we can divide this semicircle in two parts. First one is basically this chord, and second one is this chord. This positive chord and this negative chord. We can divide this in two parts. Yes, sir. Now you guys tell me one thing, sir. We know. Because of the chord, electric field at this point is something like this. This is the direction of electric field. Why? When positive charge is present on the chord, and if negative charge is present on the chord, then we say direction of electric field will be towards the charge. Okay. So now over here, can I say, sir, because of this negative side, electric field would be something like this. And how much this electric field would be? Let me just show you over here. Let me just make it over here. So we say this part contains positive charge. This part contains positive charge. This contains negative charge. Sir, because of this chord, negative side, electric field will be towards. And how much? We say, sir, root 2k lambda by r. Why? Because we know electric field due to a chord is root 2k lambda by r. Now, this will have two components. First one is this one, k lambda by r. This will have another component that is k lambda by r. Don't get confused with this one. Why? Let me just tell you. See, if we have a vector, let's suppose, if we have a vector, let's suppose f. If we have vector, let's suppose f. What angle between these two is 90? What is the resultant? You say, sir, root 2f. Because whenever the angle between two vectors is 90, angle resultant is root 2f. Now, can I come from the reverse side, from the back side? What is that? I can say, sir, if you have a vector root 2 of f, its one component will be f, its another component will be f. It is one and the same thing. Same is the case over here. If you have a vector, electric field is a vector. If its value is root 2k lambda by r, its one component will be k lambda by r, another component will be k lambda by r. Sir, done and dusted. Sir, done and dusted. Now, sir, because of this positively charged chord, electric field would be something like this away from the chord. That is root 2k lambda by r. Okay. Now, this also will have two components. First one is this, another one is this. So this will be k lambda by r and this will be k lambda by r. Now, you guys tell me one thing. Sir, clearly this vector is opposite to this vector. They will cancel each other. And you have resolved this, you have resolved this. And these two vectors are in the same direction. K lambda by r, k lambda by r. So if we can add both of these, we can add both of these. So net electric field would be, sir, k lambda by r plus k lambda by r. K lambda by r, then you have plus k lambda by r. It becomes 2k lambda by r. Done, 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 done. Clear? Towards the right. Yes, it will be towards the right. Towards the right, 2k lambda by. Okay. Now, let's move on to the next one. Sir, what is the net electric field at center? See, half of this, it is something like this. Let me make it over here. In this particular case, sir, half of the ring is given as positive charge. Okay, this is semicircle. And another semicircle, another part of the semicircle is given as negative charge. This is given as negative charge. It is given as negative charge. Okay. Electricity is back. And we are back to basics. Okay. Now, sir, half of the ring is given as positive charge, half of the ring is given as negative charge. We are supposed to find net electric field at center. You tell me one thing. Sir, this negative side part, just a second. Sir, this negative side part, this negative side, this semicircle which is having the negative charge, will be having the electric field towards itself. And how much will be the electric field? We say, sir, 2k lambda by r. Why? Because of the semicircle, electric field is 2k lambda by r. Now, you guys tell me one thing. Sir, because of this semicircle, which is having positive charge, can I say electric field would be away from the charge? And that is also 2k lambda by r. Why? Because this is semicircle. Because of semicircle, electric field is 2k lambda by r. Now, because of positive, it will be away. Because of negative, it will be towards. Both of these are in the same direction. So, net will be, sir, this 2k lambda by r, then plus 2k lambda by r. So, this would be 4k lambda by r. Done, done, done. Yes, 4k lambda by r. Okay. You have next one. Let me know in the live chat what is the answer of this one. in the live chat. And guys, if you have not liked the session, I want you guys to increase the likes right now. Mark the attendance right now, okay? Because everyone who is watching, who is learning from the session, if teacher is telling you something, you are supposed to do it right away. You are supposed to follow it, as simple as that. I'll give you the break at 8:30, okay? That was the deal actually. Okay. Yes, in this case, electric field would be 0. Why? Now see, sir, this circle or this ring is made up of 4 chords. See, if I divide this in 4 chords, this chord has positive charge. Then you have this chord, it has got negative charge. Then you have got this chord, it has positive charge. Then you have got this chord, it has got negative charge. Now you tell me one thing, my dear friends, in this case, sir, because of this negatively charged chord, electric field would be towards the chord. Why? Because in case of negative charge, electric field is towards the charge. And because of this negatively charged chord, electric field is towards the chord. Okay. Now, sir, these two electric fields would be equal, so they will cancel each other. Now, because of this positively charged chord, electric field is in this direction, away from the chord. And because of this positively charged chord, electric field is in this direction, away from the chord. So they will also cancel each other. So we say net electric field at center would be 0. 0, 0, 0, 0. Okay. I hope you got it. I hope you got it. Next we have this one. Next we have, because of the rod, electric field due to a rod. Rings and questions we are done. Now let's talk about the rod. Okay. Now see, clear? Let's suppose we have a rod over here. Let's suppose we have a rod over here. Let's suppose we have a rod over here. This is the rod we are having over here. Okay. And on this rod, positive charge is present. We have distributed charge on the rod. Okay. And if I tell you, in this case, exactly at this particular point, which is exactly at the center, at this center, at this center. At this center, okay, at this center, this is what we call the perpendicular bisector. This is a special point, perpendicular bisector. Okay, see, I don't want you guys to focus on this particular point. I don't want you guys to focus on this particular point. Yes, I don't want you guys to focus on this particular point. We have a rod, okay, and Q charge is exactly present on this rod. Sir, we say a rod has Q charge on it. A rod has got Q charge on it. So we say, so it will create electric field. If a rod has got charge on it, it will create electric field, that's for sure. Now, we are supposed to find the electric field at what distance? We say, sir, let's suppose at our distance at this particular point. This point is what we call the arbitrary point. Arbitrary point means the general point. It is not a specific point. Sir, this, if I just tell you at this point, this is an axis point. This is the perpendicular bisector point. It's a general point. Okay, this is at our distance. Now, because of this, we have to find, so it will create electric field. To find electric field at our distance, we have to find electric field at our distance. What we will do is that we'll take this point and we'll join this point with this end. Okay, fine. We'll take this point and we'll join it with this end. We'll take this point and we'll join it with this end. We'll take this point and we'll join it with this end. We call this angle as theta 1. We call this angle as theta 2. We call this angle as theta 1. We call this angle as theta 2. Now, electric field at this point would be E is equal to, listen to me very carefully. It would be K lambda. What is lambda? Lambda is charge per unit length. Whenever we have a rod, we take lambda. K lambda divided by R. R is what? At what distance you are supposed to find the electric field? K lambda by R. Then you have sine of theta 1. Then you have sine of theta 1. Plus, we say sine of theta 2. Sir, what is sine theta? Theta 1 is this angle between R and this line which is joining, which is matching at the end of the rod. Then you have plus, we say cos of theta 1 minus cos of theta 2. Yes, sir. This would be the electric field at this point. I want you guys to basically remember this expression directly. I want you guys to remember this expression. I want you guys to remember this expression directly. I want you guys to remember this expression directly. This is K lambda by R, sine of theta 1 plus sine of theta 2. This is the electric field. This is the electric field. This is the electric field at P due to the rod. Sir, whenever there is a rod, it has got charge on it. It will create the electric field at P point R distance. How much is the electric field? K lambda by R, sine theta 1 plus sine theta 2 plus cos theta 1 minus cos theta 2. Now, this is what I have exactly mentioned. And this is the general expression. This is the general expression. Now, let's suppose I say you have got the same rod over here. On this rod, Q charge is present. And at this R distance, which is exactly at this is the perpendicular bisector point. At equatorial position, or you say perpendicular bisector, or you say equatorial position. At this point, see, over here, this is not the point which is in the middle. This is a general point. This is over here, here. But when you talk about this case, this is the point which is exactly at the middle of the rod. Sir, over here, we say this theta 1 would be equal to theta 2, and let's call it theta. Now we have to find electric field because of this rod, same rod, at this point which is at R distance. At this point which is at R distance, which is the perpendicular equatorial bisector. Yes. So we say in this case, sir, use general formula. Use general formula. What is the general formula? Sir, general formula is K lambda by R. Then you have sine of theta 1 plus you have sine of theta 2. Then you have plus cos of theta 1 minus you have cos of theta 2, and this will be closed. Now, sir, theta 1 is equal to theta 2 is equal to theta in this case. So we say electric field is equal to K lambda by R. Then you have sine of, sir, what is the value of theta 1? It is theta. Plus, what is the value of theta 2? It is, sir, theta. Then plus, sir, what is the value of cos of theta 1? So cos of theta 1 is also theta because both the angles are same. Then you have plus cos of theta, and this is minus. Minus, okay? In case of equatorial point, this is plus theta 1 plus theta 2. Theta 1 minus theta 2 in this case. So this would become 0, this term. Cos theta minus cos theta is 0. So what remains over here? E is equal to K lambda by R. Sin theta plus sin theta is 2 sin theta. We say this is nothing but 2 sine of theta. So this will be E is equal to 2K lambda by R. Then you have sine of theta. This is the electric field. This is the electric field because of the rod, charged rod at equatorial point or equatorial bisector. Okay. Next we have over here infinitely long rod. Okay. If we have a rod which is infinitely long, sir, what is infinitely long? See, infinity is a relative term. If I say, sir, there is a big rod, and if I take a point very near to that rod, then for this point, this rod becomes infinitely long. If I say, sir, there is a point at this particular, this is the point I'm taking. So for this board, this is, for this point, this board is not infinity. If I'm taking this point very near to the board, so from this point now, if I'm seeing, I can see board only, okay, from all the point, from all the, in all the directions. So we say for this point, the board becomes infinity. Now, simply, you remember over here, if we have a rod which is infinitely long, let's suppose this is infinitely long rod, this is infinitely long, it is something like this. We have a rod, and this rod, okay, we have a rod which is infinitely long. It is something like this, and Q charge is present on this one. So we make infinitely long rod something like this. This is going till infinity. This is going till infinity. Now, in this particular case, listen to me very carefully. You have Q charge present on the rod. And if the Q charge is present on rod, it will create electric field. We have to find the electric field at this R distance. Now, you tell me one thing. Sir, what was theta? Theta was, if you take this point and if you join it with one end of the rod, this angle would be theta. If you take this point, if you join it with another end of the rod, this would become theta. Okay. By joining the ends of the rod, you will get theta. I want you guys to join this point with the end of the rod. Can I do it something like this? Sir, no. Why? Because this is not the end of the rod. The end of the rod is at infinity. So if you have to meet the end of the rod, you will have to go till infinity. So in that case, what we do is we make the line something like this, parallel to this one. So we assume this line will meet the end of the rod at infinity. And from the upper side also we make the line something like this. Do not get confused in this one. Whatever I am saying, just keep remembering it, as simple as that. So we say, sir, this would be theta 1 and this would be, sir, theta 2. Don't you think, sir, this is making the angle 90? So over here, theta 1 is equal to 90, theta 2 is equal to 90 degrees. Okay, theta 1 is equal to 90, theta 2 is equal to 90. Now, sir, use the general expression to find this one. We say electric field is equal to K lambda by R. Then you have sine of theta 1. Then you have plus sine of theta 2. Sine of theta 1 plus sine of theta 2. Then you have minus plus cos of theta 1 minus cos of theta 2. This is the general expression. Okay. Now over here, in case of infinitely long rod, we say in case of infinitely long rod, theta 1, theta 2 both are equal to 90 degrees. So we say here in infinitely long rod, we say theta 1 is equal to 90, theta 2 is equal to 90. So we can write E is equal to K lambda by R. Sine of theta 1, we say sine of 90 plus we say sine of 90 means 2 times sine of 90. And cos of 90 minus cos of 90, this would become 0. Okay, cos 90, cos 90. So this would become E is equal to, sir, K lambda by R. Sine 90 is 1 plus sine 90 is 1. 1 plus 1 is 2. So electric field would be 2K lambda by R. So I'll show you all the problems. Don't worry. I have put up so many problems over here. Still scenes. Okay. Don't worry. Okay. So This is basically electric field due to infinitely long rod. Similarly, if you take the semi-infinitely long rod, you can see all the details I have put up over here. Sir, in semi-infinitely long rod would be, sir, from one side it is, we say, or you say from one side, it would be finite. From one side it would be finite, okay? Mean infinity, infinitely long means it is going till infinity from upper side, from lower side, from both the ends it is going till infinity. When it comes to the semi-infinitely long rod, it is finite from this side, but from the another side it is going till infinity. This is what we call the semi-infinitely long rod. And over here, we take theta 1 is equal to 90 degrees, first theta, and another theta is equal to 0 degrees. One at 90, another at 0. If at this point you are supposed to find, then theta 1 is 0 degrees, theta 2 we say 90 degrees, whatever you say over here, another this angle, because this will be 90. So in this case, so what would be the, I'll just write the expression directly. All the details are mentioned over here. You can see. Sir, at this point, electric field because of semi-infinite, it will be, that is a root 2 k lambda by r. Directly write it. Now see, what I am trying to say, if we have a rod, which is finite, we have finite rod. Sir, at this r distance, equatorial point, electric field is nothing but, we say k lambda by r, 2k lambda by r, then we have sine of theta. This is the electric field because of finite rod at this distance, equatorial point. Then if we have infinitely long rod, it is going till infinity. We have at r distance, electric field is nothing but 2k lambda by r. And if we have semi-infinitely long, this is going till infinity from one side only. At this distance, electric field would be under root 2k lambda by r. Directly remember these expressions. Is it clear, guys? In the live chat, let me know. Is it clear to each and everyone? Is it clear to each and everyone? Guys, crystal clear with the fire symbols and the Josh. I'll give you the break in just 5 minutes. Okay, we have this good question. I want you guys to solve this question. This is a very good question from this rod. Yes, great. Okay, can you solve this particular question? See, what is given in this question is that we have an infinitely long rod, okay? And if this is the infinitely long rod, at r distance, we have a charge that is minus q, okay? And this charge is minus q and its mass is minus m. Now we are giving some velocity to this charge. And when we give some velocity to this charge, it will keep on doing the circular motion about this rod. It is like I have a rod over here and there is a charge minus q placed over here, okay? This rod is positively charged, and this is negative charge. We know this negative charge will be attracted towards rod. If we give some velocity to it, it will keep on rotating or performing the circular motion around this rod. My question to you is, what velocity should we give to this charge so that it keep on revolving in this circle? Sir, I gave velocity v to a charged particle. I gave some velocity v to this charged particle. at r distance from the line, at r distance from the rod or line, it will follow the circular path. It will move in circle. As line attracts minus q, find velocity v. With what velocity it will rotate in this? With what velocity gave I to this particular charge, so that it revolves in this circle. Now, in order to solve this particular question, you must know one thing. See, there are two forces which actually exist over here. Two forces. The first one here, two forces are acting on the charge. Sir, first one is, this charge is performing the circular motion. Whenever any particle performs circular motion, centripetal force will act on it. Remember it. Whenever a particle performs circular motion, centripetal force will act on it. And that centripetal force will be equal to, we say, mv square divided by r. This is the force acting on a particle which is performing circular motion. And another force acting over here is electrostatic force. This charge is revolving around this. Okay. Now, sir, this line is having positive charge. Guys, am I audible? Am I audible? Am I audible? Am I audible? Let me know in the live chat. In the live chat. Okay, great. Now see, sir, another force which is acting is nothing but electrostatic force. This rod is having positive charge. It will attract this negative charge towards itself with an electrostatic force, because both are having the charge. So that electrostatic force is nothing but Q times of E. Sir, what is this Q times of E? You didn't tell about this. See, remember it. I'll tell you. We have, if I say, for example, there is, I'll tell you this after some time. We have to study this, but for now, remember it. If we have an electric field is present in this region. And if we place a charge Q in this electric field, this charge Q will experience force. Whenever we place a charge Q in the electric field, it experiences force. That force is equal to, sir, Q multiplied by this electric field E. As simple as that. Now come over here. Sir, this line is having, this rod is having positive charge. So it will create the electric field over here, because whenever there is charge, it creates electric field. Because of this rod, electric field would be exactly over here. And I know, sir, I told you, because of the infinitely long rod, what is the electric field? That is 2k lambda by r. So we say, sir, because of this infinitely long rod at this r distance, the electric field would be 2k lambda by r. Now, this electrostatic force will be F is equal to Q times of E. So we say, sir, this is Q into 2k lambda divided by r. This electrostatic force. And in this case, this electrostatic force will be equal to the centripetal force. Both the forces are towards the center. Both will be exactly equal in this case. Okay? Okay? Both will be equal. Don't ask me, sir, why? Because centripetal force is not a real force. It is created by electric force here only. Just remember, this charge is revolving around this rod. Two forces will act, centripetal force and electrostatic force. Both are equal. Both are equal here. If both are equal, can I just write, this force is equal to this force? I can write it something like this. F centripetal is equal to F electrostatic. Centripetal is equal to mv square by r. Electrostatic force is equal to over here. Sir, K 2K lambda by R. So this is Q 2K lambda by R. This R and this R will get cancelled. Take it M over here. This will be M V square is equal to Q 2Q K lambda by this M. So V will be equal to Q K lambda by M and its whole root. Its whole root. Done, 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 done. Done, 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 done. It's time to take a break, guys. Let's take a break, huh? Let's take a break. Yes, exactly. The necessary centripetal force is provided by the electrostatic force. As I told you, centripetal force over here is not the real force. It is created by electrostatic force over here. And if you, I'll tell you another example from mechanics. If I have, for example, a string over here, okay? And if you rotate the string something like this, you attach a stone to this, if you rotate it, and in this case, this tension will create the centripetal force. Tension force will create the centripetal force. So, but in this example, what will create the centripetal force? We say, sir, over here, this electrostatic force will create centripetal force. And in case of gravitation, if we say one mass is revolving another around mass, so we say over there, gravitational force will create the centripetal force. All the examples, different examples. So let's take a break, guys. Let's take a break. Is everything clear? Shall I take a break or not? I want to know in the live chat. Shall we take a break or not? Shall we take a break or not? And afterwards, we'll start the electric flux. Break. Shall we take a break? Just a second. Just a second. I need to know in the live chat, is everything clear till over here? Is everything sorted? Is everything sorted? Yes. We'll take a break. We'll take a break. Okay, so we are taking a bit long break, okay, because then in the next go we'll complete the entire session. We say break till 9:10 p.m. Okay, we'll be back at 9:10. Okay, till then, bye bye. Okay, break till 9:10 p.m. Okay. So see you guys at 9:10. You guys have some dinner. Okay. I'll have some dinner and you'll also have some dinner. So thank you so much for this love and support. Okay, guys, we are back. Okay, let me know if I'm audible and visible properly, and we can start this particular session. We can start this particular session. Let me know. We can continue this session. And the guys who are new, subscribe to the channel and like this session as soon as possible. Okay, I guess we need to start now. Let's start the session. Great, 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 great. All clear. All clear. Just a second. Just a second. I'll come. Okay, guys. So, are you ready to kill rest of the session now? Okay. Let's start from the electric flux portion. Okay. What does electric flux actually mean? Okay. So, listen to me very carefully. Everybody over here. Okay. That's great. Great, great. Okay. See, let's suppose I say I have a surface over here. This is a surface. This is a surface. Sir, what does surface mean? Let's suppose I am placing some sort of area over here, a sheet over here, a surface over here, which has some area. Like this is, I am placing over here. This is some sort of area I am placing over here. This is a surface. Okay, great. Now see, sir, from over here, the electric field lines are coming. These are the electric field lines which are exactly coming from this side. Sir, where are these electric field lines coming from exactly? You say, sir, maybe some sort of charge is placed over here or some source is present over here from which electric field is leaving. So these are the electric field lines which are crossing the surface. What I'm trying to say is that if I say I have a charge over here, okay, I have a charge over here, and from this charge electric field lines are leaving which are crossing this surface, which are crossing this sheet, which are crossing this area over here, okay, and I am placing another area, I am placing another area over here, I am placing another area over here which is bit small, these are the field lines, these are the field lines which is coming from this side. Okay, now my question to you is, this is surface A, this is surface B. My question to you is, you have placed a bigger sheet, then you have placed a smaller sheet over here, and electric field lines are coming from some source, from some charge. If I ask you the simple question, how many field lines are crossing this particular surface? You'll say, sir, 1, 2, 3, 4, 5, 6. So we say number of lines, number of field lines crossing surface A is equal to 6. And if I ask you how many number of field lines are crossing the surface B, you say, sir, number of field lines crossing B is equal to 1, 2, 3, 4, only 4. So we say in that case over here, sir, flux is 4 and over here flux is 6. Sir, what does that mean? Electric flux is nothing but the number of field lines crossing the surface perpendicularly. Sir, more field lines are crossing the surface means more is flux. If I say I have a surface over here, field lines are crossing this surface means flux is being produced over here. Electric flux is nothing but number of field lines crossing the surface perpendicularly. More field lines are crossing the surface, more is the flux. Less field lines are crossing the surface, less is the flux. As simple as that. In this case, I am placing a bigger sheet, bigger area. Field lines are more crossing, we say flux is more. Field lines are less, field lines are crossing, we say flux is less. It is 4, it is 6 over here. I hope you got it. Now, my question to you over here is nothing but, we say, see, we say, if I place a bigger source over here, if I place a bigger charge over here, okay? So we say, from the bigger charge, we say more field lines will leave, okay? And if I place some surface area in that case over here, we say, sir, more field lines will cross the surface. Now, in that particular case, now listen to me very carefully. Sir, can I say this electric flux is number of field lines crossing the surface perpendicularly. Okay. Now, sir, if I say, we represent this flux with nothing but phi. Now, I say, sir, this flux is proportional to the electric field. More is the electric field, more field lines will be there. And if more field lines will be there, so more field lines will cross the surface, so more is the flux. Flux is directly proportional to electric field. And we say this flux is directly proportional to the area also. See, if you place a bigger area, in this case, you have placed this bigger area. To bigger area, more field lines were crossing, so flux was more. To smaller area, less field lines are crossing, so flux is less. So bigger is the area, bigger is the flux, large is the flux. And if electric field is strong, more electric field, more field lines are there, flux will be more. On joining these two, we say flux is equal to, that is nothing but E dot A. We can say it is something like this. Flux is nothing but E dot A. Okay, so flux is simply number of field lines crossing the surface perpendicularly. Now, listen to me very carefully. Let's suppose, in some cases, if I have a surface, this is the surface, something like this. And what is the area of this surface? You say, sir, the area of this surface is nothing but, I call that A. And area is a vector quantity. And this direction of the area is always perpendicular to the surface. If I say, for example, I have this area over here. And if you ask me, how much is the area? You say, sir, this much is the area of this surface. And what is the direction of the area? Perpendicular to this area. Perpendicular to this surface will be the direction of area. Now, same is the case exactly over here. Sir, in this particular case, the area, direction of area is perpendicular to the surface. Now, over here, if I say electric field is at some angle, this is the electric field, it is making an angle of theta. Now, when it comes to the electric flux is defined as number of field lines crossing the surface perpendicularly. You tell me one thing, sir, over here, if I resolve this electric field in two components, we say, sir, this will be E cos of theta and this will be E sine of theta. Can you please tell me which of the two components is crossing the area over here? Sir, E cos of theta is crossing the surface. E cos theta is crossing the surface. And E sine theta is just touching the surface. So that electric field which crosses the surface contributes to flux, creates the flux. And if you have to write the flux in this particular case, you say, sir, flux is nothing but electric field into area. What is the electric field? You say, sir, E cos of theta into how much is the area of the surface? That is A. You can write it something like this. This is E A cos of theta. And you can write it something like this, E dot A. That is E dot A. Okay. I hope you got it. You can write it something like E dot A. Okay. E A cos of theta, E dot A. Okay. I hope each and everything is clear till over here. Okay. So that's why I took that component of electric field which is crossing the surface. I don't have to that component which is touching the surface, because in flux, the component which cross the surface will only contribute to the flux. Okay, fine. Now the question over here is, so what is the formula for flux? We can say E is equal to, flux is equal to, so flux is nothing but E A cos of theta. And we can also say flux is nothing but E dot A. You can simply say it something like this also. Now, my question to you in this particular case is, listen to me very carefully. Sir, find the flux passing through the area. Find the flux passing through the area. You tell me one thing. Find flux passing through the area. Now see, this was the question which was asked in AIPMT 2006. In this particular case, these are the field lines which are over here. This is the electric field which is over here, something like this. It is the case in which I can show you. I have a surface, and these are the field lines which are just touching the surface. These are the field lines which are touching the surface. These field lines does not cross the surface. So we say when field lines does not cross the surface, so no flux is being produced. In this case, we say flux is equal to 0 because no field line is crossing. No field line is crossing the surface. No field line is crossing the surface. No field line is crossing the surface. Now, the next is basically the Gauss law. I'll be showing you a lot of questions on this one. Just let me finish this particular thing. What does Gauss law exactly say? Gauss law says that if, for example, we have a closed surface, this is a cube and this is a closed surface, okay? And inside this closed surface, listen to me very carefully. Inside this closed surface, we have placed a charge Q. This is a closed surface. So Gauss law says that, sir, because of this charge, electric field lines will be something like this. Okay? Away from the charge. Yes? Now, could you please tell me, sir, these field lines are crossing this surface? Yes, sir. I have a box. I have a cube. Inside this cube, I am placing a charge. Now, because of the charge, electric field will be there. And that electric field is away from the surface. And those electric field lines are crossing the surface. And if electric field lines are crossing the surface, we say here, field lines are crossing the surface. Here, field lines are crossing the surface. So flux is being produced. So over here also flux is being produced, because whenever the electric field lines cross surface, flux is being produced. Now, in order to find the flux over here, so Gauss said, I'll tell you how to find the electric flux through a closed surface. So we say, flux through a closed surface. So flux through a closed surface will be. So Gauss said, if you have to find a flux through this closed surface, he said, just write it flux through closed surface. It would be simply, that is nothing but Q inside, charge inside, or Q enclosed divided by epsilon naught. The amount of charge present inside the cube, divide it with epsilon naught. It will give you the flux through the surface. Now, in this particular case, sir, how much is the flux being produced? You say, sir, the charge present inside is Q divided by epsilon naught. if I, for example, give you the question something like this, listen to me very carefully. If I say, for example, I have this cube over here, I have this cube over here. Inside this cube, we have 2q charge. We have 2q charge. And flux will be nothing but, flux through this closed surface will be nothing but, sir, q enclosed divided by epsilon naught. So this is what Gauss said. In order to find the flux through a closed surface, simply take the charge which is present inside the surface divided by epsilon naught. So what is the charge inside the surface? That is 2q divided by epsilon naught. As simple as that. Okay, like we have the cylinder over here. Cylinder is a closed surface. Now, because of this charge, electric field lines will come out. Electric field lines will come out. Okay. So these field lines are crossing the surface. Now, sir, they will create the flux over here. Flux will be produced. So how much is the flux through this surface? You say, sir, flux is equal to q enclosed divided by epsilon naught. How much is the q enclosed? That is q divided by epsilon. Cool? Yes. Now find flux through the cylinder. Can you please tell me how much is the flux through this cylinder? Over here, flux is, this charge is not present inside the surface, but it is present at the edge, Do not make mistake over here. Do not make mistake over here. It is present at the edge. Is everything clear till over here? Let me know in the live chat. Is everything clear till over here? Let me know in the live chat. Is everything clear? Let me know in the live chat only. Clear? How much is the flux? How much is the flux in this particular case? See, I'll tell you how to do this type of question. Listen to me very carefully. Listen to me very carefully. Let's suppose we have a cylinder over here. Let's suppose we have a cylinder over here. And we have the charge which is present. We have the charge which is present at the edge. If I say this charge is present inside this cylinder, it is enclosed in the cylinder. In that case, if I ask you to tell me the flux, you say, sir, in that case, flux is nothing but q inside divided by epsilon naught. Then the question becomes very easy. But what I am trying to say is that the charge is not present inside the cylinder, but the charge is present over here at the edge. So it is not enclosed. I say here charge is not inside the closed surface. So charge is not inside the closed surface. The charge is not inside the closed surface. Now, if the charge is not inside the closed surface, what we do is that we basically attach an imaginary cylinder to this one. We attach an imaginary cylinder to this one. Let's suppose there is another imaginary cylinder which is fixed at this end, or you attach one more cylinder to this one. Okay. Now, when you attach this one more cylinder to this one, don't you think that this charge now becomes the enclosed charge? This charge appears that it is present inside this long, bigger cylinder. Yes. Now, this becomes closed surface. This becomes closed surface for Q, for this charge Q. Yes. So over here, we say over here, this closed surface is made up of how many cylinders? It is made up of 2 cylinders. Remember, this closed surface is for this charge Q is made up of 2 cylinders. Yes, sir. And we know, sir, flux through the closed surface is equal to Q inside divided by epsilon naught. Yes, sir, we know it. Now, when it comes to the closed surface over here, the closed surface for this charge is made up of 2 cylinders. One is this one, another is this one. So we say flux through closed surface. You can also say this is Q by epsilon naught. Flux through closed surface means flux through 2 cylinders. Yes, sir, flux through 2 cylinders. So in this case, we say flux through two cylinders. Flux through two cylinders is equal to Q by epsilon naught. And if I ask you to tell me flux through one cylinder, how much that will be? That will be Q upon 2 epsilon. I hope this is clear to each and everyone. What you are supposed to do in this question is that you attach one more cylinder, and when you attach one more cylinder, this charge becomes the enclosed charge. This charge now is placed inside this bigger cylinder. So this closed surface is now made up of two cylinders. So flux through closed surface is equal to flux through two cylinders is equal to Q by epsilon naught. And then flux through one cylinder is equal to Q by 2 epsilon naught. In the live chat, let me know if this is clear. Is it clear, guys? Give me a signal, I'll move on. Then I'll show you some more questions on this one. Over here, we have the charge present. We have the charge present at the edge. We have the charge present at the edge. Great, great. We have the charge present at the edge. And we are supposed to find flux through the cube. Find flux through the cube. Find flux through the cube. You are supposed to tell me the flux through the cube. Find flux through the cube. Find flux through the cube. In this particular case, see, in order to solve this particular question, sir, this is present. Let me find a cube over here. Is there a cube? Okay, I'll take this. Okay, this is a dustbin. Okay, manage it. This is some sort of cube. If I place the charge over here, how many more cubes I need to attach to this cube so that this charge becomes inside, this charge becomes enclosed charge. This charge then becomes inside this entire closed surface. Sir, one cube you attach from this side. Okay. Let me just show you over here. See, I have this cube. If I place the charge over here, it is at the edge. How many cubes I need to add more? How many cubes I need to add more so that this becomes the enclosed charge? This becomes the charge which is present inside that closed surface. You say, sir, one cube I'll attach from this side. One cube I'll attach from this side. Okay, sir, 1, 2, and another cube from this side. So how many cubes more? We say 3 cubes more. Okay. So in this case, you are supposed to add 3 more cubes. You are supposed to add 3 more cubes in order to add, yes, 3 more cubes in order to make this surface as enclosed. Just we say, sir, here attach 3 more cubes to make the charge inside that closed surface. Then charge will become enclosed charge. Now you tell me one thing. So we say flux through that closed surface is equal to flux through 4 cubes. How, sir? Because when you attach 3 more cubes and 1 cube is this one, total of 4 cubes. So flux through that closed surface, because closed surface over here is made up of 4 cubes in total. So flux through 4 cubes is equal to, that is Q by epsilon naught. We are supposed to find flux through 1 cube. So flux through 1 cube will be nothing but that is Q upon, this is 4 epsilon naught. I hope you got it. Take this 4 over there and this will be Q by 4 epsilon naught. One more question, important question. This is what you are supposed to do over here only. This is a very beautiful question. I want you guys to basically solve it as soon as possible over here. I want you guys to solve it as soon as possible over here. Okay. Now see, in this case, we have a cylinder. Inside this cylinder, the charge Q is present. Now, because of the charge, electric field lines are leaving. So if electric field lines are leaving, let me just make the figure over here. Sir, we have a cylinder. We have a cylinder over here. Okay. Inside this cylinder, we have a charge. And from this charge, electric field lines are leaving something like this, 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 something like this. Now the questioner says that, sir, if electric field lines are leaving from all the sides, so we say flux is being produced over here. Flux will be through curved surface. Flux will be through two plane surfaces. This is a plane surface. When we talk about the cylinder, a cylinder is made up of a curved surface, one plane surface, another plane surface, total of two plane surfaces and one curved surface. Now listen to me very carefully. In this particular case, we say, sir, question is saying flux passing through curved surface is given as phi. Flux passing through this curved surface is given as phi. We are supposed to find how much is the flux passing through this one plane surface. Flux passing through one plane surface. Listen to me very carefully. We say, sir, over here, this closed, or simply we say cylinder. This cylinder is made up of, it is made up of, we say one curved surface plus two plane surfaces. One curved surface plus two plane surfaces. Now, this curved surface and two plane surfaces make the closed surface over here in this particular case. So we say, sir, flux through closed surface is equal to, sir, closed surface means cylinder over here because charge is present inside. Flux through closed surface means flux through cylinder, which means flux through, because cylinder itself is made up of one curved surface and two plane surfaces, which is flux through one curved surface plus flux through two plane surfaces. Yes, sir. Now, can I say that, sir, flux through closed surface is Q by epsilon naught. So this is Q divided by epsilon naught. Flux through closed surface is Q by epsilon naught. And flux through closed surface means flux through cylinder, means flux through one curved plus two plane. So I can say flux through one curved surface plus flux through two plane surfaces. Yes, sir, I can say it something like that. Now, in the question, it is saying that flux through curved surface, flux through curved surface is given as phi. So I can write Q divided by epsilon naught is equal to, this is given as phi plus flux through two plane surfaces. We have to find flux through one plane surface. Now, can I just write over here? Flux through two plane surfaces plus phi is equal to Q divided by epsilon naught. Take it over there. Flux through two plane surfaces is equal to Q by epsilon naught minus, we say, sir, phi. Then we say flux through one plane surface will be nothing but, flux through two is this much. Flux through one will be 1/2 of Q by epsilon naught minus phi. How many of you people understood this question very properly? How many of this question understood this question very properly? Let me know in the live chat itself. Is it clear to each and everyone in the live chat itself? All the people, send some fire, send some hearts. I want my energy to go from zero level to the maximum. Okay, I hope you understood this. Let's move on to the next one. Electric field due to a hollow sphere or metal sphere. Now see. Great. Electric field due to a hollow sphere or metal sphere. What does a hollow sphere mean? See, have you seen the football? Obviously, yes. When it comes to the football, from the inside, from the inner side, there is no mass present. Nothing is present. It is air only. So mass is present on the surface only. So that is what we call the hollow sphere. Over here, we take that sphere in which charge is present on the surface only. Inside, no charge is present. It is hollow. So we call this as hollow sphere. Okay, we call this as hollow sphere. We say in case of hollow sphere, charge is present on the surface only. Charge is present on the surface only. You take that sphere in which you have placed the charge on the surface only. No charge is present inside. That is what we call the hollow sphere. Now, sir, whenever you distribute the charge on anything, it creates electric field. Over here, you are distributing the charge on this hollow sphere. So it will create electric field. I write here, charge is present on hollow or distributed charge is present on hollow sphere. So it produces electric field. So it will produce electric field. Now we are supposed to find that electric field only. The first point is, sir, where do we have to find the electric field because of that hollow sphere? Listen to me very carefully. Sir, this is a hollow sphere. The radius of the hollow sphere is given as capital R. First thing, you are supposed to find the electric field at a small r distance. We say outside. We say we are supposed to find electric field outside the sphere. And then we are supposed to find the electric field on the surface. And then we'll find the electric field inside the sphere at a small r distance. See, r is variable. For outside, r is this much. For inside, r is this much. Hollow sphere has charge on it. It will create electric field. We have to find the electric field at 3 points. The first one is outside the sphere. The second one is on the sphere. Okay. The second one is on the surface. And the third one is inside the sphere. Listen to me very carefully. Over here. Sir, when it comes to outside the sphere, we say because of this electric field outside will be that is K. How much charge is present on this one? We say, sir, Q. Q divided by at what distance you are finding the electric field, that is R. So this will be KQ by R square. Because see, sir, this is the formula which we have studied in case of the point charge only. You have charge Q at R distance, electric field is KQ by R square. Yes. Listen to me very carefully, sir. If you place a sphere, bigger ball, if you take a bigger ball and you are looking at this bigger ball from very far distance. So from very far distance, it will appear to you as a point. Even if it is a solid, if it is hollow. That's why for hollow sphere, outside at very large distance, electric field is KQ by R square. Because from very far, we consider it a point charge only. Why, sir? Because from very far distance, it will appear to you as a point only. You will not be able to see the complete big ball. No, just a point. That's why the formula is same. E is equal to KQ by R square. Now you just tell me one thing. We say, sir, if we keep on reducing this R and once we reach the surface, sir, at surface, can we say the radius is capital R? So we say at surface, we say the value of small r becomes capital R. If you keep on reducing this R, small r becomes equal to capital R. So in that case, electric field on surface would be K, this Q divided by capital R. KQ divided by capital R. Can I say it something like that? Yes, sir. This is KQ by capital R square because R is equal to capital R square. And then if I ask you, what is the electric field inside? Sir, inside no charge is present. Charge is present on the surface only. Inside no charge is present. So Q inside is equal to 0. See, sir, you have told us if there is a charge, there will be electric field. If there is no charge, there is no electric field. If inside no charge is present, will there be any sort of electric field? No. So electric field will be 0 in that case. Electric field inside would be 0 in that case. Electric field inside would be 0 in that case. Okay. Electric field inside would be 0 in that case. There is some spammer in the live chat. Okay. You don't have to focus on him. Just keep on learning the concepts, keep on studying, as simple as that. Okay. Just focus on the study. Don't keep on sending the messages in the live chat like this. Don't listen to that guy. Okay. Just focus on the study. So electric field inside would be 0. Now, if I ask you graph between electric field versus R in case of hollow sphere. Sir, we have to plot the graph between electric field versus R in case of a hollow sphere. You tell me one thing. Sir, when it comes to electric field inside electric field would be 0. Sir, this is a hollow sphere. Inside electric field is equal to 0. Okay. Now, from center to surface, electric field is 0. At surface, the electric field is equal to kq by capital R square. And outside it will be kq by small r square. So means from center till the surface is where R is equal to capital R. And at surface E is equal to kq by capital R. And outside, if we say, sir, outside is kq by small r square, means outside is nothing but inversely proportional to r square. So from surface till outside, the graph would be something like this. So E is inversely proportional to r square. The graph would be something like this. Okay. So from center till surface, electric field inside is 0. This is inside the sphere and this is outside the sphere. Electric field inside is equal to 0 and electric field outside E is inversely proportional to r square. E is inversely proportional to r square. Is everything clear over here? Is it clear? Is everything clear? Okay. Is it sorted? Let me know in the live chat, guys. I just want to know. Is it clear to each and everyone? Is it clear to each and everyone? Let's move on to the next one. Now we have a solid sphere. Okay. Solid non-conducting, we call it. Now see. Here, solid sphere means in which charge is present inside the sphere only. In which charge is present inside the sphere also. Now see, here, charge is present inside the sphere also. In case of hollow, charge was present on the surface only. Here, charge is present inside also. That's what we call the solid sphere. That is what we call the solid sphere. Okay. So this is what we call the solid sphere. Now here also, how much charge is present inside the sphere? This solid sphere is filled with the charge Q. So this will also create electric field. So it also creates electric field. Now the question is, we have to find the electric field. The first is outside the sphere, E outside, okay? The second is we have to find the electric field on the surface, okay? And the third is we are supposed to find electric field inside also at this small r distance, inside. E outside, E inside, and E surface. Sir, when it comes to the outside, from very far distance, if you have a solid ball, if you have a hollow ball, from very far distance, both of the spheres will appear to you as a points. Both of the spheres will appear as the small points. So we say outside, E outside would be nothing but that is kq by small r square. So we say at very far, we consider it a point charge only. Okay, that's great. Now listen to me very carefully. Sir, when we talk about the surface, if we keep on reducing this r, and once we reach the surface, so we say at surface, small r becomes equal to the capital R, that's radius. So we say at surface, small r becomes equal to capital R. So can I say in that case, electric field on surface would be kq divided by capital R square? Yes, this will be on the surface. Now, in this case, will the electric field be zero inside or non-zero? But over here, inside electric field is non-zero. Why? Because charge is present inside also. So we say inside the sphere, electric field is, remember it directly, it is nothing but K, that is Q. K is constant. Q is the charge inside the sphere, KQ. And then this small r, at distance, small r is the distance at which you are finding the electric field inside. From the center, KQ small r divided by, we say capital R cube. Where capital R is the radius of the sphere. Is it clear to everyone? KQR small r divided by capital R cube. Is it clear to everyone? Let me know in the live chat itself. Is it clear to everyone, guys? Is it clear to each and everyone? Okay. Great. Okay. Now, the graph of this was asked in previous NEET. Now, here, electric field graph between, this is a very important graph. We say graph between electric field versus a radius. Graph between electric field versus small r. In case of we say solid sphere. Sir, this is a solid sphere over here, and the radius of the solid sphere is r. If we say, sir, outside electric field is nothing but kq by small r square. Sir, electric field on the surface is nothing but kq by capital R square. You just told us. And then if we talk about boys and girls, inside the electric field, inside the sphere, electric field inside is nothing but, sir, kq small r divided by capital R cube. Sir, clearly we can see over here, electric field inside is proportional to small r. Sir, electric field outside is inversely proportional to r square, small r square. This is electric field outside. Electric field inside is inversely proportional to small r square. Outside it is inversely proportional to small r square. Inside it is directly proportional to small r. Now, if I ask you to make the graph between electric field and r, if I ask you to make the graph between electric field and r, sir, this is the center O where r is equal to 0, means at this particular point the value of small r is 0. And if you keep on coming out, electric field, the radius, this small r will keep on increasing. This small r will increase. Now at center, small r is 0. So this is center because small r is 0 over here. You keep on moving towards right, r will increase. Now from center to surface, electric field is directly proportional to small r. So the graph would be straight line. E is directly proportional to small r. And from surface to outside, and if we talk about outside, electric field is inversely proportional to small r square. So the graph would be something like this. So this is E is inversely proportional to small r square, and this would be the surface where r is equal to capital R. And this is outside, this is inside. This was the question which was asked in, I guess, NEET 2022 or something like that only. But this is a previous year question. This is inside the sphere, this is outside the sphere, and this is nothing but, we say, surface in this case. This is surface in this case. Is it clear to each and everyone, guys? Is it clear to each and everyone, guys? Okay. Is it clear to each and everyone? Yes, great. Give me a thumbs up, everyone. We'll move on. Okay. Now we have, guys, I'm not leaving a single concept. Remember it, I'm not leaving a single concept, and I'm showing you all the problems which are expected, which are important on this. Now see, I don't think so. You just wait, I'll cover all the topics, okay? We have so many topics which are left. Don't worry about that. Okay, great. Now see, now electric field due to infinitely large non-conducting sheet. Electric field due to infinitely large non-conducting sheet. Okay, this is what we call the non-conducting sheet. Sir, what is conducting sheet? I'll tell you after some time. Like we have over here, this solid sphere we consider as, sometimes in some books you will find that solid sphere, in some books you will find solid non-conducting. When the charge is present inside, you consider this as solid non-conducting. And when the charge is present on the surface, you say it is hollow sphere, metal sphere, or hollow conducting. These are the different names. And when it comes to this one, this is infinitely large non-conducting sheet. Let's suppose over here I have this sheet. This is a sheet on which charge is exactly present. Charge is present on the area. This is infinitely large sheet, infinitely long. It's very long. It's infinitely long. So for this point, it can behave as an infinitely long. So this is a sheet. Okay. So now charge is present over here, and I have told you before only. When it comes to the sheet, it has area, and we write it has sigma is nothing but surface charge density. Sir, what is sigma? Sigma is surface charge density. Charge present on unit area. How do you find the charge present on its unit area? By the help of sigma. We say, sir, sigma is total charge upon total area. Now, we say this sheet has charge on it. This sheet has charge on it. So it will create electric field. So it will create electric field. The sheet has charge on it, so it will create electric field. Now, in order to find the electric field, let's suppose we'll find the electric field at this point P. We'll find the electric field at this point P. Now, the electric field near to this sheet will be exactly, listen to me very carefully. We say this electric field due to a sheet will be sigma divided by, we say 2 epsilon naught. Sir, what is sigma? Epsilon naught is what? Permittivity of free space. And sir, what is sigma? Sigma is the surface charge density. Surface charge density is what? Sir, this sigma is nothing but surface charge density. And the surface charge density is what? Charge per unit area. On unit area, how much charge is present? This is the electric field because of the charged sheet. Now, my question to you is, this is the electric field in terms of sigma. That formula of electric field in which sigma is present. Now, if I ask you to tell me the electric field because of the charged sheet in terms of Q, in terms of charge Q, if let's suppose Q charge is present, if Q charge is distributed on this one, you say, sir, as we know, sir, sigma is total charge upon total area. How much is the total charge present on this one? That is Q. How much is the total area of this sheet? That is A. Now put in this equation, you will get E is equal, instead of sigma, you will put Q by A. So this is upon Q upon, this is 2A epsilon naught. This will be electric field in terms of charge Q because of the infinitely long non-conducting sheet. Now, if we have a conducting sheet, so conducting sheet would be something like this. This is what we call the conducting sheet. We have, if I just try to show you the conducting sheet example in this case, I'll just give you a little feel. If I just give you the little feel over here, see, we have this sheet, we have this sheet, okay? Now, it is something like this. This contains charge, this contains charge, okay? So it is something like this. So this is what we call the non-conducting sheet. This is what we call the conducting sheet. Conducting sheet would be something like this. The charge is present from this side. It is basically made up of these charged sheets. This charge sheet, this charge sheet. Between these two, charge is not present. So this is what we call the non-conducting sheet. Basically looks something like this. Just remember it simply. As simple as that. Now, if I just tell you, electric field because of this one, okay? It has sigma has the linear surface charge density. So this sheet has charge on it. So it creates the electric field. Now we are supposed to find that electric field only. Because of the conducting plate, conducting sheet, electric field would be nothing but sigma divided by epsilon naught. Sigma by epsilon naught. Because of non-conducting, it is sigma by 2 epsilon naught. Because of conducting, it is sigma by epsilon naught. Now, this is the electric field because of conducting sheet. Now, if I ask you to tell me, listen to me very carefully. If I ask you to tell me, find the electric field in terms of charge Q. If I say Q charge is present on this one. So you say, sir, in terms of Q, charge Q. This is the electric field in terms of sigma. That formula of electric field in which sigma is present. We have to find electric field in terms of charge Q. So you say, sir, electric field would be, that is, instead of sigma, we say, sir, sigma is equal to Q divided by A. Now the question over here is, see, how much is the charge present on this one? That is Q. And what is the area? Sir, this conducting sheet looks like it is made up of two parallel sheets. So, area of this one is A and area of this one is A. So, can we say over here area is 2A? Yes, sir. So Q charge is present on 2A area, and previously Q charge was present on A area. Over here Q charge is present on this A area, and that A area means 2A area. So over here, instead of, we say sigma is equal to Q divided by 2A. I hope you got it. Total charge upon total area. Q charge is present on 2A area. So we say instead of sigma, it is Q upon 2A, and then we have epsilon naught. Sir, electric field, this is a very important question. This was previously asked in AIPMT. Electric field, because of a conducting plate, in terms of sigma, is this sigma by epsilon naught. Electric field, because of non-conducting plate, in terms of sigma, is sigma by 2 epsilon naught. But electric field, just a second. Electric field, because of non-conducting plate, non-conducting sheet, in terms of charge Q, it is this Q by 2 epsilon naught. Over here, it is also Q by 2 epsilon naught. Means in terms of charge Q, both will create same electric field. In terms of sigma, we say electric field will be different. In terms of charge, electric field is same. In terms of sigma, electric field is same. Okay, I hope this is clear to each and every one. I hope this is clear to each and every one. Okay, now I have got a question over here. Two parallel non-conducting plates. Find electric field at A, B, and C. Don't find the electric field, just tell me where is the electric field 0, A or B. Tell me where is the electric field 0, A or B or C at A or B or C. Will the electric field be 0 at this point, or at this point, or at this point? We have got the 3 points. Is it visible? 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 Yawar sir in the chats, okay? The king is writing himself, huh? Great. Can you tell me, sir, where the electric field will be 0 if we have a sheet? This is infinitely long sheet, okay? So this is one sheet and this is another sheet. Negative charge is present on this sheet, positive charge is present on this sheet. This is plus sigma and this is minus sigma. You are supposed to tell me this is the point A, this is the point B, and this is the point C. Is the electric field 0 at A or B or C? You are supposed to tell me that only. You are supposed to tell me that only. Where will be the electric field 0? See, because of this sheet, electric field at this point will be towards the sheet. Why? Because it is minus sigma. Negative charge is present on this sheet, so it will be towards this. This is electric field due to negative. And because of positive charge at this point, electric field will be something like this. Electric field because of negative, electric field because of positive, both are in the same direction. So at this particular point, electric field net cannot be equal to 0 because both are in the same direction. Now over here, if I just tell you, electric field because of this plus sigma is something like this. Electric field because of this minus sigma will be towards this, towards the plate, towards the sheet. So we say over here electric field will be 0. Now sir, this point is close to this one and this point is far from this one, so electric field will be different over here. No, we say this point, this is infinitely large sheet, so we say electric field due to a sheet does not depend upon the distance. You see, Sir, it is Q by 2A epsilon naught. There is no distance. Sigma by epsilon naught, sigma by 2 epsilon, no distance, because this is infinitely large sheet. So this point is in front of infinitely large sheet. So electric field because of both will be same. Now, because of this negative charge at this particular point, electric field will be towards the sheet. Because of this positive sheet, electric field at this will be away from the sheet. So net electric field would be in this case 0. So electric field in this particular case is 0 at A, it is 0 at C, but it is not 0 at B. Is it clear to everyone? Is it clear to everyone? Is it clear to everyone, each and everyone, guys? Yes, 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 yes. Okay, 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 okay. Okay, this is a question, very good question actually. And in this particular case, you are supposed to tell me the value of, find the value of sigma over here. Find the value of sigma. So the question is, we have got a sheet, okay? And the charge is present on the sheet. So it has, the sigma is basically the charge density in this particular case, surface charge density. We are supposed to find this sigma only. And there is a thread, there is a string or thread attached to this one. And this is a charge which is attached to this thread. The charge is Q and the mass of this is M. Okay. And this charge is at equilibrium. This charge is at equilibrium. Stayed over there. You are supposed to tell me what is the sigma of this one? What is the sigma of this one? What is the sigma of this one? Okay. This is a sheet. Okay. I have a sheet over here and I am attaching a thread to this particular sheet. And there is a charge which is attached to this thread. Now it is placed over here. Positive charge is on this one. Positive charge is this charge. Now we say it will remain somewhere around over here in the equilibrium. It will stay over there only. And you are supposed to tell me at equilibrium, the charge Q will be in equilibrium. The charge Q will be in equilibrium. And in that case, you are supposed to tell me then find sigma. Sigma is the surface charge density of this one. Sigma is the surface charge density of this one. Surface charge density of this sheet. Okay. Sir, how do we solve this question? I'll just tell you the approach. This is your homework. I'll just tell you the approach. Sir, when this charge is exactly at equilibrium, we know in the downward direction, force mg will act. Okay. And if this is theta, we say this will be tension. This will be tension force, because there is a thread string, there is tension. If this is theta, can I say, sir, this will be also theta? This is T and this will be theta and this will be T cos of theta. And from this side, this will be T sine of theta. Yes, sir. And from this side, there will be electrostatic force, that is F is equal to Q times of E. I have told you this. Okay. Now balance the two forces over here. Balance the two forces. This T sine theta is equal to Q times of E. And more specifically, you can write this as Q into, what is the electric field at this point? Electric field would be because of this sheet. Electric field because of this would be, this is a charged conducting plate. Because of conducting plate, how much is the electric field? This is sigma by epsilon naught. Sigma by epsilon naught. You can see over here. Sir, electric field because of the conducting plate is E is equal to sigma by epsilon naught. So you can say over here, this is sigma by epsilon naught. This is charged conducting plate, sigma by epsilon naught. Now clearly you can see, sir, T sine of theta is equal to, that is Q sigma divided by epsilon naught. Okay. And then you have T cos of theta. Then T cos of theta. See, this charge is in equilibrium. Upward force is equal to downward force. Rightward force is equal to leftward force. So this rightward force is T sine theta is equal to the rightward force, this one. Upward force is T cos theta is equal to downward force, that is mg. Okay, divide this, okay, divide both the equations. So we say this is nothing but tan of theta is equal to, this is q sigma upon mg epsilon naught. Okay, now take it over there. So we are supposed to find sigma. So we say, sir, sigma is equal to, we say mg epsilon naught, and then you have tan of theta divided by this q, divided by this q. This will be the value of sigma in this particular case. This will be the value of sigma in this particular case. Is it clear to each and everyone? Is it clear to each and everyone? Is it clear? Guys, let me know in the live chat. Is it clear, guys? Is this clear? See, you were supposed to find the value of sigma over here. You were supposed to find the value of sigma over here. Okay? So, what you did is that this charge was in equilibrium. Draw all the forces which are acting on this charge. Upward force, this is tension, this is T cos theta, this is T sin theta, this is mg, this is this electrostatic force. Then balance these forces and then get the value of sigma. That's it. That's it. Next question. Okay, this was the NEET 2019 question. This was asked in NEET 2019. This was asked in NEET 2019. We have infinitely long rods. We have infinitely long rods. Okay. Now in this case, it is something like, are you able to see this? I'll make it over here. We have infinitely long rod. Okay. This is lambda. And then we have another infinitely long rod. This is minus lambda. And distance between these two is, we say this is r and we say this is r. So this is 2r. Now, we are supposed to find in this particular case, find electric field at the midway of the two line charges. We are supposed to find the electric field at this point. We are supposed to find electric field at this point. You guys tell me one thing. Because of the infinitely long rod, this is infinitely long. I have told you, sir, because of this rod, this is plus sigma and this is plus lambda and this is minus lambda. Means positive charge is present on this rod, negative charge is present on this rod. We say, sir, because of the positively charged rod, electric field is away from the rod. Because of the negatively charged rod, electric field is towards the rod. Don't you think that both the electric fields are in the same direction? Yes, sir. So we say net electric field. We say net electric field in this case is electric field due to positively charged rod, because this is plus lambda. Electric field due to negatively charged rod, because this is minus lambda. And this will be nothing but, that is 2k lambda by r, because due to an infinitely long rod, electric field is 2k lambda by r. I have told you this. Sir, this is 2k lambda by r plus, because of this, it will be 2k lambda by r. So this is nothing but 4k lambda by r. 2 plus 2 is 4. Done, guys? Is it clear to each and everyone? Is it clear to each and everyone? Is it clear? Let's move on to the next question. Okay, we have an interesting topic. Before this topic, just give me 1 minute. I'll get some water. I'll get some water. Just give me that. Okay. Now let's get done with this topic. Motion of a charged particle. Motion of a charged particle in uniform electric field. Okay, fine. What is this concept all about? Listen to me very carefully. Let's suppose we have an electric field over here. This is the electric field. This is the electric field over here. This is the electric field. In this region, we have created the electric field. Sir, how do you create the electric field? Let's suppose we have placed a bigger charge over here. Because of that charge, this is the electric field present in the region. These are the electric field lines present in this region because of that. Now listen to me very carefully. Sir, now in this electric field, I say, sir, this is the electric field. In this electric field, I am placing I'm placing a charge. Let's see what's gonna happen to this particular charge if I place a charge of Q and which has mass M inside this electric field. Let's see what will happen. Let's see what will happen. First is, we have to see motion of a charged particle in uniform electric field. This is the electric field. Inside this electric field, I am placing some charge. The first thing, whenever, remember this, whenever we place a charge inside the uniform electric field, I say it experiences force. It experiences force. Whenever you place a charge inside an electric field, it will experience a force. Sir, what will be the value of that force? We say that force will be equal to Q times of E. That force will be equal to Q times of E. Now, listen to me very carefully. Sir, we have studied if there is a force, there is acceleration. Okay? Because from Newton's second law, we say F is equal to mass into acceleration. As F is equal to mass into acceleration. So we say acceleration is equal to F divided by M. If you apply a force on anybody, it will accelerate. It will have acceleration. So we say acceleration is F by M. Now, how much is the force over here? You say, sir, QE divided by M. So we say acceleration of that charge would be QE divided by M. So means if you place a charge inside an electric field, it will experience force. Force will be applied on this charge because of the electric field. How much is that force? Q times of E. Q is the charge, E is the electric field. Now, whenever there is force, there is acceleration because F is equal to MA. Acceleration is F by M. Instead of F, you write QE divided by M. So acceleration would come out to be QE divided by M. This is the acceleration of the charged particle placed in uniform electric field. This is the acceleration of the charged particle placed in a uniform electric field. I hope this is clear. Yes, sir. Now you tell me one thing. Sir, if you are placing a charge in an electric field, you say, sir, force is being applied on this one. It will experience force. Don't you think, sir, it will accelerate or it will gain some velocity? It will have some velocity after some time. Yes. Now it will gain some velocity. And in order to find that velocity, how much will be its velocity after time t? We say, sir, V is equal to U plus AT. Use this equation. Sir, in this particular case, we consider initially it was at rest. Initially, U is equal to 0. Initially, it was at rest. We say, sir, V will come out to be 0 plus acceleration into time. What is the acceleration of the charged particle? That is QE divided by M. So we say this is QE divided by M into T. So velocity would come out to be QE by M into t. So this is the velocity of a charged particle placed in an electric field after some time t. After some time t, it will have the velocity, we say v is equal to qe by m into t. Okay. Now, if somebody asks you to plot the graph between velocity and time, clearly you can see v is directly proportional to t, so it would be a straight line. Now, sir, this is the velocity. This is the velocity. Now, what if I ask you, sir, tell me the momentum? We say, sir, momentum of the charged particle. Sir, if anybody is having mass, anybody is having velocity, it will have momentum. Okay. Now, this charge has velocity, sir, v. It is having mass m, so it will have momentum. We say, sir, momentum p is equal to m into v. Remember it directly. Sir, when it comes to momentum, we say p is equal to mass is m. And what is the value of velocity? That is q e divided by m into t. This will get cancelled. So it will come out to be q e t. So momentum of this body, momentum would be nothing but p is equal to q e into t. And if somebody asks you what is the graph between momentum and time, you say, sir, it would be simply straight line. P is directly proportional to t. Yes. Now momentum is down. Momentum is done. Now let's suppose we say displacement after time t. You are supposed to tell me the displacement after some time t. You are supposed to tell me displacement after some time t. See, sir, if you have placed a charge, in an electric field, okay, sir, force is acting on this one. So if force acts on this one, it will move forward. So after time t, how much it has displaced, how much it has moved forward, that's what we are supposed to calculate. Sir, if force is acting, it will move forward, and how much will be this displacement after time t? So we'll use the formula S is equal to ut plus 1 by 2 at square. So we say S is equal, initial velocity is 0 because initially it was at rest. And then we have 1 by 2 acceleration. So acceleration is qe divided by m. We just calculated it, t square. So this would be S is equal to q e t square divided by 2m. This is the displacement of that charged particle. And if somebody asks you plot the graph between displacement and time, clearly you can see S is proportional to t square. So the graph would be something like this. S is proportional to t square. Displacement is proportional to time square. Guys, is it clear? Is it clear to each and everyone? Is it clear to each and everyone? Let me know this displacement. I need to know in the live chat. Every one of you just write in the live chat if it is clear. Only and only then I will move forward. Only and only then I will move forward. Great. There are many topics left. Almost we're about to finish this electric charge and fields part. Then afterwards we'll start the next chapter from this one, that is potential part. That is potential. Okay, is it clear? Yes, great. Now, this is the displacement, how much displacement it has covered after time t. Now, The displacement is done. Let's talk about the kinetic energy. Kinetic energy of a charged particle in uniform electric field E. Sir, when it comes to the kinetic energy, we know, sir, kinetic energy is equal to 1 by 2 mv square. We have seen this equation from our 9th class. Now over here, as velocity, what is the value of velocity? Sir, we have recently got the velocity, that is QE by m into t. Now put the value of velocity over here, that is QE by m into t. Put the velocity over here and get the kinetic energy, that is 1 by 2 m. Instead of v, we just write this is q and this is v square. So it will be q square, e square, t square. It will be q square, e square, t square divided by m square. This square and this m will get cancelled out over here. Kinetic energy will come out to be, that is, we say q square, e square, t square divided by 2m. Okay, this is the value of kinetic energy in this particular case. And kinetic energy is also proportional to T square. This is kinetic energy and this is. Okay, cool. Yes. Now, if somebody asks you, is it clear? I hope this is clear to each and everyone. And if somebody asks you, sir, we are done with the kinetic energy. Velocity after displacement x. Sir, what does this mean? Let me just tell you. If I have this electric field E, inside this electric field, I have placed a charge Q. And we say, sir, after some time, this charge will reach over here because force is acting, it will reach over here. Previously, I asked you to tell me, after a time t, what is its velocity? Like over here. Sir, velocity after time t, that is QET by m. So after traveling the time t, how much will be its velocity? How much velocity it has gained? Now I am asking you the question. That is velocity after displacement x. I'll not mention the time over here. After displacing x, after covering the displacement x, when it has reached over here, how much is the velocity? Velocity after covering the displacement x. So in this case, we use the formula v square minus u square is equal to 2ax. Sir, v square minus initial velocity is 0, that is 0 square, is equal to, what is the value of acceleration? Sir, we know acceleration of the charged particle is q e divided by m into, sir, x. So v is equal to under root of 2q x by, this is the velocity of the charged particle after displacement x. And if somebody asks you to tell me the graph between v and x, we can clearly see that it is nothing but it would be something like this. V is proportional to root of x. So the graph would be something like this because v is proportional to root x. Now, over here, this is okay. Now one more last one I'll tell you, that is kinetic energy after displacement x. What is that? Sir, let's suppose x, so let's call this as x. After a displacement x or s, one and the same thing. Sir, when it has displaced x, how much is the kinetic energy? Because kinetic energy is 1 by 2 mv square. So how much is the kinetic energy after displacement x? You say, sir, this is a charge. When it has displaced x, after this displacement, how much kinetic energy it has gained? So we say, sir, kinetic energy is equal to 1 by 2 mv square. Now, see, what is the formula for v in terms of x? That is v square is equal to 2qex by m. Just put this equation directly over here. V square is equal to QEX by M. Because this is the velocity in terms of x. So we need kinetic energy in terms of x. We'll be putting up this equation over here. So we'll get kinetic energy is equal 1 by 2. You have M. Instead of V square, you'll put 2 QEX divided by M. Sir, this 2 and 2 will get cancelled. This M and this M will get cancelled. This kinetic energy would come out to be, that is QEX divided by, that's it, QEX. Is it clear, guys? Let me know. Is it clear? Okay. Is it clear? I'm seeing your live chat. Is it clear? Give me a thumbs up. Give me a thumbs up. Is it clear to each and everyone? Thumbs up, everyone. Momentum I have already calculated. Everyone. We'll be taking one more break at 11:30. At 11:30 we'll be taking the break. At 11:30. Okay, great. Okay, let's finish this one. Now see, we say motion of a charged particle perpendicular to the electric field. Listen to me very carefully. Previously, we were saying that, sir, this is electric field in this direction and we have placed a charge Q. The charge Q will move along the electric field. Both are moving parallel to each other. This is along the electric field. Now, this is a charged particle projected perpendicular to electric field. What does that mean? Sir, over here, electric field is in the upward direction, okay? And charged particle is moving perpendicularly inwards. Charged particle is moving perpendicularly inwards. Charged particle is moving perpendicularly inwards. It is in the upward direction. This is the electric field and it is moving inwards perpendicular. Charged particle projected perpendicular to the electric field. Previously, it was parallel to electric field and now it is perpendicular. You tell me one thing. If we have a charge, it is moving perpendicular to the electric field with a velocity u. Now listen to me very carefully. If it is moving parallel to this with a velocity u, I am saying one single thing over here to you guys. That is nothing but, sir, whenever you place a charge inside an electric field, it experiences force. So this will be the force. This will be the force in the upward direction. You guys tell me one thing. I'll tell you one more thing. If, for example, we have an electric field E, and inside this electric field, I have placed the charge Q, plus Q. And we say, sir, if the charge is positive, force will be Q times of E. And it is along the direction of electric field. Remember this. And if we have electric field, inside this we are placing a negative charge. Force will be opposite to the direction of electric field. This force will be opposite to the direction of electric field. This force will be along the direction of electric field. Now over here, sir, this is the electric field in upward direction. You are placing the charge Q. You are placing the charge Q inside this electric field. So this electric field will apply force on this one along the same direction, Now, this charged particle was supposed to go along this path. But because of the force, it will pull it in the upward direction. So the path will be deviated. It will go something like this and it will come out. And when it comes out, it will come out at an angle of theta. Okay? The electric field, this charge was supposed to go straight. but because of the force in the upward direction, it will pull it in the upward direction. So the path is deviated and it leaves with a velocity v at an angle of theta. Now in this case, one important point is to notice what is the value of this theta. The value of this theta is, I want you guys to remember, the value of this theta is, we say tan of theta, at which the angle it leaves, it is nothing but q. Q is the charge, E is the electric field, D is the distance in which electric field is present, divided by M. M is the mass, and then you have U square, mu square. U is with what velocity you have launched it, with what velocity you have launched it. Class will end, it will take some hours, okay? We have to complete the entire chapter. Please don't keep on asking the same question over and again. Yeah, dipole will be coming up on that one. Okay, so this is basically the value of tan theta. This is the value of theta at which this charge leaves, that is qd upon mu square. Okay, now what I'm trying to say is, listen to me. We say tan of theta is equal to qed upon mu square. See over here, sir, the question in this case is, the point in this case is, we say this theta is proportional to q. This theta is directly proportional to q. This theta is directly proportional to electric field. This theta is proportional to d. What does it mean? See, if for example, you have this electric field E, you have this electric field E, and you are sending this charge inside this, okay? Now, more is the value of charge, more force will act on this one, because F is equal to Q times of E. Sir, force is equal to Q times of E. If charge is more, force is more. So, if force in the upward direction is more, the deviation will be more. So, that's why. So, if deviation is more, theta will be more. Theta is directly proportional to Q. And then we say theta is directly proportional to electric field. If electric field is strong, means this electric field is strong, force is strong. So we say deviation is more. It will deviate more. If d is more, if this distance is more, so for the more time this charge remains in the electric field, we say theta will be more. I hope you got it. And theta is inversely proportional to m. Theta is inversely proportional to u square. More is the mass, deviation is less. More is the velocity, more fastly it will cross this electric field. Just remember it. Now the question is just direction of this is something like this. Now the question over here is, we have an electron. This is the electron we have exactly over here. This is the electron we have over here. Okay. And we are releasing there is an electric field. There is the electric field in the upward direction. This is the electric field in the upward direction. And inside this electric field, we have placed an electron. Now this electron will fall. Okay. It will fall down. Okay. It will fall down. Because this force will apply, this electric field will apply the force on this electron in the opposite direction. It will fall down. Okay. When it falls down, it will take the time, we call it time of electron. How much time it takes in falling down is time of electron. Then we have this electric field in the downward direction. Okay. And over here we have a proton, that is a positive charge. And the mass of proton is, we say, mp. Mass of proton is mp. Mass of electron is me. And this proton also falls down. The time of falling of protons tp. How much time does it take in falling is tp. How much time does it take in falling is te. We are supposed to find which will take less time in falling. If electron falls in electric field, if proton falls in electric field, which will take less time in electric field? Can anybody tell me in the live chat which can take less time in falling? We say, sir, in order to find the time, listen to me very carefully. We say use to find the time of falling. To find the time of falling, use S is equal to ut plus 1 by 2 at square. So we say S. S is what? S is the height. Let's suppose it has h height, it is coming down. So this will also come down h height. So we say h is equal to initial velocity. We are releasing both of these. Initial velocity is 0. 1 by 2. What is the acceleration of a charged particle placed inside the electric field? You say, sir, acceleration is nothing but QE divided by M. Acceleration is QE by M. So we say this acceleration will be QE divided by M into T square. Now from over here, you can find the value of T square. 2M, take this 2M, multiply it with over here. So you say it will be, that is 2M, this 2M into this H divided by, this will be, sir, QE is equal to yahan se T square. Okay, so this 2M multiplied with the 2H, this QE divided over here. Now this T will be nothing but under root of, that is 2mH divided by QE. Now you tell me one thing. See, this time, this 2H, both are falling the same height. This is the time. This is the formula for time. This is falling the height H. This is falling the height H. Both are falling the same height. Yes, sir. The charge on this is plus E. The charge on this is minus E. But in terms of magnitude, both has the same charge. Yes. Sir, electric field. This is placed in the electric field E. This charge is also placed in the electric field E. Yes. Now, what is different? Mass. Mass of this is MP. Mass of this is ME. We can clearly see over here. Time is, we can clearly see over here. Time is proportional to mass. Now, we know, sir, mass of proton is greater than mass of electron. If time is proportional to mass, then we say time of proton, time of falling of proton is greater than time of falling of electron. So proton has more mass, it will take more time in falling. Electron has less mass, it will take less time in falling. So electron will take less time in fall. I hope you got it. First we calculated, we got the relation of T, then we got the answer. Is it clear, guys? Let me know. Is it clear, guys? Each and everyone, I just need to know over here in the live chat. I'm watching, I'm seeing your comments. And I want each one of you, every one of you to like this session as soon as possible. I want every one of you to like this session as soon as possible, because that is mandatory. Okay. Everyone like the likes are 805. I want these likes to become 900 right now only. Let's see if you can make these 900. Can you guys make these 900? I'm watching. Okay, let's complete this. Now see, at 11:30 we'll take a break. Okay, don't worry about that. Now see, over here in this particular case, we got this question. Let's move on to the next one. Okay, Three particles with same velocity perpendicular to the field under uniform electric field. We have this uniform electric field E. We have this uniform electric field E. Okay. And inside this we have placed A, B and C, three particles. Okay. And now the electric field has to be something like this. This is the electric field. And now you guys are supposed to tell me which one has the highest charge to mass ratio. That means Q by E, charge to mass, Q by M. Q by M. Which one has highest Q by M ratio? Which was has highest Q by M value? This one, this one, this one. It is very simple. Sir, see, there are three particles, A, B, C. This particle is moving something like this. This is something like this. This is something like this. All the three gets deviated because of the electric field. Because of the electric field. Now, we know, sir, tan of theta, deviation is equal to QED divided by MU square. Now, clearly you can see over here, Q by M is proportional to tan of theta. We say tan of theta is proportional to Q divided by M. Tan of theta is proportional to Q by M. Charge upon mass ratio is proportional to tan theta. So, the one which has more deviation will be having more value of Q by M. Clearly you can see, sir, this is A. Sir, this is B. And this is, sir, C. C has more deviation. C has more deviation. C has more deviation. So, it has more Q by M ratio. It has more Q by M ratio. Cool? Yes, sir. Now comes basically the electric dipole. We'll finish this electric dipole till 11:30. We have to get done with this particular chapter. Do you guys want me to finish this particular chapter till 11:30? Then we'll start the potential afterwards. Let me know. You guys want me to finish this till 11:30? Then we will start with the potential part. Okay, great. Okay. Now see, let's talk about the electric dipole. Listen to me very carefully. Electric dipole. Sir, what does electric dipole mean? Let's suppose I have a positive charge over here. I have a negative charge over here. Both are separated by some distance. Let's call this as a D. Okay. So whenever you have a positive charge, you have a negative charge. Both are separated by some distance D. This combination, it is called, we say electric dipole. It is called electric dipole. Means, sir, whenever you have a positive charge, you have a negative charge separated by some distance. This combination is called electric dipole. This formation is called electric dipole. Means, sir, in this electric dipole, the number of positive charge is equal to the number of negative charge. Can I say in this electric dipole, net charge has to be 0? Yes, sir. So, we say, sir, two equal. Sir, these two charges are equal. Two equal and opposite charges. Sir, these two charges are equal. These two charges are opposite. This is positive, this is negative. So, two equal and opposite charges separated by some distance, forms electric dipole. Sir, whenever you have two equal and opposite charges, we say separated by some distance, they form the electric dipole. Sir, can I call this plus 2q and plus 2q as electric dipole? No, no, no. These are two equal charges separated by some distance, but they are not opposite. They are not opposite. Over here, we say, sir, no. Can I say, sir, this is minus 4q, this is plus 2q. Are they, is this a dipole? We say, sir, no. Why? They are opposite in nature, but they are not equal. Sir, if I say minus 4q and then plus 4q, they are separated by some distance. Is this a dipole? Yes. The condition is the two charges has to be equal and opposite, okay, separated by some distance. So that's what is mentioned over here. When two equal and opposite charges are placed at a very small distance, it forms the electric dipole. Now, one more concept is exactly over here. That is nothing but this dipole has a dipole moment. This dipole has a dipole moment. And if I say this is minus q, this is plus q, its dipole moment is from negative charge to positive charge. Its dipole moment is from negative charge to positive charge. If I say this is minus q, this is plus q, its dipole moment is from negative charge to positive charge. And this dipole moment P is equal to, we say this is equal to charge, or we say magnitude of charge. Magnitude of charge multiplied by distance. Just a second. Magnitude of charge multiplied by distance between them. Magnitude of charge multiplied by distance between them. Okay, this dipole moment. So we can say, sir, this dipole moment, what is the magnitude of charge? Take it, that is q. Take any of these two charges as q, and distance between them, let's call this as d, q into d. This will be the dipole moment. So sir, when it comes to the dipole, two equal and opposite charges form a dipole, and the dipole has a dipole moment. The direction of that dipole moment is from negative to positive, and the value of this dipole moment is q into d. Okay, it is from negative charge to positive charge. Okay, now we have a question over here. The question is, find electric dipole moment, net electric dipole moment. Over here, we're given minus 2q charge, plus q charge, plus q charge. The first and the foremost thing is this a dipole? Is this a dipole? See, this is minus 2q, this is plus q. This is plus q. Can you guys let me know, is this a dipole in the live chat? Is this a dipole? Can you please tell me, is this a dipole? Can they form a dipole? See, they are not equal. They are not equal. Is this a dipole? Is this a dipole? Let me know in the live chat. I need to know how many of you are understanding each and every single thing. Is this a dipole? Yes or no? We say yes. It is a dipole. Sir, how? Let me show you. See, this is plus q charge, this is minus 2q charge. Can we make it something like this? This is minus 2q charge. If we break it, can we write it? This is minus q and minus q separately. Sir, minus q and minus q again becomes minus 2q. And this plus q I'll write over here. And this plus q I'll write over here. Yes, sir. Now, you guys tell me one thing. Sir, this minus q and this plus q forms one dipole. This minus q and this plus q forms another dipole. Yes, it was a dipole. Now, this dipole has a dipole moment separately. This dipole has a separately dipole moment. So its dipole moment is from negative charge to positive charge. We say that is P. We say that is P. This dipole moment has a dipole moment from negative charge to positive charge. That is P. Now, this P is something like this. This P is something like this. Okay. Sir, between this P and this P angle is 120 degrees. So we say this angle is 120 degrees. We say this angle is 120 degrees. Do you guys know I have told you in the starting, whenever the angle between the two vectors is 120 degrees, we say, sir, the resultant dipole moment P net in that case will be P only. If this is F, resultant will be F only. So in this case, net dipole moment is P, and P is equal to Q into distance between the charges, that is L. So we say Q into L. I hope you got it. Yes. Next, can you find the net electric dipole moment in this case? You have plus 2Q minus Q plus 3Q minus 4Q. Can you find the net dipole moment in this case? Plus 2Q minus 4Q plus 3Q. Can you find the net dipole moment in this particular case? See, I'll tell you. Sir, let's make it over here. 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 Now see, sir, this is minus Q. This charge is minus Q. Let me just write the minus Q as it is. Sir, this is plus 2Q. Let me write plus 2Q as it is. Plus 2Q as it is. And this is plus 3Q at this corner. Sir, I'll do one thing. I'll write plus Q over here and plus 2Q over here. Because this is plus 2Q, plus Q is plus 3Q. So it becomes again plus 3Q. And at this corner, we have minus 4Q. We can split it in plus minus 2Q and minus 2Q. Minus 2Q minus 2Q plus Q plus 2Q. I hope each and everything is clear and sorted. Yes, sir. Now, sir, this forms one dipole. This forms one dipole. I'll just write it over here. Just a second. So we say this forms one dipole over here. This forms one dipole over here. This forms another dipole over here. And this forms another dipole over here. Yes, sir. Yes, sir. See, minus Q, equal and opposite charges. Sir, minus 2Q plus 2Q, another equal and opposite charges. This is another dipole. Now, the dipole moment of this will be from negative to positive, and let's call this dipole moment as P, from negative to positive. And the dipole moment of this will be from negative charge to positive charges. Let's call this as 2P. Why, sir, 2P? Because the charges are 2Q, 2Q over here. The charges is Q and Q over here. That's why it is 2P. And in this case, this is the dipole moment, that is 2P. That is from minus 2Q to plus 2Q. I hope each and everything is sorted. I hope each and everything is sorted. Yes, sir. Now let me make these over here. Sir, this dipole moment is in the downward direction, so this will be 2P. And this dipole moment is in the forward direction. This is, sir, 2P. Sir, this dipole moment is in the upward direction. I can make it somewhere around over here. That is, sir, P. That is, sir, P. Now, you guys tell me one thing. Sir, what is the resultant of this dipole moment and this dipole moment? This is 2P minus P. Upward is less. This vector is less than this vector. So, result will be, sir, this is 2P in the forward direction as it is. And in the downward direction, 2P minus P, this is P. Now, this 2P and this P will have the resultant something like this, that is P net. And I know how to find the P net, sir. How do we find this P net? We say this P net will be under root of. If you have this vector, you can find the resultant of these two vectors as under root of. This is 2P whole square plus this is P square. Don't say it will be under root of P. Why? Because then in that case, this vector has to be equal to this vector. This is twice P, this is P. So just find the resultant something like this. So this P net in this case will come out to be 2p square is 4p square plus p square plus p square and then under root. Okay. So it will come out to be 4p square plus p square is 5p square and square root will get, this will be p root 5. P root 5, how many of you? P root 5, how many of you got the p root 5? How many of you got the p root 5? You got it? Let me know, guys. Is it clear to each and everyone? Okay, great, great. Electric field due to an electric dipole. Electric field due to a dipole on the perpendicular bisector. See, we have a dipole over here. This is minus q charge. This is plus q charge. Distance between them is 2a. Now, we know, sir, whenever there is a charge, it will create electric field. Because of this charge at this point, electric field will be there. Because of this charge at this point, electric field will be there. Okay. Because of this charge at this point, electric field will be there. Because of this charge at this point, electric field will be there. So because of both the charges, what is the net electric field at this point? So that is the electric field due to a dipole. Sir, electric field due to this dipole at this point, this is what we call perpendicular bisector. From this point till this point, this is perpendicular bisector. This is the point which is on the axis. So electric field because of this at perpendicular bisector is, oh, I'll just write dipole has charge in it. So dipole contains charge. So it will create. So it will create electric field. So I say to find that electric field at perpendicular bisector. So that electric field will be nothing but E is equal to, we say, Kp divided by x cube. This will be nothing but Kp by x cube. On the perpendicular bisector, electric field will be Kp by x cube. I want each one of you, every one of you to let me know in the live chat only, and then we can move forward. Is it clear to each and everyone? Is it clear to each and everyone, guys? And then we'll move forward. Okay. So this is nothing but Kp by x cube. And more specifically, if we say that is minus Kp by x cube because it is in the backward direction. So electric field because of the electric dipole at this point is minus Kp by x cube. Now, sir, we have this dipole. Because of this dipole, electric field at this point, which is at x distance. Now over here, let me come back. Sir, what is this x? K is constant. P is what? P is the dipole moment. This P is dipole moment. Electric field because of this dipole at this is nothing but K P by x cube. P is the dipole moment. How do we find the dipole moment? Magnitude of charge into distance between the charge. Divided by x cube. X cube is the distance at which you are finding this. This is the x. Okay. Then you have over here. Then you have over here. Then you have over here. In that case, just a second. On the axis, then you have over here on the axis, electric field at the axis. You say, sir, electric field on the axis is nothing but 2kp. P is the dipole moment divided by x cube. This is the electric field because of the dipole on its axis, Electric field because of the electric dipole on its axis, on its axis, on its axis. Just a electric field because of the electric dipole on its axis, that is twice kp by cube. Fine. Now, sir, first we talked about the electric field because of the electric dipole on perpendicular bisector. Second, we talk about the electric field because of the electric dipole on the axis. Third, we are talking about the electric field at the general point. This is the minus q charge, this is plus q charge, this is the x distance, and this is the general point, this is theta. Now, to find electric field at general point, this is, see, if I just talk about this point, this is perpendicular bisector. If I talk about this point, this is axial point. But when I talk about this particular point, this is not an axial point, neither a perpendicular bisector point, but it's a general point. So over here at this point, electric field will be, that is K, we have P, we say electric field is nothing but Kp divided by x cube. Then we have under root of 3 cos square of theta plus 1. 3 cos square theta plus 1. Sir, what is K? K is constant. What is P? P is the dipole moment. And what is X? X is the distance at which you are finding the electric field. And then you have 3 cos square theta. Theta is the angle, this, between this line and this dipole moment. Now, over here, listen to me very carefully. Even if you remember this formula only, you can find the electric field on the axis and perpendicular bisector. How? Let me just tell you. If I say, sir, you come on to this axial point, so you will have to decrease the theta. This angle, this is the theta. You will have to decrease. And when you reach over here, this becomes the axial point. So can I say at axis, we say theta is equal to 0 degree. Yes, sir. If you keep on decreasing, and this is the 0 degree, because this is the line, this is along, this P is along this line only, then theta is equal to 0. So on axis, what is the value of theta? It is 0. Now you tell me one thing, angle, it is the angle between this line and this. So when you decrease it, it will be 0. So we say electric field will come out to be, that is Kp upon x cube. Then we have under root of 3 cos square, cos 0, that is 1, because at axis theta is equal to 0. Cos 0 is 1. So this is 3 plus 1 is 4. So root 4 is 2. Electric field will come out to be 2 Kp divided by x cube. We have the legend in the house.
What's up?
We have legend in the house.
What's up?
In the chats, people.
What's up? Where is the Josh? Where is the Josh? Where is the Josh, people? Where is the Josh? Where is the Josh? Yawar sir has been teaching you from past 6 hours. Yes? Definitely he would deserve some hearts, some fire emojis. Yes? So where is it? Let me know quickly in the chats. Where is it? Where is it? I would want a lot of hearts, a lot of fire emojis in the chats, people.
We want a lot of hearts for the Wasim sir only, okay?
For me, I will get.
Great.
So what's up? How is it going, guys? All enjoying? I could see it. I'm constantly checking the session. You guys are enjoying. That's absolutely amazing, right? Finally, you got the perfect match for your physics. And absolutely, I can see like all your things in the chats. You guys are loving it. That's great. And sir is absolutely teaching in detail, right? I think every single thing he has touched till now, whatever topics he has covered. And I believe this is the first time you are seeing this kind of physics, right? Honestly. Otherwise, all the electrostatics chapter, it used to be done and dusted in 2-3 hours, right? You are going to fall in love with physics, people. Trust me on that. Exactly. Yes, he's my younger brother, by the way. He looks old. He's not. He's not. He's not. Great, great, guys. Glad to see your Josh. So I think this chapter will take further 3 to 4 more hours, I believe.
3 hours.
3 hours.
Yes, it will take 3
So,
hours.
chalo, wishing you all the luck, Yawar sir, as well as all the students watching him right now.
Yes.
Yeah. Yes, sir, his teaching is like yours. Congratulations. Congratulations, Yawar.
He's going to make fun of me afterwards. Okay, so don't comment like this.
He's gone now. he has to listen to this for one complete week.
Now he'll roast me completely.
Chalo, perfect. Chalo, guys, you carry on. I thought of coming just to boost you up. Yeah. And you are already boosted. Yes, Yawar sir absolutely is OP. Overpowered. Yeah. So keep on showering love to him. Yes. And he'll make sure that he gives you the best of the content, right? As far as your NEET as well as JE is concerned. Hello, guys. You take care. Carry on. God bless you all. By the way, our tomorrow's session is postponed. I'm not going to take general organic chemistry tomorrow, right? So that session is postponed to Sunday. So tomorrow there will be one session in which all the NEET English educators, right, will be there. I mean, we'll interact with you. We'll have the strategy session and all. Perfect. We all are going to come together tomorrow and have a session with all of you. Yeah. Perfect. Our general organic chemistry session will be on Sunday now. Sunday 5 p.m. that's going to happen. Perfect. Chalo, let him complete the chapter. After that, he has to come to me only. Yeah.
Okay.
Chalo, see you guys. Take care. God bless you. Bye.
क्या कर रहा हूँ? क्या इसका सही? Okay, let's continue this particular session. Now see over here. So we say if we play at axis, we say theta is equal to 0 degree. So in that case, we say electric field will come out to be 2kp by x cube. See, that's what I told you over here. On the axis, electric field is 2kp by x cube. That's what I'm saying. You are supposed to remember this general formula. And for axis, make theta is equal to 0. And at equatorial bisector, don't you think, sir, this angle would become 90 degrees? See, if you keep on increasing and it becomes 90 degrees at equatorial point or perpendicular bisector, we say theta is equal to 90 degrees. And if for this particular point theta is equal to 90 degrees, use the same formula. Sir, we say electric field is nothing but that is kp divided by x cube under root of, this is 3 cos square of, we say 90 plus we say 1. Okay. So in that particular case, cos 90 is 0. So this will be 0 plus 1 is 1. So root of 1 is 1. Electric field will come out to be that is kp divided by x cube. This is what I told you. Electric field due to an electric dipole at perpendicular bisector is kp by x cube. This is what you got over here. Just remember this general formula, okay? And then at axis theta is equal to 0. At perpendicular bisector, we say theta is equal to we say 90 degrees. Theta is equal to 90. Now this is a question which you are supposed to solve. We have a dipole over here. This is the dipole 1, P. We have another dipole over here which is something like this. It is something like this. We have to find the electric field at this point which is at x distance. This x distance is from this dipole also, from this dipole also. Because the dipoles are small, that's why we take x distance for both. Now you tell me one thing. We have to find the electric field at this particular point because of this dipole. We say because of this dipole, electric field at this particular point. Listen to me. It will be, sir, that is nothing but that is K 2kp divided by x cube. See. This point will behave as an axial point for this dipole. This point will behave as an axial point for this dipole. This point will behave as an axial point for this dipole because this is on its axis. So, for this dipole, electric field at this point is 2kp by x cube because at axis electric field is this. Now, this point will behave for this dipole as perpendicular bisector. So, because of this dipole, electric field at this will be kp divided by x cube because electric field due to a dipole at perpendicular bisector is kp by x cube. Now you have one vector, you have another vector. Again I am saying for this dipole, this point behaves as axial point. For this dipole, this point behaves as equatorial bisector or perpendicular bisector. So electric field will be in the opposite direction. If this was the electric field, if this was the electric dipole, at this point electric field was in the backward direction. So that's what over here. So first, okay, now we say one vector is in this direction. So can we say this will be the net electric field, and net in this case will be nothing but under root of, we say that is 2kp divided by x cube its whole square plus this, that is kp divided by x cube its whole square. Solve it and you will get the answer. I hope you got it. Let's move on to the next question. Okay. Electric dipole placed in a uniform electric field. Electric dipole placed in a uniform electric field. Now see, let's suppose we have an electric field placed over here. We have an electric field over here. And inside this electric field, I am placing a dipole. Dipole means negative charge and positive charge separated by some small distance. Okay. Now, in this particular case, listen to me very carefully. In this particular case, if I say, sir, distance between them is something, and sir, this is the dipole moment from negative charge to positive charge. I have an electric field. Inside the electric field, I am placing a dipole, and the dipole moment of the dipole is P. Now, on this positive charge, listen to me very carefully. Sir, the direction of electric field is in the forward direction, such that the angle between these two is theta. Angle between electric field and dipole moment is theta. Now, I am saying that whenever you place a dipole in the electric field, sir, on this positive charge, force will act in the forward direction. Because we know, sir, whenever we place a positive charge in electric field, force acts along the direction of electric field. And when we talk about this negative charge, force acts opposite to the direction of electric field. Fine. Don't you think that we have a dipole something like this? One force is acting in the forward direction, another force is acting in the backward direction. These two forces will try to rotate the dipole. Yes, sir. These two forces will try to rotate the dipole. So these forces will rotate the dipole something like this. So whenever there is a rotation, we say torque is produced. Torque is something which is produced whenever any body rotates. We say, listen to me very carefully. If I have a block, it moves forward. We say, sir, this block moves forward because of the force. Now, if I say this rod is rotating, we say it is rotating because of the torque. Whenever there is rotation, there is torque. Now see, over here, because of the two forces, because of the two forces, we can say because of the two forces, the dipole will rotate. The dipole will rotate. Because of the two forces, the dipole will rotate. So whenever there is rotation, there is torque. So torque is produced. Sir, if there is a rotation, if I say this body is rotating, it is because of the torque. If I say this body is accelerating, it is because of the force. Now, in order to find that torque, we say to find that torque. We're supposed to find that torque. Sir, that torque will be equal to, listen to me very carefully. That torque will be equal to, what is the value of dipole moment over here? That is P. And what is the electric field? That is E. And then PE. Then you have sine of theta. PE sine of theta. PE sine of theta. So this is the torque which is being produced over here. Sir, from now onwards, we remember, if there is an electric field, you place a dipole in that electric field. Sir, the dipole will rotate in that electric field. So torque is produced in that electric field. Sir, that torque will be PE sine of theta, or you can call this as torque is equal to P cross E also, because AB sine theta is equal to A cross B. Sir, PE sine theta is equal to P cross E. This is the value of that torque. Now, there are some points in this that I want you guys to know, that I want you guys to remember, is that the first is, listen to me very carefully. The first is, if theta is equal to 90 degrees, what does that mean? You have the electric field, and you are placing the dipole something like this. This is negative charge, this is positive charge. So dipole moment is in this direction and electric field is in the forward direction. Over here, we say theta is equal to 90 degrees. Theta is equal to 90 degrees. In this particular case, sir, what is the value of torque? We say, sir, torque is equal to PE sine of theta. Sir, theta is 90. You say, sir, PE, we say sine of 90 degrees. Sir, we say in this case, torque, sine 90 is 1, torque is PE. And this is what we call the maximum torque. So it is like if you place a dipole inside an electric field, something like this, maximum torque will be produced, maximum rotation will be there. Okay. So force on this will be something like this, force on this will be something like it will rotate. Now, if I say over here, if we say theta is equal to 0 degrees, if I say theta is equal to 0 degrees, listen to me very carefully. Sir, this is the electric field. This is the electric field. Okay. This is the electric field. Okay. Now, if theta is equal to 0 degree means, sir, this is negative charge, this is positive charge. And dipole moment will be from negative charge towards the positive charge. Dipole moment will be from negative to positive. Now, in this particular case, sir, what is the angle between, listen to me, what is the angle between P and E? What is the angle between P and E? Sir, that is 0. And see, we say, sir, tau is equal to PE sine theta. Mention here where theta is the angle between P and E. Theta is the angle between P and E. Now, in this particular case, sir, theta is equal to 0 degrees. This is P and E. Now, over here, boys and girls, can I say torque will be nothing but PE sine of theta, sine of 0. Sine 0 is 0. So torque in this case will be 0. It is logical also. If you place the dipole over here, something like this, on the positive charge, force will be in the forward direction. On the negative charge, force will be in the backward direction. These two forces are pulling this rod, pulling this dipole. Do you think it will rotate the dipole? No. If you apply the force something like this, then the dipole will rotate. But by pulling, dipole will not rotate. That's why torque comes out to be 0. Okay. We have this concept. This is the last concept from this one and we are done. Then we'll start the next chapter and I'll give you the break once we are done with this one. No, capacitors will not finish in this one because then it will take more than 12-13 hours. We'll take the capacitors next session. In this one, we'll be completing the potential. Potential part will be completing. Okay, now see. Potential energy stored in a dipole. I told you, sir, torque on an electric dipole. Whenever you place a dipole inside an electric field, it creates the torque. Torque is being produced. Now see, over here. Let me just give you a simple example. Let's suppose you have, this is the surface of Earth. This is the Earth's surface. And on this Earth's surface, you have a block which is placed. And if you take this block from this point to this point, if you take this block from this point to this point, okay? Now you have displaced it with the height h. Sir, on the surface, everybody knows that we say potential energy is 0. So once we lift it to the height h, we say potential energy is mgh. Just the simple example, 9th class example. As of now, you remember this one only. Okay. Sir, we lifted it at height h, means potential energy is being stored. My question to you is, how does this potential energy come over here in this block? You say, sir, when I lifted this block, the downward force was gravitational force, gravity. And upward force, I applied the external force. So by applying the external force over here, sir, we lifted the block. So work is being stored, work is being done over here. Now I say, so my work done. See, I have lifted the block from this point to this point up to height h. At this surface, its energy was 0. At this height h, its energy is mgh. Then only I lifted the block, then only energy is being stored. If I would have not lifted the block from this point to this point, no energy would have stored in this one. So can I say my work done? I used my energy in lifting the block. So my work done will be stored as potential energy of the block. Yes, sir. I can say. So my work done in lifting the block, is stored as work done. My work, is stored as potential energy of the block. Is stored as potential energy of the block. My work done in lifting the block is stored as potential energy of the block. Sir, at ground surface, energy was 0. Over here, it is mgh. Why it is being changed? Sir, we say by doing the work done, you did the work done. Due to that work done, potential energy changed. W is equal to delta U. Sir, initially, potential energy was 0. Over here, it is mgh. Means you have changed the potential energy from 0 to mgh. From 0 to mgh. So you change W is equal to mgh. Now, this is the normal scenario. Let me show you if I have an electric field. If I have an electric field, listen to me very carefully. And inside this electric field, we have a dipole. This is a dipole. We show it with the dipole moment P. Okay. This is the negative charge over here. This is a positive charge over here. This is a dipole. Now I'm saying that you angularly displace or you rotate this dipole. You are saying, sir, I'll rotate this dipole by this much of amount, that is theta. My question to you is the dipole rotating by itself or some external agent, that is me, I am rotating the dipole? You will say, sir, you are rotating the dipole. It is not possible for the dipole to rotate by itself. You are rotating the dipole. You are doing the work. You are using your own energy. Like over here, I lifted the block from this point to this point. I did the work. Same is the case over here. I rotated the dipole from this position to this position. So I did the work. Will my work be wasted over here? You say, sir, no. Your work done will be stored as the potential energy of the dipole. Over here, my work done was stored as potential energy of the block. I'll write my work done. See, my work done in lifting the block. Over here, my work done in rotating the dipole. In rotating my work done in rotating the dipole will be stored as potential energy, of the dipole. Will be stored as potential energy of the dipole. Will be stored as potential energy of the dipole. My work done in rotating the dipole will be stored as potential energy of the dipole. Okay. Now, boys and girls, so over here also I can write W is equal to change in potential energy delta U. Now, sir, you lifted the block and the potential energy has been changed. So finally, what is the energy? U is equal to mgh. Now, sir, same is the question over here. If you rotate the dipole, potential energy will be stored in the dipole. How much? What is the value? Here it is mgh. How much it is here? That potential energy will be, I'll just write that potential energy will be, we say U is equal to minus PE cos of theta. What is P? P is the dipole moment. What is E? E is the electric field in which you have placed it. And what is the P is dipole moment. Dipole moment. E is electric field and theta is the angle between P and E. This is what I was trying to say over here. In lifting the block, the energy is stored mgh. In rotating the dipole, the energy stored is minus PE cos of theta. Or we call this minus PE cos of theta as U is equal to minus P dot E also. P dot E also. I hope you got it. Minus P dot E also. Hey, let me know in the live chat. You are understanding each and everything. Or my energy is getting wasted over here. Or my energy is getting stored as a potential energy of your brain. Let me know. Is it clear, each and everyone, with the fire symbols? That's cool. Clear. That's cool. Yes, energy is stored in the form of knowledge to us. Very good. Great. I'll give you the break. Let me basically finish this one first. Okay. Now see. If I say in this particular case, sir, if theta is equal to 90 degrees, listen to me very carefully. Sir, if I say this is the electric field, and in this electric field, the dipole is placed something like this. Can you tell me what is the angle between dipole moment P and electric field E? You say, sir, theta is equal to 90 degrees over here. This is the dipole moment, this is the electric field. And what will be the value of potential energy over here? You say, sir, U is equal to, that is minus PE cos of theta. You say, sir, U is equal to minus PE. Cos of theta is 90. So, sir, cos of 90. Sir, cos 90 is 0. So, U is equal to minus PE into 0. So, this will be 0. Means, sir, at 90 degrees, potential energy is 0. Yes. You have to accept it because This is from the derivation we got this expression over here, this minus PE cos theta. So we have to take it and we assume that at theta is equal to 90 degree, potential energy is 0. And if I say theta is equal to 0 degrees, if I say theta is equal to 0 degrees, means this is the electric field and this is the dipole moment placed something like this. Angle between dipole moment and electric field, both are in the same direction, means theta is equal to 0. What is the potential energy? U is equal to minus PE cos of 0 minus PE cos theta. So you say, sir, U E cos 0 is 1 minus P into E. This is the potential energy. And when theta is equal to 180 degrees, this is the dipole moment and electric field is in the forward direction. Theta is 180 degrees. In that case, we say U is equal to, that is minus PE cos of, we say, sir, 180. Cos 180 is minus 1, I guess. This is minus PE and this is minus 1. U is equal to minus into minus, it becomes plus. So this is plus PE. And this is what we call the maximum potential energy. Maximum potential energy. So means when theta is equal to 180 degrees, in that case, potential energy is maximum. And that is minus PE. That is plus PE. Okay. I hope you got it. Now, there are few questions which I want exactly you guys to do. I just need to know the answer of these questions in the live chat. Let's suppose we have, are you able to see this question? Are you able to see this question? No, let me just show you. Let me just show you. We have, I'll make the figure over here. We have an electric field. This is the electric field. And inside this electric field, we have placed a dipole, which is something like this. This is a dipole P. And then we are rotating this dipole by 180 degrees. Okay, P. This is initially angle between electric field and P is 0. And this is finally. Sir, if we are rotating the dipole from 0 degree to 180 degrees, means we have to do some sort of work. And I am asking you to find that work done by external agent in rotating the dipole from initial to final from 0 to 180 degrees. Find the work done from okay. What is the value? What is the value in this case? What is the value in this case? Okay. What is the work done in rotating? See, there is an electric field. In this, you have placed the dipole something like this at 0 degrees. Now you are rotating it by 180 degrees. It will not rotate by itself. You have to rotate it. External agent has to rotate it. So external agent has to do the work done. How much work done he has to do so that it will rotate from 0 to 180. So we say, as, sir, you told us the formula. Sir, that formula over here is work done is equal to change in potential energy. By lifting the block, you are changing the potential energy. By rotating the dipole, you are changing the potential energy. So W is equal to change in potential energy. We have to use this formula only. As we know, W is equal to delta U. W is equal to change in potential energy. Sir, what is this change in potential energy? Change in potential energy means final potential energy minus initial potential energy. So we say W is equal to, what is final potential energy? Listen to me very carefully. Sir, final potential energy. Sir, potential energy. What is the formula for potential energy? Minus PE cos theta. So we say minus, we say PE cos of. Finally, sir, finally, this is the situation when theta is equal to 180 degrees, minus PE cos of 180, then minus this formula minus, then initial potential energy. Initially, theta is equal to 0 degrees. Then you have minus PE cos of 0 degrees. So we can say this is minus PE cos 180 is minus 1, minus into minus. So this is PE cos 180 is minus 1, minus, then you have minus cos 0 is 1. This is PE. I hope you are able to understand these questions. Sir, minus into minus becomes plus, so this is PE. Minus into minus becomes plus, this is PE. PE plus PE becomes 2 times of PE. How many of you got the 2 times of PE? Very, very good. Absolutely good. Yes, it is 2 times of PE. Okay. Now solve this, solve this. Find work done in rotating it from theta 1 to theta 2. Over here, this is the initial position. This is the final position. Are you able to see this? Yes, 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 yes. Find work done in rotating from initial position to final position. Are you able to see this? Tell me. This is in the electric field. This is the electric field. How much is this? See, over here, cool. Now see, sir, initially the dipole is something like this. I'll make the diagram over here. This is the electric field E. Okay. Initially, this is the dipole. Okay. And finally, this is the dipole. Initially, it is making an angle. It is making an angle. This is 60 degrees. This is also 60 degrees. This is initial situation and this is final situation. Now see, sir, this is initially, this is finally. And clearly, sir, this is the dipole moment P. This is the electric field. So this is the theta 1. Over here, this is theta 1. Sir, what is theta 2? This is not the theta 2. Keep that thing in your mind. See, total angle is how much? It is like this. It is like, I'll show you over here. It is like this. Sir, from this point to this point, angle is 180 degrees. And this much is 60 degrees. 180 minus 60, you will get this angle. That is 120 degrees. So, from 60 degree to 120 degree, the dipole has rotated here from 60 degree to 120 degree. So, in this particular case, I'll just write here, the dipole has rotated from, we say, 60 degree to 120 degree. From 60 degree to 120 degree. Okay. Dipole has rotated from 60 to 120 degree. Now, because we measure the angle between P and E, this is P and this is E. Okay. Now, in this particular case, work done is equal to change in potential energy. Work done is equal to U final minus U initial. Work done is equal to U final. Finally, dipole is at 120 degrees. So this is minus PE cos of 120, then minus this formula minus, and you have minus PE cos of 60 degrees. Now we say minus PE cos of 120 is minus 1 by 2 minus, and then you have minus PE cos of 60 is 1 by 2. Keep that thing in your mind. Instead of cos 120, I write minus 1 by 2. Instead of cos 60, I write 1 by 2. Now see, sir, minus into minus becomes plus. So this is PE divided by 2 minus, and minus into minus again becomes plus. So this will be PE divided by 2. PE divided by 2 plus PE divided by 2. This becomes PE. So how many of you got P? Yes, yes, yes. Great. I can see in the live chat people writing PE. Okay. How many of you? We are done with the first chapter. Okay. Now we have its electric potential part. That is itself the second chapter. That is itself the second chapter. Sir, I have never seen the lecture like you. Teaching physics in this way is superb and I'm getting it very well. Thank you. Means a lot. Means a lot. I want all of you to like this session. Okay. So now We have the next chapter. Till then, we'll take a break first. We'll take a break. Break. Break till what is the time? We'll take we'll take break 12:20. Okay, break till 12:20. Okay, we'll take break till 12:20 and then we have some slides and we'll finish this very soon. Okay, it will not take much time. It will not take much time. That's for sure. We are done with the maximum part. We'll take the break till 12:20 and then we have this. Okay, let's take a break till 12:20. Not 12:20, we'll take it till 12:15. Okay, let's take a break till 12:15 p.m. Okay, that's 20 minutes break. Okay, 12:15. Okay, 12:15 I'm taking. Okay, great. Everybody of you like this? Like this session as soon as All right, people, we are back. We are back to basics. We are back to the game of NEET. Okay, so let's start the session. Let's start the session. Am I audible and visible properly? Let me know in the live chat. The one who have not liked the session yet, to join it, like it as soon as possible. Okay, let's start the session. Cool. Now, basically, let's talk about the most important topic, that is nothing but potential energy, electrostatic potential energy. In gravitation, you might have studied gravitational potential energy. Here you will be studying the electrostatic potential energy. What does this potential energy concept says? Listen to me very carefully. Let's suppose I say over here, this is the Earth surface. This is the surface of Earth, okay? And on the surface of Earth, I am placing a block. Okay? Same example I'll take once again. And I'm lifting this block from this point to this point. I'm lifting the block from this point to this point. Okay? My question to you is, sir, at this particular point of time, we say potential energy is zero. At this surface, we say energy is zero, potential energy is zero. And when we lifted it to some height, we say potential energy is mgh. We say potential energy is mgh. My question to you is, sir, how does this potential energy come in this block? You say, sir, by doing the work done. Sir, you lifted the block from the surface till the height h, so you did the work done. That work done will not be wasted. That work done will be stored in the form of potential energy. W is equal to delta U, which I told you in this slide. I'll tell you. My work done in lifting the block is stored as potential energy of the block. W is equal to delta U. Same is the case over here. My work done in lifting the block will be stored as the potential energy of the block. Okay, cool. Now, let's suppose I have a charge plus Q1 over here, and I have another charge plus Q2 over here. And this charge is at infinity. It is at very large distance, very far a distance. Okay, fine. Now, I am asking you the simple question. That is nothing but, I'm saying that bring this charge from infinity, nearer to this charge. You say, sir, while I am bringing this charge from infinity nearer to this charge plus Q1, I'll have to do the work done. See, over here in the downward direction, gravitational force was acting. In the upward direction, you applied the external force because you did the work. Now, over here, we can say, sir, once you were taking this charge from infinity towards the positive charge Q1, you were doing some sort of work here. This plus Q1 was repelling this plus Q2 with electrostatic force. We know, sir, positive charge repels positive charge. Now, sir, if this plus Q1 is repelling this plus Q2, in order to bring it close to this Q1, we'll have to apply the external force opposite to this one. This is the external. So by applying the external force, you are bringing the charge from infinity to this point. Now, when you are applying the external force, means you are applying the work. You are doing the work done. Will the work done be stored? You say, sir, no, the work done will not be stored. But that will be stored as potential energy in case of the charge. I hope It is clear. So we say my work done in bringing the charge from infinity, let's suppose it is at point P, infinity to, or we say r distance to r distance, is stored as potential energy between the charges. Yes, sir, it will be stored as potential energy between the charges. So means work done, by this work done, potential energy has been changed. W is equal to delta U. This formula is applicable over here also. This formula is applicable over here also. See, you were lifting the block from this surface to this height, so you were doing the work. Because of that work, potential energy is stored. And over here also, you are taking the charge from infinity to this point P. You are again doing the work. Now over here, the work will be stored in the form of potential energy between the charge. Over here, the work will be stored in the form of potential energy of the block. I hope this is clear to you. Now, my question to you, my dear friends, is how much will be that potential energy? How much will be that potential energy? I write that potential energy will be. See, in this case, you say, sir, potential energy is mgh. In this case, we say potential energy will be U is equal to, that is K, this is Q1, this is Q2 divided by, we say, R. If you finally have taken this from infinity to this point, so means potential energy at R distance is nothing but K Q1 Q2 by R. And if we take initially potential energy as at infinity is 0, and potential energy at R distance while you taking this from infinity to R, this is the potential energy. Again, I am saying, sir, I am bringing the block from infinity to point P. I am doing the work done. That work done will be stored as potential energy. How much will be that potential energy? That is nothing but U is equal to K Q1 Q2 by R. As simple as that. Just remember it directly. Where does this potential energy come from? My work done by external agent. Okay, fine. Yes, absolutely cool. Now, the question is, I'll tell you one more point. We say potential energy exists between the pair of charges. This potential energy exists between the pair of charges. If we have Q1 charge, if we have Q2 charge, then only we say the potential energy between them is K Q1 Q2 by R. You cannot say, sir, if we have one charge only, potential energy will be there. No. Why? Because if you are bringing the charge from infinity, you are doing the work done. Let me just show you over here. If for example, you have the charge Q1, another charge is at infinity. You are bringing this charge Q1 nearer to this charge. See, this charge is repelling this charge with a force electrostatic. You are applying the force that is external. If I say, for example, only one charge is present, no charge is present over here, will there be any electrostatic force on this one? No. If there is no electrostatic force on this one, do we have to apply external force on this one? No. Just push it something like this, then it will keep on moving by itself. So we'll not have to do any sort of work in that case. If we don't have to do any sort of work, so means no work is to be done, means no potential energy will be stored, no potential energy will be there. That's why for single charge potential energy is not defined, but there has to be two charges. Okay, I hope you got it. And if you check the definition of the potential energy, if you see in any book, in every book it is mentioned that it is defined as the amount of work done in bringing the charge from infinity to that point. It is defined as the amount of work done in bringing the charge from infinity to that point. the amount of work done you do in bringing this charge from infinity is stored as potential energy, is defined as potential energy. It is one and the same. You got it? I hope this is crystal and clear. I need to know in the live chat with the fire symbols. If not, I'll explain it once again. Let me know in the live chat. Is potential energy concept clear? Is it clear? Guys, give me some signal, yes or no. That's it. I can move forward. Great. Now. So this potential energy is how much? U is equal to K Q1 Q2 by R. Now, listen to me very carefully. If I say potential energy exists between the pair of charges. I have plus Q charge over here. I have plus Q charge over here. I have plus Q charge over here. Distance between them is L. Sir, whenever there is a pair of charge, there is potential energy. So, sir, okay. Am I audible? Let me know. Sir, this is the first pair that I can see over here. So between these two, potential energy will be there. This is the second pair between these two, potential energy will be there. This is the third pair between these two, potential energy will be there. I hope this is clear. So potential energy exists between the pair of charges. We say in this case, we are supposed to find net potential energy of the system. Sir, between the two charges, potential energy is K, Q1, Q2 by R. In this case, potential energy between this charge and this charge, it will be K, Q1 is Q, Q2 is Q divided by R. Then plus, between this charge and this charge, it will be K, this is Q divided by R, plus between this charge and this charge, it will be, sir, K, this is Q divided by R. So can I say this will be KQ square by R plus KQ square by R, KQ square by R, that is 3KQ square by R. This is net potential energy of the system. This is net potential energy of the system. Is it clear? Now tell me, what is the net potential energy of this system? What is the net potential energy of this system? We have one charge over here, another over here, another over here, another over here. How much is this potential energy of this system? You say, sir, in this case, we say net potential energy will be. Don't get confused. Whatever I am saying, just remember it and move forward. Sir, in this case, net potential energy will be, sir, between these two charges, potential energy exists between the pair of charges. So over here, potential energy is between these two charges, between these two charges, between these two charges, between these two charges. So we say it is, if I say between these two charges, it is K, Q, and this Q divided by distance between them is L. That is L. KQ by L. KQ by L. Now, this one is one pair. Between these two is next pair. Between these two is next pair. Between these two is next pair. Total number of pairs placed at the corners are 4. So we say 4 times of KQ square by L. Then plus, sir, this is also one pair. These two diagonal pairs, another pair. So diagonally there are 2 pairs. Let's find the potential energy between this one and this one. You say, sir, K, this charge is Q, this charge is Q, that is Q square divided by distance between them is under root of 2L. Now this is between these two. Between these two also it is root 2L. So that is 2 times. So diagonally there are 2 pairs and at the corners, at the sides, there are 4 pairs. So net potential energy in this case is nothing but 4KQ square by L plus 2 times of KQ square by under root 2L. You can take some common also over here. and then you can simplify it more. Okay, now there is basically a formula by checking the number of pairs, that is n into n minus 1 by 2. This is how do you find the number of pairs. The formula in order to find the number of pairs, n into n minus 1 by 2. How many n is the number of charges? 1, 2, 3, 4. That is 4. 4 into 4 minus 1, 4 into 3 is 12 by 2 is 6. 4 plus 2 is 6. Number of pairs, how do you check? In this case, how many number of pairs are there? 4 plus 2, 6. Let's see with the formula. N is how many charges? 1, 2, 3, 4. So this is 4 into 4 minus 1 by 2. 4 minus 1 is 3. 3, 4 is 12. So this is 12 by 2, which is 6. So in this case, 6 pairs. 4 are the side pairs, 2 are the diagonal pairs. Done. Is it clear? With the fire symbols, is it clear? Is it clear, guys? Now in this particular case, you are supposed to tell me, we are bringing the charges, choose the, okay. Now, okay, cool. Now see, in this case, what we are doing is that we have the charge Q, we have another charge Q, we have another charge Q. Now we are bringing the 3 charges close to each other. We are shrinking this triangle. So initially they were at a distance A, Afterwards, once we took them close to each other, now the distance becomes A by 2. This is also A by 2. This is also A by 2. So sir, from A distance to A by 2, we have to do some work. From bringing the charges from A to A by 2 distance, work is to be done. Here. So we have to find that work done. How much is the amount of work done? Sir, we know in order to find the work done, we know work done is nothing but change in potential energy. Whenever they ask you to find the work done, just apply one single formula, that is change in potential energy. And I'll just tell you over here, just remember it directly. We say work done by external agent. That is me over here, who is doing the external work, is equal to, that is nothing but is equal to delta U, change in potential energy. And if somebody asks you to find the work done by electrostatic force, electrostatic force, that is equal to negative of change in potential energy. Just remember this directly. If from, see over here, it is mentioning find work done by external agent. So you are finding the work done by external agent, you will say W is equal to delta U, change in potential, in positive. But if the questioner would have asked find the work done by external agent by the electrostatic force, then negative of change in potential energy. As simple as that. Over here, let's find the work done. Sir, this work done is nothing but, we say U final minus U initial. Sir, this work done is nothing but U final. Sir, finally, this is the final situation. Finally, the triangle has shrunk. Initially, this is initially. Sir, if we talk about finally, what is the final potential energy? Sir, potential energy of this system. Now see, how many pairs are there? 1, 2, 3. So we say 3 times, we say K, Q, that is Q square divided by, sir, this is A by 2. This is the potential energy of this system finally. And what is the potential energy initially? Sir, that is minus, how many pairs are here? 1, 2, 3. 3 pairs are here initially. So we say 3 times of K, this Q and this Q, that is Q square divided by A. Can I say it something like this? Further, if we simplify it, sir, we can write W is equal to, see, if you take this 2 in the numerator, 3 2s is 6, 6kq square by A, 6kq square divided by A minus 3kq square by A. 6 minus 3 is 3. So work will be nothing but 3kq square divided by A. Done and dusted. Let's move on to the next question. Okay, very important question from NEET 2022. NEET 2022. Come on, let me know. In this particular case, the questioner is saying that over here, the questioner is saying that 6 charges plus q minus q plus q minus q plus q minus q. These are the charges placed at the corners, okay, of a hexagon, are fixed at a corners of hexagon of side A, of side D. The work done in bringing the charge q naught from center to, a charge to the center of the hexagon from infinity. Okay. We have got a hexagon over here. Let me just make the diagram. We have got a hexagon over here. This is the hexagon. On this corner, plus q charge is placed, minus q charge is placed on this corner. Plus q is on this corner, minus q is on this corner, plus q is on this corner, minus q is on this corner. The questioner says that we have a charge q naught which is placed at infinity, very large distance, and we have to bring it from infinity to the center. From infinity to the center, we have to bring it from infinity to center. In order to bring it from infinity to center, we have to do the work done. Now, in this case, we are supposed to find how much is the work done in bringing the charge from infinity to center. How much I have to do the work done in taking this charge from infinity to center. Sir, we know work done is nothing but that is change in potential energy. Whenever you have to find the work done, you apply the formula change in potential energy. So we say, sir, this work done is nothing but U final minus U initial. Sir, could you please tell me what is initial potential energy? Initially, this charge was at infinity, so Ui is equal to 0. Because I have told you, at infinity, we assume the potential energy as 0. We assume the potential energy as 0 at infinity. Once you are taking it from infinity to the center, so Ui is equal to 0. And what is the value of, sir, UF? Listen to me very carefully. We say this W is equal to UF, final potential energy. See, sir, final potential energy will be, how many pairs are exactly over here? Sir, between this is one pair, between this is another 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 pair. Total number of 6 pairs. Let me write the potential energy of all 6 pairs over here. So we say work done will be, listen to me very carefully, final potential energy I am saying, between these two, that is K, this Q naught, this Q naught divided by distance between them is D, that is D. Then between this negative charge and this positive charge, we say this is minus. First, this charge is minus. Right? The sign of the charge also, along with the sign. We say K, this is Q, this is Q naught, and that is this Q divided by D. This potential energy, this potential energy. Now write between this. You say, sir, again plus, that is K, this Q naught, this Q divided by R, then minus between this and this, K, Q naught, this Q divided by R, then between this and this, plus K, q naught by r. Then between this and this, minus k q naught divided by r. And this is the final potential energy. All of this is basically final potential energy. Finally, it is at here. This is u final. All of this is the value of u final. Minus u initial. Sir, initial potential energy is how much? 0. You tell me one thing. Sir, this will get cancelled with this one because they are similar. This is positive, this is negative. Positive, negative, positive, negative. So 0 minus 0. Final answer would be 0. So answer over here is 0. Is there anyone who can tell me the answer of this one? Answer is 0. Let's move on. See, it is definitely final potential energy. It is definitely final potential energy minus initial potential energy. Okay. Finally, final potential energy minus initial potential. 0. Answer cannot be D. How answer can be D? I can give you another logic also. This distance in case of hexagon is exactly same. This distance is same. This distance is equal to this distance. See, without solving the question, I'll tell you the work done will be 0. Forget about this solution. If you have got any confusion in the solution, forget about the solution. I'll tell you. See, we have this hexagon. We have this hexagon. One charge is plus q, minus q, plus q, minus q, plus q, minus q. You have this at infinity. So you have to bring it from infinity to over here, center. You are supposed to say how much work you are supposed to do. Cool. See, while I am taking this charge from infinity to center, I have to do the work done. Work is only being done in that case if electrostatic force is applied on this one. Then I apply the external force opposite to the direction of electrostatic force. I told you, if there is no electrostatic force, no external force I have to apply, means no work has to be done. Now see. If I say, sir, there are negative charge, 3 negative charge. So 3 negative charge will, forget about this, 3 negative charges, this one. 3 negative charges will attract this positive charge towards itself with force F. Okay, this is electrostatic force towards them. Now this positive charge, and this positive charge, 3 positive charges will repel this with the same force F, because 3 are the positive charge, 3 are negative charge. This is also electrostatic force. This electrostatic force will get cancelled. So electrostatic force net will be 0. So no electrostatic is acting on this, or net electrostatic force is acting on this is 0. If electrostatic force net is acting on this 0, do we have to apply any sort of external force in that case? No. If we don't have to apply any sort of work in that, if we don't have to apply any sort of force in that case, means we are doing 0 work. So we say work done in that case will be 0. That's why answer is 0. Now, how many of you got this answer? How many of you got this answer, which I told you? I need to know in the live chat. Okay. This is D. Sorry. This is D. All of these are D. It's one and the same thing. This. Okay. I got it. Cool. Let's move on to the next question. Okay, this was also the previous year. This is also the previous year question. Let me show you over here. See, In the electric field of the charge Q, another charge is carried from A to B. We have, okay, in this particular case, we have a charge at center. We have a charge at center. And we have another charge Q. We are taking it from point A to point B. From point A to point B. This is a here, whatever you call it. Then you take it from point A to point C. This is point B. See, I have a charge Q. One charge is at center, another charge Q is over here. You are taking this charge from point A to point B through this path. Then again, you are taking this charge Q from point A to point C through this path, And then you are taking this from point A to point D through this path. And then you are taking it from point A to point E through this path. Now, sir, I am taking now see, sir, I am taking this charge through path A, then through this path 2, path 3, path 4. My question to you is, sir, in this particular case, you are supposed to tell me, work done through all the paths will be, sir, while you are taking this charge from this point to this point through this path, some work you have to do. While you are taking this charge from this path to this path, some work you have to do. While taking this charge from this point to this point, some work you have to do. While taking this charge from this point to this point, some work you have to do. The options are minimum work you have to do along path AB. You have to do less work along path AB. Minimum work along path AD. You have to do less work along path AD. Minimum work along path AE. Along this you have to do 0 along each path. Which option is correct over here? Sir, whenever we have to find the work, we say W is equal to change in potential energy. Okay. Sir, over here, W is equal to U final minus U initial. Let's find the work done through this path. Sir, this one charge is at here plus Q. Another charge is at here. Now, this is the radius. From center to this surface, this is called the radius. Okay. Now, sir, in this case, could you please tell me when initially the charge was over here, what is the potential energy between these two? This is the initial point A, when the charge was at A. Sir, potential energy is K. This finally the charge is over here. This distance is also R, radius. Initially charge is over here, finally charge is over here. When charge is at final position, what is the potential energy between this charge and this charge? You say, sir, that is U final. That is K. This charge is Q. This charge is Q divided by distance between them is R. K Q1 Q2 by R minus initially, sir, initially the charge was over here. And finally, this charge is over here and this charge is over here. Between these two, this Q and this Q, what is the potential energy? K, Q divided by R. This will cancel. This is 0. And my dear friends, if you check the potential work done along this path, that will also come out to be 0. If you check work done along this path, that will also come out to be 0. How? U final minus U initial. So work done along each path is 0. Yes, option 4 is correct. 0 along, yes, exactly, yes, 100%, because equipotential. 100%, correct logic. Cool. Now we have electric potential. Now, let me just tell you what the electric potential is all about. Listen to me very carefully. Now see, I'll make you understand this electric potential. Sir, What is this electric potential? What does it mean? Let me just tell you what the electric potential is all. Let's suppose you have a charge Q over here. Okay, you have a charge Q over here. And you have another charge plus Q over here. This is another charge plus Q over here. And this charge is placed at infinity. And I am asking you to bring this charge from infinity to this point P. This is point P. Okay, at R distance. If you bring this charge from point P, if you bring this charge from infinity to the point P at R distance, you will have to do some work. Okay, so I say, sir, on bringing the charge Q from infinity, I have to do some work. And we know, sir, that work will be stored as potential energy. I know that work will be stored as potential energy. And if you ask me, sir, how much is that potential energy? You say, sir, that potential energy we already discussed, that is U is equal to K, Q1 is Q, Q2 is this Q, divided by distance between them is R. This is the potential energy we know. Now, what if I tell you? Is it clear to everyone? Is it lagging or is it clear? Is it clear to everyone or is it lagging? Okay, great. Now see, if I say this is, we are bringing it from infinity, this will be the energy, this work done will be stored as the energy, potential energy, that is K, capital Q, small u, Q divided by R. Okay. Now, if I say, if Q is equal to 1 Coulomb charge, or we say unit positive charge. Sir, unit positive charge means 1 Coulomb charge. This charge which you are bringing from infinity is 1 Coulomb. Its value is 1 Coulomb. You are bringing this charge from infinity to this point, its value is 1. In that case, could you please tell me the value of this potential energy? You say, sir, U is equal to, that is K, this Q, instead of this Q, I'll write 1 divided by, we say R. Sir, this comes out to be U is equal to K, this is Q divided by R. I'll give you the crystal clear feel of electric potential. Okay, a lot of people feel this is tough. Now I will tell you how do we exactly get the feel of this one. So it becomes U is equal to K, Q divided by R. Sir, now can I say this is the potential energy. This is the potential energy of 1 Coulomb charge. Yes, sir. This is the potential energy of 1 Coulomb charge. Why? Because you are bringing the charge Q from infinity. What is Q? Q is 1 Coulomb. So you are bringing the charge 1 Coulomb from infinity. So the amount of work done you did in bringing 1 Coulomb from infinity, that work done only is stored as potential energy. How much is that potential energy? This much, sir. This much, sir, KQ by R. And this is what we call the potential energy of 1 Coulomb charge. So, sir, we say U is equal to K capital Q divided by R. This is what? Potential energy of 1 Coulomb charge. Potential energy of 1 Coulomb charge. And this is what we call the potential and is called potential. Sir, from this definition, you are trying to say is that potential is nothing but potential energy. From this, you can say that, sir, potential is nothing but potential energy. Yes, Potential is the potential energy of 1 Coulomb charge. Potential is the potential energy of 1 Coulomb charge. That's why we say potential. Potential is nothing but potential energy per unit charge. Definition of potential is nothing but potential energy per unit charge. Unit charge, the amount of energy, potential energy a unit charge has is nothing but potential. I hope this is clear. So we say, we represent potential with V. We say potential energy per unit charge. U is equal to V by Q. Now we can write, sir, V is equal to, what is the value of U? This is K, capital Q, small q divided by R, and then divided by, you have this Q will get cancelled. This is KQ divided by R. So sir, what is potential? Potential is nothing but potential energy, but of 1 Coulomb charge, Let me just show you over here. Guys, if you find the, if you see the definition of this electric potential from the books, the definition will be, it is defined as the amount of work done. It is defined as the amount of work done in bringing the unit positive charge from infinity to that point. Sir, what is the difference between the definition of potential energy and potential? I'll tell you. Sir, the difference is nothing but, over here, when it comes to the potential energy, it is defined as the amount of work done in bringing the charge from infinity to that point. Charge can be anything. But when it comes to the potential, it is defined as the amount of work done in bringing 1 Coulomb charge, unit charge, from infinity to that point. So the amount of work we did in bringing that charge will be stored as potential energy, and that potential energy is nothing but potential. Give me the thumbs ups if you got the feel of this one. Come on, everyone, let me know. I hope this is crystal and clear. We say potential energy is nothing but potential energy per unit charge. V is equal to U by Q. Come on, in the live chat. Is it clear, guys? Potential is nothing but potential energy only, but for 1 Coulomb charge. When you bring 1 Coulomb charge, means you are defining potential. At infinity, yes, we assume 0. At infinity, we assume 0. Okay, great. Perfectly understood. Yes, capacitors will be done in the next session. Great. Let's move on. Okay. We have this question over here. Now, from now onwards, remember one thing. That is nothing but, so you got it. So now let's suppose I have, remember one thing. If I have Q1, if I have Q2, distance between them is R. And if I ask you how much is the potential energy between these two, you say, sir, U is equal to K, this Q1, this Q2 divided by R. This is the potential energy between the two. Now, if I have a charge Q at R distance, it will have potential. That potential is nothing but, we say K, this Q, K this Q divided by R. KQ by R. We say KQ by R. This is how we define the potential of a single charge, KQ by R. Now, the question over here is, we have a charge plus Q, we have a charge minus Q, and you guys are supposed to tell me the net potential at the center and net electric field at the center. Now see, sir, because of this charge, first let's find the electric field. Let's find the electric field at the center at this R distance. Sir, because of this plus Q charge, at this point, electric field would be something like this away from the charge. Sir, because of this one, the electric field at this point would be something like this towards the charge. Sir, we say in this case, E net is nothing but this electric field plus this electric field, that is 2 times of electric field. And that will be 2 times of, how much is the electric field because of a charge? Sir, because of this charge at this point, electric field will be K, this charge Q divided by this distance R square. So this is nothing but 2KQ by R square. This will be the electric field. Now, if I ask you to tell me the net potential at the center, see, how do you find the net potential? Potential is a scalar quantity. Electric field is a vector quantity. Electric field has a direction. Potential does not have the direction. Keep that thing in your mind. Sir, this is plus Q. Because of the plus Q at R distance, potential is V is equal to, I just told you how to find the potential because of a charge, KQ by R. Electric field is KQ by R square. So it is K, this charge is Q divided by this distance is R. Now, this is the potential because of this. Now, if I ask you to tell me potential because of this, you say minus, you say, sir, K, this charge is Q divided by R. So net potential is nothing but 0. Net potential is nothing but 0. Net potential is nothing but 0. I hope you got it. I hope you got it. There is an important concept that I need to tell you over here. That is potential decreases. Potential decreases in the direction of electric field. Remember it, as simple as that. Don't use your brain. We don't have the time to explain the entire thing over here. Just potential decreases in the direction of electric field. So if I just tell you in this particular case, let's suppose this is the direction of electric field. And if I move along the electric field, the potential will decrease. So if I say this is the point A over here, if I say this is the point B over here, we can clearly see in this particular case, sir, potential at A is greater than potential at B. Why? Because you only said, sir, potential decreases in the direction. Potential decreases in the direction of electric field. So at A, potential will be more. If you move along the electric field, it will keep on decreasing. So at B, it will be less. I hope this is clear. I hope this is clear. I hope this is clear. Yes, sir. Now, let's come over here. This is the first question. If we have a positive charge, if we move, we know, sir, because of a positive charge, electric field is away from the charge. Electric field is away. If I just say this is A point, this is B point, we are moving along the direction of electric field. Now, in this particular case, sir, we can clearly see that potential at A is greater than potential at B. Why? Because potential decreases in the direction of electric field. And if I ask you electric field, sir, if this is a charge, near to the charge, electric field is more. Away from the charge, electric field is less. Yes, great. Okay. Wasim sir is trying to clear all your doubts in the chat. That's great. So we say if we have a charge over here, near to this charge, we say electric field is more, and away from the charge, electric field will be less. Everybody knows that. As we keep on moving away from the charge, electric field keeps on decreasing. Now see, at this point, it is nearer to the charge, electric field is more, At this point, it is away from the charge, electric field is less. That's why electric field at A is greater than electric field at B. Let's come on to this one. We have a negative charge. In case of negative charge, electric field is towards the line, towards the charge. Now, sir, at point A, at point B, if we move along the direction of electric field, potential decreases. So, sir, at point B, potential at B is greater than potential at A because we are moving along the direction of electric. So, potential at A is less than potential at B. Clear? But when it comes to the electric field at A will be more. Why? Because near to the charge, electric field will be more. Even if it is a positive charge or it is a negative charge, in both the cases, electric field near to the charge will be more. That's why. That's why we say electric field at A is greater than electric field at B. Now in this case, sir, potential at A is greater than potential at B because along the direction potential decrease. And over here, we say electric field at A is greater than B because the lines are diverging over here. I hope you know this one also. If the lines are close to each other, we say electric field is more. Lines are diverging, electric field is decreasing. Let's move on to this one. Okay, this was the question which was asked in NEET 2013. A, B, C are the 3 points in the uniform electric field. The electric potential is A, B, C, D. Maximum at B, maximum at A, maximum at C. Sir, potential decreases along the direction of electric field. So at this particular point, electric field will potential will be more. VB is more. Why? Because if you move along the direction of electric field, potential will decrease. Same at all the points. No, no, no. Okay. Potential at B is maximum. Okay. Find the net electric field and net potential at the center. Okay. Let's find the net electric field. Sir, when it comes to the electric field, because of this charge at a center, electric field will be away from the charge. Why? Because of the positive charge, electric field is away. And because of this positive charge, electric field at this point will be away from the center. Now, because of this positive charge, electric field is away from the center. Because of this positive charge, electric field is away from the center. So because of all the positive charges, electric field are away. This will cancel with this one. This will cancel with this one. So net electric field at center is 0. When it comes to the potential will be, sir, V net. Potential is a scalar quantity. It does not have the direction. It will not cancel out. So we say in this particular case, sir, potential at center will be potential because of this, potential because of this, potential because of this, potential because of this. And if this distance is L, I have told you this distance will be L by root 2. So potential because of this at center is K Q by R. R is how much? L by root 2. And this is because of this one. Because of this one, it will be same. Because of this one, it will be same. Because of this one, it will be same. So it will be 4 times. It will be 4 times KQ upon L by. So we can, this will be 2 into 4 is 8. Okay. This is not, this is L by root 2. So this we can further write as 4 root 2 KQ by. Is it clear, guys? Give me a thumbs up in the live chat. Is it clear? Is it clear? Clear. Okay. Okay, great. 146th slide. Okay. I've showed you this type of question also before. Okay. Let's follow this question. Great, great, great. Let's follow this question. Yes, this is the geometric progression question. We have a charge q which is at 1 meter. We have a charge q which is at 2 meter. We have a charge q which is at 4 meter. We have a charge q which is at 8 meter. And we have a charge q, it is going on. Okay. And this is origin. And because of all the charges, we are supposed to find the net potential at this point. Sir, net potential will be, we know if there is a charge, it creates potential. What is the value of that potential? K Q divided by R. At what distance you are finding the potential? Now, sir, here potential will be because of this charge at this point. It will be because of this charge, this charge, this charge, all the charges. So because of first charges, which is at 1 meter, potential will be K Q divided by R. R is 1. Plus, because of this charge, potential at this will be K Q divided by 2. Because of this charge, it will be, sir, K Q divided by 4. Yes. And then we say, because of this charge, it will be, sir, K Q divided by 8. And it is so on. Now, in all of these, what can we take common? We can take common as KQ. And then what remains? It is 1. Then we have plus. See, I'm writing all of these potentials from this point to this point, distance is 2. From this point to this point, it is 4. It will be 1 plus 1 by 2 plus 1 by 4 plus 1 by 8 plus so on. Can I write it something like this? Now, this is nothing but a geometric progression. I have told you how to find the sum of, how to add these terms, how to find the sum of geometric progression. We say sum is equal to A upon 1 minus R. Sir, what is A? A, I have told you in the previous question, A is first term. First term in this is 1. That is 1 upon 1 minus, what is common ratio? R is common ratio. How do we find the common ratio? I have told you this also. Take any term that is 1 by 4. Take any term 1 by 8 or 1 by 4. Divide it with the term which comes before it. So 1 by 4, before it, it is 1 by 2. 1 by 2. 2 ones, 2 twos. So it is 1 by 2. 1 by 2. The value of R is 1 by 2. So once we solve 1 upon, this is 2 minus 1 by 2. 1 upon 2, it will come out to be 2. So the answer of this, so we say, sir, V net in this case will be KQ and this KQ, and instead of this, I'll write the 2 directly. 2KQ. This is the answer. Let's move on to the next one. Electric potential due to a ring. Thank you. Okay. Now we have over here electric potential due to a ring on its axis. Now see, sir, you said if there is a charge, it creates the potential. Okay. And if we have a charge Q at R distance, potential is nothing but KQ by R. Okay. Now I am asking you the simple question. If this charge, I place it on a ring, I distribute this charge on a ring. This is plus, 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 plus. I distribute this charge on the ring. Now, over here, the radius of the ring is capital R. Now, sir, if the ring has charge Q, I say ring has charge Q q on it. A ring has charge q on it. So it will create potential. So it will create potential. Whenever there is a charge, it creates potential. Whenever there is a charge, it creates potential. At r distance, because of point charge, it is kq by r. Now we are distributing that charge on the ring. Because of the ring, we are supposed to calculate the potential. Because of the ring, we are supposed to calculate the potential. Let me know if everything is getting clear to each and every single one of you over here. Is everything getting clear to you over here, guys? Let me know in the live chat. Yes. Now listen to me very carefully. So ring has a charge on it, so it will create potential. I say to find the potential, at x. We are supposed to find the potential at x. We are supposed to find the potential because of the ring at x. You say, sir, how do we find the potential because of the ring? See, we say, just remember directly, because of this ring, potential at this x distance from the center, it will be k. How much is the charge? How much is the charge, sir? Q upon under root of r square plus x. This is the potential. We represent potential with V. This is the potential because of a ring at point P at x distance. Yes, sir, clear? Yes, sir, clear? Now, you guys tell me one thing. Sir, this is the potential because of ring at x distance. Cool. I understand. Now, I say, sir, at center, you have told us the value of x is 0. If you keep on reducing this x and once you reach the center, x is equal to 0. Because from x only we start measuring the x. At center, x is equal to 0. Put the value of x is equal to 0 over here. You will get v is equal to kq upon the root of, this is r square plus 0. This and this will get cancelled. So it will come out to be kq by r. So at center, potential is not 0. It is kq by capital R. It is kq by capital R. One more thing. Sir, at center, we got as v is equal to kq by capital R. If x is much less than r, means we are saying that this is the ring, this is r radius, and over here we are finding x. Very close to the ring. This is very close to the ring. Sir, because of the ring, potential is kq upon r square plus x square under root. So it is nothing but potential at x distance. If x is very small, in that case, how much is the potential? We say it will be v is equal to kq upon under root of r square plus x square. Now x is very small compared to r, so we can neglect x. So we say this will again come out to be v is equal to kq divided by r. Even if you say potential at the center of a ring is kq by r, and or if you say potential very close to the ring, it is also kq by r. Then when it comes to if r is much less than x, means over here this is the ring, radius is r. You are saying, sir, at a very far distance over here, this r becomes very small as compared to the x. Now in such case, what is the value of potential? V is equal to kq upon under root of r square plus x square. Here r is small, we take r as, we neglect r, so we say this is x square. This and this will get cancelled. V is equal to kq by x. I have told you all the cases. Sir, in case of a ring, potential at x is kq upon under root of r square plus x square. And sir, at center it is kq by r. And if x is much less than r, v is equal to kq by r. Okay. And if r is much less than x, then v is equal to kq by x. Let me know in the live chat if this is clear to each and everyone. Let me know in the live chat. This is a very good question. Very important. I want you guys to solo this also. Is it clear to each and everyone? Let me know in the live chat, guys. Is it crystal clear? Is it crystal clear? Is it clear, guys? Yes, 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 yes. Great, great. Okay, solve this question. Solve this question. I want you guys to solve this question. Okay. Yes, I want you guys to solve this question. I want you guys to, and the guys who have not liked the session, guys, I want you to like the session as soon as possible. Okay. Now, in this particular case, we are supposed to find VA minus VB. See. Over here, is it visible clearly? Q minus Q. Yes. See, we have got a ring. On this ring, plus Q charge is present. We have got another ring. On this charge, minus Q charge is present, negative charge. The radius of the ring is R. The radius of the ring is R. And the center of this is A. The center of this is B. Such that the distance between the two is X. And X is much, much greater than R. Okay. You are supposed to tell me what is the value of VA minus VB. That is potential at the center of this ring minus potential at the center of this ring. Just subtract them and you'll get the answer. Let's first find the potential. Let's first find VA. Okay. Sir, let's first find VA. That is potential at the center of this ring. Listen to me very carefully. Sir, at point A, potential will be because of two rings. First is this one. Second is this ring, because both the rings have got charge. Sir, for this ring, this point is the center. Sir, for this ring, this point is the very far distance. And we know how to find the potential at center. Sir, the value of potential at center is KQ by R. KQ by R. R is the radius. Sir, because of this ring, potential at center is K. The charge on this ring is Q divided by the radius of this ring is R. Crystal clear, sir. Now, potential because of this ring, potential because of this ring at this. Now, use this formula. Sir, potential because of a ring at very far distance, that is KQ divided by X. Because you are seeing at X distance, X is very far. Now, in this case, we say this is minus charge. So it will be, instead of plus, I write minus. This will be K. This charge is Q. This charge is Q divided by, because of this ring at very far distance, X is much, much greater than R. So it will be X. Similarly, if I ask you, what is the value of VB? You say, sir, potential at this point B. It will be, B is the point for this circle. For this ring, it is center. For this ring, it is at X distance. So at point B, potential will be, because of this ring, it is minus K Q divided by R, because at center point. Similarly, because of this ring, at this point, potential will be plus K. Charge on this is Q divided by this distance is X. You got the value of VA, you got the value of VB. Now VA minus VB will be simply, sir, what is VA? That is KQ divided by R minus KQ divided by X. Okay, then you have minus then you have formulas minus. VB, what is VB? VB is this one, that is minus KQ divided by R plus KQ divided by X. So we can clearly see over here, sir, this will be KQ by R minus KQ by X. Minus into minus becomes plus. This is KQ by R and this is minus KQ divided by X. Minus into minus is plus, minus into plus is minus. Now see, KQ by R, KQ by R, it becomes twice KQ by R. So we say VA minus VB is equal to 2 times of KQ by R, 2 times of KQ by R, and minus KQ by X, minus KQ by X. It becomes minus 2 times of KQ by X, 2 times of KQ by X. Take this common, 2 times of KQ will take common, 1 upon R minus 1 upon. This is the net potential. Is this clear to everyone? Is this clear to everyone? Let me know in the live chat, boys and girls. Is it clear, guys? Show some fire symbols, thumbs up. Potential due to a hollow solid sphere, hollow conducting and solid non-conducting. Great, 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 great. Now see. Now see. Potential due to a hollow and solid sphere, hollow conducting and solid non-conducting. Okay. I have told you, sir, hollow sphere means in which charge is present. Charge is present on the surface. And solid sphere is that sphere in which charge is present inside the sphere also. Here charge is present on the surface. Now, if there is a charge, it will create potential. I write it will create potential. It will create potential. We have to find the potential at 3 points. First one is V outside. Second one is V surface. And third one is V inside the sphere. Sir, when it comes to the outside, V outside will be same as that of a point charge, because I have told you, from very far a distance, even if you have a bigger sphere, it will appear to you as a point. So we'll be using the same formula for this sphere outside as the formula point charge. So that is K, this charge is Q, divided by this distance is R at a distance R. So because of this sphere at small r distance, potential is K Q divided by R. So this is the potential. This is the potential outside at small r distance. Now, if I say, sir, at a surface, small r is equal to capital R. If I say, sir, at surface, this small r becomes equal to the capital R. So in that case, we say, sir, V surface would be K, this Q divided by, instead of small r, I write capital R. Instead of small r, I write capital R. Okay, fine. Now, when we talk about inside, sir, inside over here, I know there is no charge present inside. But the potential which is on the surface will be same as the potential inside. I can give you the logic over here also, but it will take a bit of my time. Let me show you why. Because when it comes to the work done is equal to Q delta V. Okay. So what is the change in potential? What is the change in potential from the surface to infinity. In this case, we say change in potential is 0. Work done in this case will be 0. Or forget about this one. We say work done is equal to delta U. Work done is equal to delta. Forget about this equation. Work done is equal to delta U. Work done is equal to change in potential energy. If I say you have a charge over here on the surface, electric field inside is equal to 0. You have to move this charge from surface to inside. Inside there is no electric field. Do you have to do any sort of work done in bringing the charge from infinity to this point? Sir, no. So I can say in that case work done will be 0. And if work done will be 0, this change in potential will be 0. Change in potential will be 0. Surface potential is equal to inside potential. And forget about this one, whatever I am saying over here. Later on, I'll be telling you this. As of now, you just remember few points. That is nothing but if you have a sphere, hollow sphere. Outside the hollow sphere, potential is kq by r, small r. Sir, on the surface, potential is kq by capital R. And when it comes to the inside, at this small r distance inside, potential is same, that is kq by capital R, which is on the surface. Okay. Guys, is it clear to each and everyone? Is it clear to each and everyone? Okay. Now we have a solid sphere. If somebody asks you to plot the graph between V and R, sir, inside potential is, sir, K is constant, Q is constant, and radius of this is constant, so this is constant. So inside potential will be constant till surface. From center to surface, potential is same, kq by r, kq by r, kq by r. So it remains constant. So, and afterwards we say outside, V is inversely proportional to r. So graph would be this. Important graph, V is inversely proportional to r. V is inversely proportional to r. This is outside, and this is inside. Okay, and inside this is constant, and this is surface. R is equal to capital. Now let's talk about potential due to a solid sphere. Potential due to a solid sphere. Solid sphere is that sphere in which charge is present inside also. Here, charge is present inside also. Here, charge is present inside also. Now, so it will create potential. So we say we have a sphere. Inside the sphere, the charge is present. It is made up of charge itself. And we are supposed to find potential because of this. First is, sir, outside. Second is, sir, surface. And third is we say inside at this point. Let's suppose small r distance. Small r is variable. Sir, when it comes to V outside, because of a solid sphere, how much is the potential outside? You say, sir, that is K. Q is the charge on this inside the sphere divided by R. R is at what distance you are finding, because outside we consider it a point charge. We consider it a point charge. Now, if I say on the surface, can I say small r is equal to capital R? Yes, 110% small r is equal to capital R. Because if you keep on reducing this small r at surface, small r becomes capital R. Yes, sir. So we say on the surface, Vs will be Kq divided by, instead of small r, I'll put the capital R. Is it clear to each and everyone? Yes, sir. But When it comes to inside, inside the formula is bit long. Inside the formula is bit long. Let me just tell you, sir, because of the solid sphere, charge is present inside also. So electric field inside will be, we say potential inside will be different. Let me tell you. That potential will be, this is K is constant, and Q is the charge present inside the sphere, divided by KQ divided by, we say 2R cube. Sir, what is this R? R is the, capital R is the radius of the sphere. Remember this formula, capital R is the radius of the sphere. And then you have KQ divided by 2R cube. KQ divided by 2R cube. Then you have 3R square. Then you have 3R square. R is once again this one. Then minus R square, small r square. See, how do you remember it? You write KQ divided by 2R cube. If you take 2 over here, 3 over here, then when you move on to the upper side, just interchange these two. Take the 3 over here, 2 over here. See, 3R square. Just you are interchanging this 3 and 2. 3R square minus small r square. This will be the potential inside. This will be the potential inside because of, this will be the potential inside. Potential and electric field total mess with my mind. This is easy. Electric field has got different formulas. And when it comes to electric field, you say, sir, KQ by R square, KQ by capital R square. And inside it is KQ R small r upon capital R cube. Guys, are you able to understand what I'm trying to say? If you have a solid sphere, inside this solid sphere, you have a charge. So we are supposed to find the potential at 3 positions. The first one is outside, second one is surface, third one is inside. And this is outside, this is surface, this is inside. We'll verify this also. Let's take this formula. Sir, when it comes to inside, we say, sir, it is nothing but KQ upon, that is KQ upon 2R cube. Then we have 3R square minus R square. Okay. Now, sir, if I say at center, see, sir, at center, could you please tell us what is the potential because of a solid sphere at center? Sir, we can clearly see that if we keep on reducing this small r, at center small r becomes 0. At center small r becomes 0. So we say at center small r is equal to 0. Now we say, sir, V in is equal to, this will be KQ divided by 2R cube. And then we have 3R square minus, instead of this r, you have, sir, this is nothing but a 0. Now this is 3R square. This R square and this cube will get cancelled. So can I say what remains over here? B inside will come out to be, this 3 comes out 3. This is K. This is Q divided by 2R. Yes, sir. This is center. V at center. V at center. VO. Guys, are you able to understand? Are you able to understand this one? This is the potential at center. This is the potential at center due to a solid sphere. This is the potential at center due to a solid sphere. I'm falling in love with electrostatics, sir. If I get more comfortable when I am solving questions, I'll be confident, and that's great. That's great. Okay, cool. Now, if I ask you to tell me the graph between V versus R in case of solid sphere, you are supposed to plot the graph between potential and radius. Okay, now see, sir, on this line, let me plot it over here. This is V and this is R. See, sir, if we have a solid sphere, okay, this is the solid sphere, this is a solid sphere, this is a solid sphere. Could you please tell me what is the potential at center because of a solid sphere? Sir, potential at center is 3 by 2. This is 3 by 2 kq by r. Okay. 3 divided by 2, it means 1.5 kq divided by r. Okay. And what is the potential at the surface? What is the potential at the surface of solid sphere? That is kq by r. Let me just write over here. V surface is equal to kq divided by r. Now see, this is 1.5 kq by r. This is 1 times of kq by r. Obviously, potential at center is greater than potential at surface because this is 1.5 times, this is 1 times. Now, if I have to make the graph, see, this is R, this is V. At this point, R is equal to 0 because from here R we start measuring. R is equal to 0, 1, 2, 3. And we know in case of a solid sphere, R is equal to 0 at center. Means this is the center. Now you tell me one thing. Sir, when it comes to the center, at center means R is equal to 0. What is the value of potential? That is 1.5 kq by r. That is highest. So I say this is the potential at center. That is VO is equal to 1.5 times kq by r. Then if we decrease, then if we keep on moving till the surface, sir, what is the potential on the surface? That is kq divided by r, capital R. And obviously that is less than this one. So if we keep on moving from r is equal to 0 to surface, this is r is equal to r, which is surface. Which is surface. This is center. This is surface. So we say at surface, the potential is bit less. The potential is bit less. Okay. As compared to, this is Vs, as compared to the center. So it will graph will decrease. And then when we talk about the outside, sir, outside kq by r, sir, outside potential is nothing but, we say outside potential is nothing but, that is kq divided by r. So over here, V is inversely proportional to r. Over here, V is inversely proportional to R. So the graph would be something like this because V is inversely proportional to R and this is the surface. This is the surface. And this is V out is inversely proportional to R. This is the graph outside and this is the graph inside. And this is the surface. Very, very, very important graph. Is the graph clear? Is the graph clear? See, at center it is more because at center potential is more. Then it keeps on decreasing. At surface it will be less. Then outside it is inversely proportional to x, so rectangular hyperbola. Now we have only 2 topics left and we are done. Only 2 topics left. Is everything clear, guys? Only two topics are left, okay? Mhm. Yes, yes, yes. You are sending me the fire in order to motivate me, in order to boost my energy, huh? Great, 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 great. Okay, let's finish these two topics and we are good to go. Okay, okay, okay. Now, electric potential due to a dipole. Now, we have to find the potential because of a dipole. See, I told you, whenever there is charge, there is electric field. Whenever there is charge, there is potential. There is charge, there is potential. There is charge, there is electric field. Now, sir, in case of a dipole, dipole also contains the charge. We say this is minus q and we say this is plus q. Now, in this particular case, sir, when we make a dipole, let's suppose this is a dipole that is minus q charge over here. This is the dipole, this is plus q charge over here. Two equal and opposite charges separated by a distance d. Now, sir, in this dipole, it consists of a charge. So whenever there is charge, it creates potential. I say dipole has charge, so it will create potential. So it will create potential. Now we have to find the potential at this particular point, which is at a perpendicular bisector. Perpendicular bisector. You say, sir, because of this positive charge at this distance, because of this negative charge which is at this distance, the distance is same. At this point, can you tell me what is the potential? You say, sir, potential at perpendicular bisector is nothing but potential due to negative charge plus potential due to positive charge. Sir, potential due to positive, if I say suppose this is r distance, this is r, so we say, sir, potential because of this, just a second, we say potential because of this will be same as potential because of this, but signs are opposite. So I'll directly write over here, potential at this point will be 0. Okay, because they will cancel each other. Simply remember, sir, because of a dipole, potential at perpendicular bisector is 0. Now, at this point on the axis, it is mentioned at this point on the axis. Over here, this distance over here, sir, on the axis, which is from the center, this distance is x. The potential is nothing but that is kp by x square, Okay, that is what I'm saying over here. If you have a dipole at this distance, let's suppose this is x, the potential is 0. Now from this distance at x, at axial position, we say potential is kp divided by x square. Sir, x is what? X is the distance from the center of a dipole till this point on the axis. Okay, so we say on the axis, potential is kp, p is the dipole moment, p by x square. And on perpendicular bisector, potential is 0. Keep this thing in your mind. Okay. Now, next is basically the equipotential surfaces. Equipotential surfaces. Sir, what does an equipotential surface mean? Equipotential surface means that surface on which potential is same everywhere. What does it mean? If I say this is a equipotential surface, means potential at this point is same as potential at this point, same as this point. So potential at every point will be same. That's why this is equipotential. Equipotential means same potential surface. That surface in which on which potential is same everywhere. That surface on which potential is same everywhere. Now listen to me very carefully. If let's suppose we have a charge plus q over here. If let's suppose we have a charge plus q over here. And we say sir, at r distance, can you tell me what is the value of potential over here at r distance? You say, sir, V is equal to kq by r. Yes. Now from this side at r distance, what is the value of potential? You say, sir, same kq by r. Now at r distance from this side, potential is kq by r. From r distance, from this point at r distance, potential is kq by r. kq by r. Now, if we keep on joining these points, okay, it forms a surface. So we say this is the surface where potential is same everywhere. Sir, how? Because at this point potential is kq by r. At this point potential is kq by r. At this point potential is kq by r. Every point potential is same. Like if you have a point charge, sir, go at r distance, potential is kq by r. Go at this point, potential is kq by r. At this point potential kq by r. At this point potential kq by r. At this point potential kq by r. Now join all of these points, it forms a surface. That surface is called equipotential surface. It is that surface upon which potential is same everywhere. So for a point charge, what is equipotential surface? A spherical surface. I hope you got it. Now, if I say the potential difference between the 2 points on equipotential surface is 0. Sir, how? Listen to me. If I say, sir, this is a point charge, okay, around this point charge, this is the equipotential surface, spherical. Cool. Can I say, you tell me, at this point, which is at r distance, what is the potential at this A? Let's suppose this is A. Sir, at this point from this charge, potential is V is equal to kq divided by r. And if I say, sir, at this point B, what is the potential? You say, sir, V is equal to kq divided by r. Okay. Now, sir, can you find VA minus VB? You say, sir, VA minus VB will be nothing but this is kq by r. kq by r. And what is this? This is, sir, minus VB. That is, this is also kq by r. This will come out to be, sir, 0. So that's what I'm saying. Sir, if the potential is same everywhere, so difference will be 0. The potential difference between 2 points on equipotential surface is 0. That's what I'm trying to say over here. And then if I say next, no work is done by electric force in moving a charge from equipotential surface. If I say we have this surface over here, this surface is equipotential surface. This surface is equipotential surface. Now in this case, if I say, sir, this is point A, this is point B, okay, and we know, sir, potential at A is equal to potential at B. Why? Because this is an equipotential surface. Now I am saying that if I take a charge from this point to this point, from A point to B point, I'll have to do work. We say no. Over here, work done is 0. If you move a charge from on equipotential surface from A point to B point, C point, D point, no work has to be done. Work done will be 0. Sir, how? Give us proof. Let me just tell you. We know work done is equal to change in potential energy. I want you guys to divide with Q over here, divide with Q. Once again, you can cancel it. Now, sir, W divided by Q is nothing but, this is potential energy per unit charge. I have told you, potential energy per unit charge is nothing but potential. I call it delta V. So potential energy per unit charge is potential. Potential energy per unit charge is potential. Take this Q over here. W is equal to Q delta V. W is equal to Q delta V. W is equal to Q delta V. Okay. Now listen to me very carefully. Listen to me very carefully. Listen to me very carefully. Sir, as VA is equal to VB. Sir, we just got it. That is nothing but VA minus VB is equal to 0. What is VA minus VB? Delta V is equal to 0. Sir, on potential, on equipotential surface, we know, sir, change in potential is 0. Difference in potential is 0. Now, if delta V is 0, we say Q into 0. This will come out to be 0. That's why I say work done. This is work done in moving a charge on equipotential surface is always 0. Is always 0. Next point is electric field is perpendicular to equipotential surface at all the points. Electric field is perpendicular to equipotential surface at all points. What does that mean? Let's suppose we have a charge Q, okay? And sir, we know because of the charge, electric field is away from the charge, positive charge. Electric field is away from the positive charge. Electric field is away from the positive charge. Electric field is away from the positive charge. And if I draw an equipotential surface over here, if I draw an equipotential surface over here, it will be spherical. Now you tell me one thing. This is the electric field line. This is the equipotential surface. What is the angle between these two, sir? This is 90. Sir, this is the electric field. This is the equipotential surface. What is the angle between these two? That is 90. It is mentioned. Electric field is perpendicular to equipotential surface. See, this is electric field. This is electric field. Electric field is perpendicular to equipotential surface at all the points. Is it clear, guys? Is it clear, guys? Okay, we have a question over here. We have a question over here. This was the question which was asked in NEET 2020. Now, in this particular case, this is the homework I'll give you. Homework. Okay, you guys are supposed to solve it. This is your homework. Okay, electrostatics of a conductor. Electrostatics of a conductor. Electrostatics of a conductor. Is it clear? Okay, now electrostatics of a conductor. What does this concept exactly tell us? Listen to me very carefully. Let's suppose if we have a charge over here. Let me just show you over here. Let's suppose if we have a charge over here plus Q. And over here, I am placing a sphere, which is a neutral sphere. The amount of positive charge is equal to the amount of negative charge on the sphere. Okay, this is a neutral sphere. Now, in this particular case, sir, this is a neutral sphere. We know, sir, because of this positive charge, electric field is being created over here. Sir, whenever there is a charge, there is electric field. So this positive charge will create electric field over here. And that electric field, let's suppose this is distance x. That electric field will be K. This charge Q divided by x square, KQ by x square. This charge Q divided by x square. Now, over here, my question to you is, this sphere is placed in this external electric field. This is called external electric field. And we know whenever we place, and this sphere contains positive charge, negative charge, positive charge, negative charge, positive charge, negative, positive, negative. And whenever we place a sphere inside an electric field, the negative charge experiences the force opposite to the direction of electric field. I have told you, if this is the electric field, if you place minus q charge over here, it experiences the force opposite. And if you have this electric field, if you place a charge over here, it experiences the force along the direction of electric field. Yes, yes, sir. Now over here, listen to me very carefully, guys. See, sir, in this particular case, the negative charge will experience the force. 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 Okay. So, because of this positive charge, negative charge will be attracted somewhere around over here, and positive charge will experience the force opposite to the direction of electric field. Now we say inside also electric field is being created. Listen to me, I'll tell you something. If I say I have a positive charge, if I say I have a negative charge, could you please tell me, sir, because of positive charge, electric field is away from the charge, and because of negative charge, electric field is towards the charge. Now, as a whole, in between these two, what is the direction of electric field? You say, sir, it is from positive charge towards negative charge. Now, over here also, if positive charge is from, if electric field is from positive charge towards negative charge, so can I say over here also electric field will be from positive charge to negative charge? And this is what we call the induced electric field. What I'm trying to say, we have a charge plus Q, and we have a sphere over here, metallic sphere. Now, because of this plus Q, electric field is being created, external electric field, that is KQ by X square. Now, because of this electric field, charge separation will take place. Negative charge gets separated over here, positive charge gets occupied over here. Inside also, because of the charge separation. Now see over here, because of E external electric field, charge separation takes place in the sphere, metallic sphere. So I say E inside is created. E inside is created. Now, what will be the value of this E inside? The value of E inside is exactly the value of E external, but in opposite direction. So we say this E inside will be exactly same as this one, but in, see, external electric field is in this direction. Induced electric field is in this direction. So that's why minus, this is KQ divided by X square. Magnitude will be same. And if somebody asks you what is the value of net, you say, sir, net will be nothing but a 0. Why? Because one electric field is in this direction. Same electric field is in the backward direction. So net electric field is 0. Net electric field is 0. Now, if I ask you the question in this particular case, this is the question. You are supposed to tell me what, this was the question asked in JE. Find the E net, E induced and E external. The positive charge is placed over here. And we know, sir, because of the positive charge, E external, electric field would be something like this. E external is nothing but how much? That is KQ divided by R square. And we know because of this external electric field, charge separation takes place. But over here, positive charge, these charges gets occupied at the corners. Make sure you make it over here, okay? This is a property of a conductor, okay? It gets occupied on these corners, sharp edges. So negative charge is somewhere around over here, okay? So electric field induced is also created. And this electric field induced will be exactly equal to external electric field. So E induced is equal to negative of AQ by R square. And net is equal to 0. Next is, this is a very important question. And I am keeping this as a homework. Okay. See, we have a sphere. On this sphere, charge Q2 is present. And we have a bigger sphere. On this bigger sphere, charge Q1 is present. You are supposed to tell me the electric field because of the two spheres at point A, at point B, at point C. And then you are supposed to tell me potential at point A, point B, point C because of the two spheres. Thank you so much, guys. Do comment down below. Okay, this was all about it. We are done with this session. Next will be capacitors. And this was my first session on Unacademy NEET English. Let me know how was the session, how was the energy in the live chat. Not in the live chat, in the comments later on when the stream ends. Okay, maybe it will end tomorrow. So tomorrow you can comment over there. Okay. Thank you so much for showing this love and support. Thank you so much. Thank you. Okay, guys, I gotta go. You also go. We'll talk tomorrow now. I'm feeling tired. Huh? So see you guys tomorrow and take care and bye-bye. Do let me know later on the comments down below when the stream ends. How was the session and everything. Thank you so much.